Hey YouTube, in this super long video, I'm actually putting together all the individual videos where I'm implementing various NLP projects with the super popular transformer networks and using some of the very well-known pre-trained models from HuggingFace. And in most of the projects, I'm also fine-tuning the pre-trained models with TensorFlow or PyTorch on my custom dataset. And also beyond the individual videos which are already there in my channel that was published earlier, here in this video I'm also adding some of small parts wherever it's needed. So enjoy this long video and absolutely master Transformer. Word embeddings in BERT. That's the most fundamental and crucial concept when you are working with BERT. In this video, we will see some very simple example to understand word embeddings. Basically, this is the flow of string words being converted into a vector in BERT. So the input is a pure string or text that gets converted to a set of tokens, and then the token goes through a embedding layer where it is vectorized, and that results in these final set of vector or embeddings. And these vectors are not just any vectors, they have contextual meaning. To understand this, let's consider this sentence. She is a machine learning engineer and works in California. Say we need to extract the contextual embedding of each word in the sentence. To do this, first we tokenize the sentence and feed the tokens to the pre-trained BERT model, which will return the embeddings for each of the tokens. And that's exactly I'm going to do through these steps. So first you need to install transformers, and then I'm also importing this BERT model and BERT tokenizer. Both of them I need for tokenizing and then applying the model. And my model is defined as this pre-trained model BERT base uncased, one of the most popular pre-trained model available in HuggingFace Hub. So and this is my sentence. She is a machine learning engineer and works in California. And the first thing I do to tokenize the sentence is define a tokenizer variable like this, BERT tokenizer from pre-trained, and to that you pass the path of the relevant model that you are using here, which in this case is BERT base uncased. So that's my tokenizer, and then I just apply the tokenize method on this tokenizer to get my tokens. Let's run this. And then I just print the tokens, and they are my tokens. She is then look at this is an extra thing that has been added by the tokenizer because machine learning has been divided into these actually four tokens: machine, then hash LEA, again hash as RN, and then ing. Engineer and works in California. So those are my tokens. Now let's add two extra tokens to my original tokens, and those two tokens are CLS and separator. CLS is for represent classifier, and separator is a separator between two sentences. So that's what I'm adding to the original token. Run this, and also run print the updated tokens. And now let's see. So now I have two extra tokens. So now after adding these CLS and separator, our token length has been increased by 2 and has become 14. Previously it was 12. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Yeah. So now it is 14. Now let's say that following the same way that the way that we tokenized a single sentence, we can tokenize all the sentences in our training text corpus. But there is a problem actually, that the length of each sentences varies in any text corpus, right? And so does the length of the token. Because when the sentences varies, obviously the token length of the sentence will also vary. But the problem is that to feed the text corpus to a model, we need to keep the length of all the tokens the same. And say to keep the token length same, we keep the length of all the tokens at 16. I'm taking 16 just as an arbitrary number. There is just for an example. So we keep the token length 16 for the entire sentence. That is, no sentence should be having more than sentence as the token length. So if we look at our preceding example here, the token length is 14. So to make it 16, I need to add some pad to the token. And so I add the pad like this, tokens plus pad plus pad. And that is, I added two pads to make the token length 16. And I can run this updated token again. And here, I can actually do len over here. And I add the pads, two pad like this, tokens, and then I add one pad and then the next pad. And now I print the length of the token again, and now it is 16. So the next step is to make our model understand that the pad token is added only to match the token length and it is not part of the actual tokens. To do this, we introduce a concept called attention mask. So we set the attention mask value to 1 in all actual positions, that is where there were actual tokens, and we set the attention mask to 0 to the position where we have a pad token. And I do that with this little list comprehension node. I loop over the tokens, and wherever it is not pad, I set it as 1. That is 1 if I not equal to pad, and other places I set it at 0. And now print my attention mask. Let's run this code and then run this one. Cool. So we can see 1 for all these places where we have actual tokens and 0 for the last two position, because these two positions were the pad position. So there were actually no real tokens. We just added these boxes or added these cells or added this position to match the length of the whole tokens to be equal to 16. And that is the very basic and very fundamental concept of tokens and attention mask in any transformer model or any BERT model. And the next concept that we discuss is unique token ID, which is about mapping all the tokens to a unique token ID. And we do that with a method called convert tokens to IDs. And this is a simple code, tokenizer.convert tokens to ID, and pass to that method we pass the tokens, and that will produce token IDs. So let's print this token ID and let's see what they produce. Right. So as we can see, these are actually token IDs of each of the tokens, and the last two positions are 0 because they represent the padding. So here, if we match up with the original token, so let's just copy it. Let's just copy our original token list, which was this, right? Copy it and bring it down. Okay, so these are our tokens. Sorry, I pasted in the wrong place. Let's delete this one. Where is our unique token? Yeah, here it is. And okay, so these are our actual tokens, and the unique IDs are these. So here actually it means that the first token CLS is represented or captured by these unique ID 101. Then the next one this is another token, and this is captured by this unique ID 2016. Similarly, is represented by 2003 and so on. Delayed. So these token IDs are indices in a vocabulary. The IDs, that is the token IDs themselves, are not used during the training of a network. Rather, the IDs are transformed into vectors. Say you are inputting three words and their input IDs are 12, 14, and 4, just as an example. So what is actually is given as input to the model is three vectors, say each of n dimension, where each ID, that is each token ID, is mapped to a unique vector. And that vector in the case of many BERT model is represented as 768 dimensional, which represent each token. So in case that, let's take this as an example. In case we have 30,522 tokens, then we will have 30,522 vectors, each of dimension 768. And that will become your embedding vector to be fed into the BERT model. All right, now let's proceed. So now these token IDs and the attention mask are kind of ready to be fed into the model. And which is our model? That is what you already defined at the very top, which is BERT model from Pretrained, BERT base uncased. So before feeding these attention mask and the token IDs, I need to convert them to torch.tensor and also apply unsqueeze to the list, that is to the existing tensor. Torch.tensor token IDs, and then similarly for attention mask. Okay. And next, actually feeding this token ID and attention mask to the model. Cool, run it. All right, so that is the output of the model, and if we print just the output, this is the big representation that we get of the output variable. So here we can see two things mainly. First, they're just telling me that the model that we have used, which is BERT base output with pooling and cross attention. Then I have last hidden state, which is a tensor. That's a three-dimensional tensor we can see here. And we also get a pooler output. That's also a two-dimensional tensor. And then I get, what else do I get? Let's come down. That's a big tensor. So then I get the attention, cross entropy, post key values. They are all none. So let's go one by one through them. So last hidden state, this is one of the most important thing that you will work with in many transformer project, because that's what you take as a body of your base model, and top of that you add another head or another classifier. So the last hidden state contains the hidden representations for each token in each sequence of the batch. And the size, if you print last hidden state here, that is you get the last hidden state by doing output and taking the 0th element, and if you do a shape on that, you get this tensor, which is of size 1 by 16 by 768. And this size actually represent the first dimension is batch size, then the second one is sequence length. Our sequence length is 16 because we had 16 token. So these actually represent the number of tokens or the max token in case you have already hit the maximum token limit of the relevant model. And the last dimension is, this is the hidden size, that is each of these token or each of these vector will be of 768 dimension. And then we have these Pooler output, the next one here. And Pooler output is the embedding of the CLS special token. In many cases, it is considered a valid representation of the complete sentence. And this one is of size batch size by hidden size. And that's why it's a two-dimensional tensor, whereas the last hidden state was a three-dimensional tensor. And just like the previous one, so this output 0, that is my last hidden state, and you can access the Pooler output by doing output then passing 1, because you are taking the second element from the output. And this is that tensor, which is a two-dimensional tensor. And here if you do let's say the size output, and I take the first element dot shape, yeah, that gives me 1 by 768 that represent the batch size by hidden size. So here in this video, we just discussed about how to extract the embeddings from the pre-trained BERT model. But remember, these are the embeddings obtained only from the topmost encoder layer of the BERT, which is encoder 12, because BERT has 12 layers of encoder. So now the question is, can we extract the embeddings from all the other encoder layers of BERT? The answer is obviously yes, but that will be the topic of a separate video. Alright, that pretty much wraps up this video. If you have liked this one, smash the like button. And also do subscribe, because I'm going to do many interesting NLP projects over the coming days and weeks. So see you in the next one. Thank you very much for watching. Hey everyone, when working with HuggingFace Transformer pre-trained model, one of the fundamental technique we use in most of our project is that we take the body or base model, and then on top of that we add a task specific head to finally build our model. So in this video, we will see an example of that architecture, because the same architecture will need to be applied in many projects involving pre-trained transformer model from HuggingFace. So when we switch from the pre-training task to the downstream task, we need to replace the last layer of the model with one that is suitable for the task. This last layer is called the model head. It's a part that is task specific. The rest of the model is called the body. It includes token embeddings and transformer layers that are task agnostic. This structure is reflected in the transformer code as well. The body of the model is implemented in a class such as BERT model or GPT-2 model that returns the hidden states of the last layer. And to get the hidden state of the last layer, we do something like this. That is output, we take the 0th element, that's equal to my last layer. And the hidden state are passed as inputs to the model head to produce the final output. HuggingFace Transformer provides a different model head for each task as long as the model supports a task. That is, you cannot just use DistilBERT for a sequence-to-sequence task like translation, because DistilBERT is not a suitable model for sequence-to-sequence task. And then we have task-specific models such as BERT for masked LM or BERT for sequence classification, which uses the base model and add the necessary head on top of the hidden states. For example, DistilBERT for sequence classification is a base DistilBERT model with a sequence classification head. The sequence classification head is just a linear layer on top of a pooled outputs. And similarly, for question answering task, you would use DistilBERT for question answering class, or which is a model head. The question answering head is similar to the sequence classification head, except it is a linear layer on top of the hidden states output. And so in this video, I will use a particular dataset from Kaggle, the link of which is given here. It's a news news sarcasm detection dataset in Kaggle, and then I will take a base model, and then on top of that I will add a classification head. And the base model in this case will be DistilBERT base uncased. And so the first thing is just a regular step. I am importing all the necessary modules from HuggingFace and also from Transformers. Specifically, I am importing these load dataset from the HuggingFace datasets module because I want to structure my dataset according to HuggingFace, following the HuggingFace structural pattern and the dataset architecture. Then because I'll be using PyTorch, so I'm just importing the necessary modules of PyTorch. Okay. Now the important thing is I have already downloaded this dataset into my local directory, so I'm just defining a root path for the dataset. It's a JSON file, so I'm just defining the path of that and then reading the dataset with pandas. Read JSON. It is no more read CSV because it's not CSV, it's JSON file, but you can read it as easily as any CSV file. So we can see this dataset structure right now. That is a JSON file right now is structured like this. There are 3 columns: is sarcastic, headlines, and article link. So for our case, for our exercise in this video, this article link will not be important, and the 2 important columns are the headlines of the article and the classification of the labels, whether it's sarcastic. In that case it's a 1, and if it is not sarcastic then it's 0. And that's a whole purpose of this exercise is to predict, given a headline, whether it's sarcastic or not sarcastic. And that's why I am building a classification model on top of DistilBERT base uncased to predict the classification of a particular headline. So basically here I'm just loading the dataset with HuggingFace load dataset. So just note the special pattern that I'm using here. So you pass the load dataset method, which I have imported at the top, and because I'm reading JSON data, so you have to mention JSON here and then also mention your data files. In this case I'm just passing the path. And next I'm just removing column article link because that is not important for the exercise here. And also I'm setting the format to be pandas, and importantly, because HuggingFace dataset are all split into 3 sets, that is train, validation, and test. So here I'm defining with this line the train part, and we will be splitting the dataset into validation and test in a second. And first just some basic pre-processing on the dataset. I'm dropping duplicates from the headlines column. Then I'm doing a reset index with headlines and labels, and then I am also applying from pandas on my initial dataset HF. And then that's the important part here, which is train test split, test valid split. Yeah, so initially I'm just taking a 20% from for test size by doing this dataset.train test split, and this method is coming from scikit-learn. And then further for the test set I am dividing it again equally, that is 50% between between test and valid. And finally, after doing this, I will have a clean dataset dict following HuggingFace dataset dict format, which is train, test, and valid. So all I'm doing here in this line, from train, test, valid, I am taking the train for my train, test. From the test valid, that is from this, I'm taking the test, and for the valid part, sorry, here I need to make a little change. No, actually I'm right here. So note the difference between this first train and this train. Here the train part I am taking from train test valid, which was defined in this line, and that will take 80% of the dataset. Now for the valid part, I am taking from this test valid only the train part, and that's my validation. So actually test valid is already only the 20% of the original dataset. From that, this train will take 50%. That is actually 10% of the original dataset is for valid. And now finally, I'm just printing this dataset HF, and that will print a nicely formatted dataset dict, which is what Hugging Face datasets follows. And we can see the splits here: train, test, valid. And for my train, I have 22,802 number of rows. For test, I have 2851 rows, and for the valid, 2850 rows. Awesome. Yeah, so now a quick reminder that this DistilBERT base uncased, in this model, DistilBERT base uncased, each token is embedded into a vector of size 768, and the shape of the output from the base model is batch size by max sequence length by embedding vector size. And max sequence length is also capped for a particular model, and embedding vector size in this case is 768. I need to check. I think DistilBERT base uncased, if you can go just Hugging Face documentation to check what is the max sequence length. I think it is 512, and that's what I am using in the next line as well. So the first thing, I need to tokenize a batch. So I'm defining a tokenize method here. It will just use my tokenizer and pass it the batch headline part, because headline is my column names, and truncation to true, and max length 512, which is what the max for DistilBERT base uncased. And then my tokenized dataset is just you take your dataset HF, which is this one that we just created, dataset HF, and apply the map method. This map is coming from Hugging Face Hugging Face datasets map method, and this is a very powerful, very useful method. It will apply this tokenize method here on each row across the dataset. And obviously this tokenizer is coming from the tokenizer defined here. It is the tokenizer corresponding to my model checkpoint, which is DistilBERT base uncased in this case. So I'm just doing auto tokenizer from pretrained and passing the checkpoint. Very standard, very boilerplate code here. Nothing, no complexity right here. And tokenizer.model max length, I am defining 512. All right, so at this point, my dataset is completely tokenized, and I am just printing the tokenized dataset, and that should give me the similar structure here. Only thing is that after tokenization, I have some new things or new features added to my dataset, which is input IDs and attention mask. We can see these new columns added to each of my train, test, and valid input IDs and attention mask. Very important, because these two will be the input data or input parameters to my model, based on which the model will predict. Yeah. And now, before proceeding to build my custom model, I just need to do another pre-processing kind of thing, which is use a set format method from Hugging Face to set the dataset format to be compatible with PyTorch. So tokenized dataset. I mentioned torch. I also need to mention all the columns, which in this case will be input IDs, attention mask, and labels. And then I need to define the data collator. I have already imported at the top data collator with padding. So the data collators are objects that will form a batch by using a list of dataset elements as input. These elements are of the same type as the elements of my train dataset or eval dataset. To be able to build batches, data collators may apply some processing like padding. Some of them, like data collator for language modeling, also apply some random data augmentation, like for example random masking on the formed batch. So data collator automatically actually pads some model inputs in a batch to the length of the longest example. This bypasses the need to set a global maximum sequence length and in practice leads to faster training since we perform fewer redundant computations on the padded tokens and attention mask. And now with that, I need to construct my task-specific custom model class that inherits from the that will inherit from nn.module, that is PyTorch's nn.module. So I need to define this class here. Let's zoom out a little bit. So this is my custom model actually, and that's why I'm naming it to be explicit, my task specific custom model. In your case, whatever the task, you name it like that. For example, if you are building a classification, you can name it as my classification custom model, just for example. Here, this is an example exercise, so I'm just building my task specific custom model for the naming. It's inheriting from an nn.module. And also note that in this case, I'm using DistilBERT base uncased, but actually you can use any model in this example, not necessarily a model trained for classification, since we will only use the model's body and leave the head. Head is something we will add. So you can use many other models as well for your base model. And within super, now I'm going to load the model with a given checkpoint and extract its body. DistilBERT model equal to checkpoint, which will be the name of the original model path in HuggingFace. From checkpoint and tension equal to STAT. Okay. And now the new layer that I'm going to add. So before this line, that was my body of the model, and now I am going to add my new head. So self dot first a dropout layer, and also as an ending layer, I'm just going to add a single classifier layer, and that will be a fully connected linear layer. And here you can actually, for depending on your situation, you can actually build out your complete layer. It can be an LSTM, it can be other model, other layers, it can be multiple layers after layers, whatever your plan is. So in my case, this is a simple linear layer. This is in features, which is 768 dimension, and num labels. So the first argument to nn.linear is in features, which is the size of your input samples, and the second argument is your out features, which is the size of each output sample. And just to explain a little bit about these nn.linear, this line of code. So, for example, you define, say, self.hidden equal to nn.linear 784 by 256. It means that in your neural network, this is a hidden layer. That means because it is hidden in between one of your input and output layers, and it is also a fully connected linear layer which takes input of shape batch size by 784, where batch size is a number of inputs which are passed to the network at once, and transforms the input by the linear equation of y equal to wx plus b into a tensor y of shape batch size by 256. So I can just write it here, something like this. So this is what it means, that self.hidden will just transform the 78 batch size by 784 dimension input tensor to a tensor which is of shape batch size by 256 dimension. Anyway, that was only for explanation. Let's delete and let's continue with our class. So next, I need to write my forward function. Yeah. This is the main two inputs to my transformer. Labels equal to none. So first extract outputs from the body of the base model, which will be outputs equal to self.model, and to that I pass input. Attention mask. What else? I need to, yeah, that's it. And now, after I got the body, I need to get the custom layers. So first define the last hidden state, which is last hidden state is always outputs. Take the 0th element. That's my last hidden state. And now from this sequence outputs will be equal to self dot, sorry, yeah, self dot, because I have dropouts, to that I pass the last hidden state, and then the logits. Sequence outputs, and take the everything for first dimension, 0 from the next dimension, and everything from the third dimension. First dimension is inferred, and that's why -1, and the second dimension is 7, 6, 8. Because that's what we defined here. Now calculate the losses. loss function is nn.cross entropy. It's a binary classification problem. Cross entropy loss. logits.view. Enables. Finally, returning from the forward method is a token classifier output. We already imported the token classifier output at the very top. So loss is equal to, oops, what happened? 1 second. Loss is equal to loss outputs hidden states tensions here. And to understand more about this token classifier output, this class, we can look into the official documentation in HuggingFace. So all models have outputs that are instances of subclasses of model outputs. Those are data structures containing all the information returned by the model, but that can also be used as tuples or dictionaries. Let's see an example from Transformers. Import BERT tokenizer, BERT for sequence classification, import torch, and then I get the tokenizer outputs, model inputs. Okay, let's look into our ones, which is so these are all these output classes. For example, they have base model output, they have base model output with pooling. What was our name? Our name was token classifier output, and so this is my token classifier output. It takes loss as a first argument, torch.float tensor of shape 1 optional, and then it takes a logits classification scores, hidden states, attention. Let's go down. Hidden states, which is also a torch.float tensor, and attention. True is paused or when config.output attention equal to true, tuple or torch. Attention weights after attention softmax used to compute the weighted average in the self attention heads. Yeah, so we have already passed all these arguments here: loss, logits, hidden states, and attention. Okay, so remember these attention mask, this particular parameter we supplied here, the significance of these, because this argument indicates to the model which token should be attended to and which should not. So if attention mask is 0, the token ID is ignored. For instance, if a sequence is padded, to adjust the sequence length, the padded words should be ignored, hence their attention mask is 0. All right, before starting off the training, I need to do another thing, which is create a PyTorch data loader, because that will have the responsibility of supplying batch by batch data to during the training. So from data import data loader. And it takes, I have to pause the train here, train part of my tokenized dataset. Oops, tokenized dataset. Shuffle equal to true. Collate function will be my data collator that we have defined earlier. And I have to do the same for the validation part. Other things remain same. I also, for the validation, I don't need batch size because it is only for evaluation, no training. Okay, now get ready to start the training, but just define a few parameters for the training. Transformers, import Adam W, which is my optimizer, also get scheduler, scheduler. Yeah. What else do I need? I need to define the optimizer, which model task specific. Oh, I did not define the model task specific yet, so let's do that before defining all the parameters. So first define the device, just regular code. If CUDA is available, use CUDA, otherwise CPU, and then model task specific would be checkpoint equal to checkpoint. I have only two levels, and then transfer these to device. Cool. To the optimizer, I need to pass the parameters of the model. So what does the documentation say? The params. Yeah, the first one is nn.parameter.parameter, iterable of parameters to optimize or dictionaries defining parameter groups. Yeah, so model.parameters. Define my learning rate as well. And number of training steps would be epoch multiplied by the length of the train data loader. So num right. Okay, and I need to define Taylor scheduler. For this baseline, I just want to keep the number of warm-up steps to 0, so I do not need a warm-up steps actually. Okay. Yeah, that's cool. Okay. Next, for the metric definition for the evaluation, I need to import the load metric from datasets. My metric is F1 score. And now finally, actual training. So this is where I'm going to train my custom model. So first import UDM. training steps. This will be number of people. For key value in batch.items. Supply the model with the batch. Outputs. And also backward propagate your gradients. Optimizer tab. Update the optimizer. Skip. And after this, zero your grad. Program train. Okay, now evaluation. Task specific. Batch is equal to because I'm in the evaluation, so I need to use a context manager of torch.noGrad. And the predictions will just be equal to torch.argmax. It's the probabilities, and I need to get the max probability. So from the logits, I get the max probability across the last dimension. And now time to calculate my metrics, because I have both the actual and also the predictions. And because it's a batch by batch calculation, I need to use the add batch method here. So metric.add batch. Progress for eval. Okay, I should print my metrics here. Metric.compute. PUT. Okay. And next is the post-training evaluation. And that code is rather very simple. So first, model task specific dot eval. Now I need to get my test data loader, which is loader equal to data loader tokenized data set. From that I take the test BERT. That is key value. The structure of code is pretty much the same that we used in the training. So that's my batch, and then I need to define a context manager with torch.noGraph. Specific logits predictions is torch.argmax, just like previously. Across the last dimension. And now metric calculation, metric.add. So I'm just reading the documentation of metric.add batch. Add batch of predictions and references for the metric stack. Predictions are the predictions, references are the actual references, and both are list, array, or tensor. Yeah, that's what I'm doing. Oh, so references is my batch labels, because that's the true value. Okay, at the end, just print the metric.compute. So this is the result that we got. So during the training, our F1 score was coming like this. During the training part, that is when we are going epoch by epoch for the batches. And then for the post-training evaluation on the test data set, the metric.compute finally produced a rather very good, why it's not coming, a rather very good F1 score. Let me, of 0.923. That's my final F1 score on the test data set. So to sum up, what we did is we took the base body of the base model from HuggingFace Hub, and the name of the model is DistilBERT base oncased, and then through these custom class, we added a single linear layer, of course, with a dropout as well. That is our head, and that's how we added the head to the base body of the model and created this whole class. And that whole custom model we applied on the data set to predict 0 or 1, that is a binary prediction of our sarcastic news headlines data set. And the final computed F1 score was rather good of 0.927. Alright, that pretty much wraps up this video. If you have liked this one, smash the like button. And also do subscribe, because I'm going to do many interesting NLP projects over the coming days and weeks. So see you in the next one. Thank you very much for watching. Hey everyone, in this video I will use PyTorch to implement the transformer architecture, focusing specifically on the concept of scaled dot product implementation in self-attention. And this will be entirely from scratch implementation of transformer to see that under the hood how it works. Now, as to the architecture of the transformer encoder decoder model, there's so many beautiful blogs and also videos. So here I'm not talking too much about the architecture, because the focus of this video is on the implementation of transformer from scratch. But still, a very basic introduction needs to be made to make sense that a transformer basically consists of encoder and decoder module. So first, the encoder module is fed with the input text, and the input text is tokenized and converted to token embeddings. Since the attention mechanism is not aware of the relative position of the tokens, we need a way to inject some information about the token positions into the input to model the sequential nature of text. The token embeddings are thus combined with positional embedding that contain positional information for each token. So the encoder is composed of a stack of encoder layers or blocks, which is analogous to stacking convolution layers in computer vision. The same is true for the decoder, which has its own stack of decoder layers. So the encoder's output is fed to each decoder layer, and the decoder then generates a prediction for the most probable next token in the sequence. The output of this step is then fed back into the decoder to generate the next token, and so on until a spatial end of sequence or EOS token is reached. And now this is the representation of the key fundamental concept of the self-attention architecture, which is the scaled dot product attention mechanism. And mainly there are four main steps required to implement this mechanism. We will go through these steps in a moment with just pure Python from scratch. But these are the steps mainly that project. You got your input text. Now from the input text you got your embedding. That is a token embedding from the input text. Now the first step is project each token embedding into three vectors called query, key, and value. Then compute attention score. Third is compute the attention weights. And finally, update the token embedding. That is, once the attention weights are computed, we multiply them by the value vector. For example, these vector v, which represent v1, v2, and so on up to vn, to obtain an updated representation for the embedding. So that's my scale dot product attention calculation. And then this particular module, that is the scale dot product module, comes into the overall scheme of things here. That is, this is the total architecture of my multi-head attention in transformer, and this is the most crucial part, that is the scaled dot product attention, that we will implement in a second with Python. So for my visualization, I'm going to use a package called BERT. So you can actually install that with this pip install BERT. And I have already done that in my local machines, so I can just directly import them here. So let's zoom in. What I'm importing is from BERTviz.transformers neuron view, import BERT model, and also the show method. And we will see the implementation of both of these in a second. I also need my model checkpoint to be defined. So let's just define that. I'm going to use BERT base uncased for this entire exercise. And I also need a tokenizer. For that, I am going to use auto tokenizer, which I have imported already from Pretrained model checkpoint. Let's take any random text. So this will be my text. And now I'm going to use the show method from BERT to see the tokenized visualization of this text. So what I need to do is, oh yeah, I also need the model to be defined before show. Model would be equal to BERT model dot from pretrained model checkpoint, yes. And in the show, oh, spelling mistake. In the show, the first parameter is model, then BERT, then I need the tokenizer, and I also need the text. Let's there's another parameter, display mode. Layer 0, head. And when you run that cell, I'm just running it in my Colab, and you get a visualization like this between the different tokens and their relation. And these line weights are the line width, the total boldness of a line is actually showing how much that is related to a corresponding another text on the right side. Now let's quickly check these tokenization of the tokenizer characteristics or their attributes. So what I'm going to do, inputs equal to tokenizer. Tokenizer takes, these are the arguments. First, it will take the string, then list, and list the sequence, a batch of sequence to be encoded. Each sequence can be string or a list of strings. Okay, so text, then return tensor pt. And I also want to add the spatial tokens. Spatial token means the CLS, ACP, those kind of tokens. So let's do spatial tokens equal to, actually I'm just keeping it at false for now. So this is just to keep things simple. I decided to exclude the CLS and ACP tokens by setting these at spatial token equal to false, and then inputs IDs. And if I run this cell, let's go to Colab. Yeah, input IDs, I will get these output tensor. It's a tensor and it will give all these numbers. So what I did here is that these tokenizer returns a dictionary with all the arguments necessary for its corresponding model to work properly. The token indices are under the key input IDs. So this is that input ID that I just printed. And now yeah, so next step is that I need to create some dense embeddings. Remember, we are in the process of making the scaled dot product from scratch. So for that, the first step is to create a dense embedding, and dense in this context means that each entry in the embeddings contains a non-zero value. In contrast, the one-hot encodings are sparse, since all entries except one are zero in one-hot encoding. So for the dense embedding in PyTorch, we can do this using torch.nn.embedding layer that acts as a lookup table for each input ID. And just want to repeat another thing here again, that is, which is part of the tokenizer, that when you run this line, that is inputs equal to tokenizer, and then pass the text, what it will do is that each token in the sentence has been mapped to a unique ID in the tokenizer's vocabulary. And only then you can get all these attributes like input IDs, which is the token indices of the tokenizer's vocabulary. And now check all the configs from my BERT config. So we already have imported config pretrained. I already have the model checkpoint defined. And what is our model checkpoint? That's this board base uncased. So this will pull all the config for my this particular model based uncased model. And if I print this config, I will get all the configuration. And when I ran it in Google Colab, let's see what I got. Yeah. So when I print this config, I get all these different configuration of the this model, that is BERT base uncased. And these are all the config. For example, these architecture, hidden act, hidden dropout probability, hidden size, etc. And we can see this very properly and clearly mentioned in HuggingFace Transformer libraries documentation. And here's where I'm looking at BERT, and the part of the documentation I'm looking at is this one, BERT Transformers BERT config. And all these config are defined here. For example, the vocab size, this is the vocabulary size of the BERT model, defines a number of different tokens that can be represented by the input IDs passed when calling BERT model or TF BERT model. Hidden size is a dimensionality of the encoder layers and the pooled layer. And then I'm going to create, as we planned, to some dense embedding with torch.nn.embedding module. embedding. The first I'm going to take vocab size. And what's my vocab size? This is the one that I'm going to take. Vocabulary size. A BERT model defines a number of different tokens here. I also need the hidden size. And if I print this token EMB, then what I will get is, I'll get this. Embedding is a vector, and the shape of this vector is 30522 by 768. So basically here I used these autoconfig class to load the config.json file. And when you run this line, that is autoconfig.from pretrain and model checkpoint, that's what you will get. That is the config.json file associated with the BERT base uncased checkpoint. So in Transformer, every checkpoint is assigned a configuration file that specifies various hyperparameters like all these things, that is hidden output, hidden size, vocab size, etc. Which in our example shows us that each input ID will be mapped to one of the 30,522 embedding vectors stored in nn.embeddings, and each with a size of 768. Note that the token embeddings at this point are independent of each context. This means that homonyms, that is words that have the same spelling but different meaning, for example, flies, have the same representation at this point. And so the role of the subsequent attention layers will be to mix these token embeddings to disambiguate and inform the representation of each token with the content of its context. Now let's proceed further with this token embedding. Input start. And I'm going to print both inputs embeds and also the size. Run this cell. What happened? Input in, oh yeah, there's an extra s. Yeah, so that's these tensor, this 3D three-dimensional tensor is the input embeds, and the size of this is 121 by 768. So what we get a tensor of shape batch size. The first one, the first dimension here denotes the batch size, then sequence length, and then the last one is hidden dimension. And now the next step is to create the query, key, and value vectors and calculate the attention scores using the dot product as the similarity function. Import torch h. I need the square root for scaling the vectors. So first, what I'm going to do for now is to create query, key, and value to have the same number, the same actual value indeed. So query equal to key equal to value, which will be equal to input embeds. Inputs embeds. All right. Later, we will see that the key, query, and value vectors are generated by applying independent weight matrices. But for now, I just have kept them equal for simplicity. And in scaled dot product attention, the dot products are scaled by the size of the embedding vectors so that we don't get too many large numbers during training that can cause the softmax to misbehave really. So now get that size dimension of k, that will be key dot size, and take the last one. So this -1 will give me the last dimension of the above tensor. And now I'm going to create the actual attention scores. For that, I'm going to use torch.bmm, batch matrix multiplier. Query key.transpose. And divide this whole thing by the brace will be here. Divide this, what I'm missing here, query key.transpose. Oh yeah, sqrt dim-k. I have an extra brace here. Yeah, that should do. And then I get the score size. Let's take this whole thing to my collab and run this cell. Score is not, oh yeah, these will be scores. Yeah, so I get 1 by 21 by 21. So basically this has created a 21 by 21 matrix of attention scores per sample in the batch. And about this torch.bma method, you can definitely check the documentation. So basically the torch.bmm function performs a batch matrix product that simplifies the computation of the attention scores, where the query and key vectors have the shape of batch size, sequence length, hidden dim. And we already saw when we printed this inputs embeds.size that it gave this output torch.size 121 by 768, representing batch size, sequence length, and hidden dim. So if we ignored the batch dimension, we could calculate the dot product using between query and key values by simply transposing the key tensor to have a shape of opposite, that is hidden dim by sequence length, and then using the matrix product, that is torch.matmul, to collect all the dot products in a sequence length matrix. But we did not do that because here, since we want to do this for all sequences in the batch independently, hence we use torch.bmm instead of torch.matmul, because torch.bmm takes two batches of matrices and multiplies each matrix from the first batch with the corresponding matrix in the second batch. Now I'm going to import torch.nn.functional as f, and then widths will be equal to f dot softmax scores, that will be scores, and the dim will be equal to 1. I have to sum them up, sum across dim equal to -1. There's an extra s, okay. And then the final step is to multiply the attention weights by the values. So let's do that. Attention outputs. And I got to use the batch matrix multiplier again. Yeah, IGHTS and value. Why it's giving me, there will be a weights. Yep. And let's check their, okay. And as expected, I get the shape of 1 by 21 by 768. This is what our shape was here for the input embeds, 121, 768. And that's pretty much about calculating the attention scores. We have gone through all the steps to implement a simplified form of self-attention. Notice that the whole process is just two matrix multiplication and a softmax. So you can think of self-attention as just a fancy way to calculate the weighted average. Now, let's put these whole steps that we have individually performed in each cell into a single combined method, because that method we can then reuse across architecture. So I'm going, this is this combined function to calculate the attention. It will take query key value, and pretty much I'm going to reflect or repeat what I did back up here. That is, I created dimk, I created scores with torch.bmm. I'm going to do the same. So actually, I can just copy these two lines from here and put it inside my function. Yep. So my first torch.bmm is done. Now the weights will be just the softmax, WEI. Softmax of scores across the dim of -1. And now my weights are calculated. And now once the attention weights are computed, that is in this line, then we multiply the weights with the values by the use of torch.bmm. And that will be my final return. Weights and value. That's all. That's all 4 lines, and you get your scaled dot product attention. And here, just like previously, I used this torch.bmm 2 times. That's because these query, key, and value are batches of matrices, each with a shape of batch size, sequence length, number of features. And batch matrix multiplication is only performed over the last 2 dimensions. And now I need to allow the model to create a different set of vectors for the query, key, and value of a token by using 3 different linear projections to project our initial token vector into 3 different spaces. Because remember, initially when we did the manual calculation here, I created all query, key, and value to be equal, but that is not to be the case in practice. So the reason is because our attention mechanism with equal query and key vectors will assign a very large score to identical words in the context, and in particular to the current word itself. And the dot product of a query with itself is always 1. But in practice, the meaning of a word will be better informed by complementary words in the context than by individual words. For example, the meaning of flies is the word flies is better defined by incorporating information from its surrounding than by another mention of the word fly, because this fly is a homonym, and it has different meaning. With the same spelling of the word, it has different meaning, whether it means the insect category of flies, or it actually mentions flying as an airplane. So this context, the surrounding words, is very important, and that we have to capture through these scale dot product attention. So how can we promote these behavior? And that's where the multi-headed attention concept comes into the picture. So in our simple example till now, we only used the embedding as is to compute the attention scores and weights, but that's far from the whole story or the actual implementation in practice. So in practice, the self-attention layer applies 3 different independent linear transformation to each embedding to generate the query, key, and value vectors. These transformations project the embeddings, and each projection carries its own set of learnable parameters, which allows the self-attention layer to focus on different semantic aspects of the sequence. And each of these different independent linear projection is called attention heads. And because we have multiple of them, and that's why it's called multi-headed attention. The reason is that the softmax of one head tends to focus on mostly one aspect of similarity. Having several heads allows the model to focus on several aspects at once. For instance, one head focuses on subject-verb interaction, whereas another head finds nearby adjective. Obviously, we don't handcraft these relations into one model, and they are fully learned from the data. If you are familiar with the computer vision CNN, that is convolutional neural network technologies, then it will make more sense. So in CNN or convolutional neural networks, where one filter can be responsible for detecting faces, another filter can be responsible for detecting edges in the images, or maybe cars or cats or dogs in the images. So different filter is responsible to detect different segmentation or different aspects of the images. Here in the transformer architecture, each of these heads is responsible for finding different semantic meaning of the textual data. So now let's code the multi-headed attention. First, I'm going to define a class just to capture the three different linear transformation from QKV, query, key, and values. And then in the next step, I will apply these class to create my multi-head attention. Attention head will be an n dot module and div self dot embed dim and head dim super dot q equal to have to apply the nn dot linear transformation linear embed dim head dim self dot k will be similarly just to repeat this. Am I doing right? Yes, embed dim and head dim, and that's repeated 3 times here. Now the forward function, and instead scale dot product attention, to there I pass self dot q hidden state. Similarly, let's copy this self dot k hidden state self dot v hidden state. All right, and from the forward function I just return these attention outputs. So here we have initialized 3 independent linear layers that apply matrix multiplications to the embedding vectors to produce tensors of shape, batch size, sequence length, and head dim. Where head dim or head dimension is a number of dimensions we are projecting into. Although these head dim does not have to be smaller than the number of embedding dimensions of the tokens, that is embed dim, in practice it is chosen to be a multiple of embed dim so that the computation across each head is constant. So what I mean is, for example, BERT has 12 attention heads. So the dimension of each head will be equal to 768 by 12. That is 64. And how exactly did I get these 768 as the number for head dimension? That's because, remember, when we printed our attention outputs previously, we got 121 by 768. That's how. And then the same number we got as a shape for our inputs embeds. So 121 by 768, that was the size of our inputs embeds. All right, now that I have a single attention head, we can concatenate the outputs of each one to implement a multi-head attention layer. But to do that, I need a couple of parameters from the config. And remember, our config is at the very top. We got the config where it is. So let me quickly check. Config. Yeah. So this is my config, which is coming from autoconfig.p from Pretrained and model checkpoint. So our model checkpoint is BERT based uncased, and that's why I'm going to go to BERT official documentation in HuggingFace, and this is the config documentation. So all the BERT configs are here. And for the multi-head attention right now, in my next function, what I am going to need is this parameter from config, which is the dimensionality of the encoder layer and the pooler layer. And I also need this one. Where is that? Num of attention heads. Yeah, this one, num attention head. This is an integer which represents the number of attention heads for each attention layer in the transformer encoder. First, the constructor init method. Sorry. Self, and I need the config. And my embedding will be the config.hiddenSize. And the num head will be config dot what did he saw? That was num attention head. Num, this is heads here. And head dim. So now head dim, that will just be the embed dim divided by num heads. Embed dim divided by num. Yeah. Now calculate the number of multi-heads. Yeah, actually, so this is the number of multi-heads. And now I'm going to use the previous attention head, this method in here, because with that method I'm creating single attention heads, and that will just be multiplied within this class. So I need to use a module of PyTorch called nn.module_list. It is just like a Python list, only that because it's part of PyTorch NN module, it has its gradient tree associated with it. So self.heads module list, this one, and that will take my previous class, which is attention. What is the name? Attention head here. Attention head, and that will take embed. Sorry, that's embed dim, and embed dim. And now I need to do self.output linear will be equal to nn.linear. That will take embed dim and embed dim as well. And the next method within this class should be the forward method. Now, this is where the multi-head concept will be implemented, which is now I need to concatenate and then pass the concatenated output from the attention head so that it is fed through to the final linear layer. So concatenated output, that will be equal to torch.cat. And what I'm concatenating is, so what I'm looping through is for h in self.heads, that's where I'm looping through, and h will be here h dot, not dot, h and then hidden stat. Okay. Actually, this closing square bracket should be here. Here. Okay, so the list is made with the concatenation. I also need to specify the dimension to be the last dimension. All right, and now again I need to bring in the output linear, that is this variable. So output linear, and that will take my concatenated output here. Then just return it. Okay. Copy this entire thing and paste into my Colab. Quickly run to check I have not done any mistakes in the syntax. Yeah, looks all good. So here a quick word on this the use of these nn.module list. So this is just like I was saying, it is just Python list, but there's some differences. This module list was designed to store any desired number of nn.modules. And remember, this whole class, this is using nn.module. That is, it is inheriting from nn.module. And that's why I could use nn.module list. So NN.module's regular use case is when, for instance, if you want to design a neural network whose number of layers is passed as input. So the question is, why use module list instead of normal Python list? And the answer is, if you use normal plain Python list, the parameters won't be registered properly, and you cannot pass them to your optimizer using model.parameters, which will be required while building your neural network. All right, so now I just need to check that this multi-head attention layer produces the expected shape of our inputs. So what I'm going to do, is to pass the configuration we loaded earlier from the pre-trained BERT model when initializing the multi-head attention module, and this will ensure that we use the same settings as a BERT and will check the shape of the output. So let's invoke this multi-head attention, pass the config, and the output of this should be, just name it some variable, multi-head attn. Okay, and then the next what I'm going to do is multi-head attention. To that I will pass inputs embeds. Let's name the output to be just output. Okay, okay, and now let's check the size of my attention output. Size, copy this thing and collab, run this cell. Yeah, all right. I got this 121,768, which was my expected result, and this shape exactly matches with my embedding that we checked earlier. All right. Now I need to wrap up this section on attention. So let's use again BERT-Viz library to visualize the attention for two different uses of the word flies. And remember, flies word is a special kind of word which has two different meaning for the same spelling. And what I'm going to do is I'm going to use a particular method called head view of BERT-Viz, and I'll compute the attentions of a pre-trained checkpoint and will indicate where the sentence boundary lies. Let's code that. output attention. And now I'm going to pass two sentences which has a word flies in it. So let's just copy it. I kept it selected. So these are my two sentences on which I'm going to apply the tokenizer and then visualize with BERT. Sorry, that's attention. And here I'm going to bring in my model that we just defined over here. Model. To that I pass with the tokenized input. Sentence A star. That will be token type IDs. So that's one parameter that I'm going to explain in a second. Let's just finish this line of code now. Token type IDs equal to 0. Dimension across 1. Similarly, I need to, sorry, this will be a sentence B start. Here, a quick word on these outputs from the model, because you can see that I extracted these attentions attribute from the model output. Let's go to their documentation because it's important. So the pattern that I used in my code here is just this. That is, I take the model, and to that I pass inputs, and then these outputs is the output that I get after applying this model. Now these outputs object is a sequence classifier output, as we can see in the documentation of that class below. It means that it has an optional loss and logits as logits, an optional hidden states, and an optional attentions attribute. So this is how I got the attentions attribute. And here we have the loss, since we passed along the labels, but we don't have hidden state and attentions because, okay, so they are talking about this particular implementation because they passed one parameter to the model, which is labels, and that's why they have the loss, but they don't have attentions and hidden state. But in my case, in this implementation here, there is no labels, so I will have the attentions. And now what they're saying is you can access each attribute as you would usually do, and if that attribute has not been returned by the model, you will get none. Here, for instance, outputs.loss is the loss computed by the model, and outputs.attention is none in this case. But in my case, outputs.attentions will return me something. Okay, so that was about that. Yeah, now next I need to get the tokens. This is another method that I'm using. Convert IDs to tokens. The names gives you obviously what it does. And now finally I'm going to invoke the head view method. Tokens Um, what does it say? It takes token list of tokens, render head view, and attention I've given, and then yeah, then it takes a tokens list of tokens. Okay, then it will take sentence B star heads. All right, now let's take this and take it to my Colab. And when I ran this code here in the Colab, that is after doing the head view, this is the resultant visualization that I get. And so we can see this particular one between sentence A and sentence A. That is a relation between this pretty much represent the self-attention of various words here. And the visualization shows the attention weights as lines connecting the token whose embedding is getting updated, that is on the left side, with every word that is being attended to, that is on the right side. The intensity of the lines indicates the strength of the attention weights, with dark lines representing values close to 1 and faint lines representing values close to 0. And in this example, the input consists of two sentences and the CLS and ACP tokens. That is this first one and the separator, this one. These are special tokens in BERT's tokenizer. One thing we can see from this visualization is that the attention weights are strongest between words that belong to the same sentence, which suggests BERT can tell that it should attend to words in the same sentence. All right, now that we have covered attention, let's take a look at implementing the missing piece of the encoder layer, which is position-wise feed-forward networks. Now, the feed-forward sublayer in the encoder and decoder is just a simple two-layer fully connected neural network, but with a special property, which is instead of processing the whole sequence of embeddings as a single vector, it processes each embedding independently. For this reason, this layer is often referred to as a position-wise feed-forward layer. You may also see it referred to as a one-dimensional convolutional layer with a kernel size of 1, typically by people who are already conversed with the computer vision CNN techniques. So this is kind of where most of the capacity and memorization is hypothesized to happen, and it's a part that is most often scaled when scaling up the models. And we can implement it with a simple nn.module. So let's start the coding. All right, before writing the code for the position-wise feed-forward layer, just quickly sum up to understand its requirement in the overall scheme of things. So, each encoder in Transformer consists of two sublayers. The first one is the self-attention layer, which we have already discussed and implemented. And this layer is a layer that helps the encoder look at other words in the input sentence as it encodes a specific word. And then the next layer is called the feed-forward neural network, the one that I'm going to implement now. So this feed-forward neural network is kind of an exact same feed-forward network which is independently applied to each word in each position through its own path in the encoder. Hence, it is called position-wise feed-forward neural network. And this is a type of feed-forward layer that consists of two dense layers that applies to the last dimension, which means the same dense layers are used for each position item in the sequence, the so-called position-wise. And further on this, that similar to the multi-head attention, the position-wise feed-forward network will only change the last dimension size of the input. In addition, if two items in the input sequence are identical, the corresponding outputs will be identical as well. And now finally, I'm starting to code that feed-forward network. This also needs to come from an end.module. Module to Excel config. And now we need to have two identical dense fully connected layers. So I'm going to use nn.linear. First one is config.hiddenstat, hidden size. And the second one is config.intermediate size. Now the next layer will be linear 2, and I just need to change their sequence. Config.intermediate size and then config.hidden size. Then I'm going to use self.galu. Finally, self.dropout. Hidden dropout prob. I also need the forward function. Linear 1 x. Next one will be galu. Then it will be linear 2. Finally, dropout. All right. Now, a quick note that this nl.linear, the first parameter it takes is in features, and the second parameter is the out features. And in features mean it's the size of each input samples, and out features means size of each output samples. And also note that a feed-forward layer such as nn.linear is usually applied to a tensor of shape batch size input dim, where it acts on each element of the batch dimension independently. This is actually true for any dimension except the last one. So when we pass a tensor of shape batch size, sequence length, hidden dim, that is 3-dimension, the layer is applied to all token embeddings of the batch and sequence independently, which is exactly what you want. Now let's test these by passing the attention output to this feedforward class. So I'm just going to outputs feed forward. I'm going to use attention outputs outputs that we defined earlier. If outputs dot size, And when I ran this cell in Colab, this is the size I get, which is as per the expectation. So it's running all right. So we now have all the ingredients to create a fully fledged transformer encoder layer. The only decision left to make is where to place the skip connections and layer normalization. Let's take a look at how these affects the model architecture. So layer normalization normalizes the activations along the feature direction instead of mini batch direction, and this overcomes the cons of batch normalization by removing the dependency on batches and makes it easier to apply for recurrent neural network or in BERT and transformer, of course. So in essence, layer normalization normalizes each feature of the activations to zero mean and unit variance. And for this, I'm going to use nn.layerNorm. And talking about the skip connection, what the skip connection basically is that it passes a tensor to the next layer of the model without processing and add it to the processed tensor. Thereby, it's skipping some processing layers. That's why it's called skip connection. Anyway, so let's start coding my transformer encoder layer with the layer norm. Self and config. All right, and now super. That would be the first layer norm in m dot hidden size. Second one will be config dot hidden size as well. Now attention. I'm going to use multi-head attention. Lastly, self dot feed forward. That would be feed forward. Now the fourth function. So first I need to apply layer normalization and then copy input into query key and value. So hidden state, and that would be self dot layer norm 1 x. Then I need to do a skip connection. So my updated x will be x plus self dot attention hidden stat. Then apply feed forward layer with a skip connection. Feed forward, and to this I will pass self dot layer norm 2 x. All right. Now, just like previously, let's just check that everything is working by applying this new class. So encoder layer, transformer encoder layer. Inputs em bids Sorry, I need to bring the shape. Encoder layer. To that I pass inputs mbeds size. What's the problem here? Embeds, right? And when I ran this in Google Colab, I get 121.768 and 121.768, just as it was expected. So everything is working fine till now. And now finally, we have implemented the transformer encoder layer fully from scratch. However, there is a slight problem in the implementation that we have done till now. And the problem is that the positional information of the tokens is fully lost because since the multi-head attention layer that we have coded up till now is effectively just a fancy weighted sum, the information on token position has been lost. That means the layers right now, they are totally invariant to the position of the tokens, and that is the position of the tokens have no informational influence on the final result. So we need to solve this problem. And here comes the next key concept of a transformer architecture, which is positional embedding. So positional embedding are based on a simple yet very effective idea: augment the token embeddings with a position dependent pattern of values arranged in a vector. If the pattern is characteristic for each position, the attention heads and feedforward layer in each stack can learn to incorporate positional information into their transformation. There are several ways to achieve this, and one of the most popular approach is to use a learnable pattern, especially when the pre-training dataset is sufficiently large. This works exactly the same way as the token embedding, but using the position index instead of the token ID as input. With that approach, an efficient way of encoding the positions of token is learned during the pre-training. So now let's create the custom embedding class that combines a token embedding layer that projects the input IDs to a dense hidden state together with the positional embedding that does the same for position IDs. The resulting embedding thereby will simply be the sum of both these embedding, that is token ID embedding and the positional embedding. The first one will be vocab size. That was my token embeddings, and now I need the position embedding. And I have I need a config dot max position max position embedding. And in case you're wondering what max position embedding, currently I'm looking at the official documentation of HuggingFace for all the config params, and this is where it is defined. Max position embedding is the maximum sequence length that this model might ever be used to it. Typically set this to something large just in case. For example, 512.1024.2048. All right. Yeah, so let's get back. And the second parameter to nn.embedding will be config dot hidden size. Yeah. Self dot layer norm. Epsilon value, set it to something very low. So I'm going to set 1e minus 12. All right, that completes this part. I need to also do the forward function. Now note that now I have both, but the important part in this whole thing is that I have my token embeddings and I have my position embeddings. So now the positional information is no more lost. All right, the next one is forward. It will take self and input IDs. So first I need to create position IDs for input sequence. Input IDs dot size 1, and then position IDs will be I need to use storage.arange, range sequence length, and d type will be torch.long, and I also need to flatten it, so I'm going to use unsqueeze. And now create token and position embeddings equal to self dot token embeddings input IDs, and position embedding will be self dot POSI position embeddings position IDs. Cool. Now combine. So I have my token embeddings, position embeddings, and I need to now combine these two embeddings because, like we discussed, that the final resulting embedding is simply the sum of the token embedding and position embeddings. So this is the final embeddings. Embeddings will be token embeddings plus position embeddings, and also need to update these variable with my layer norm because I'm in the forward function. I need to continue to update these embeddings equal to self dot layer norm embeddings. And also I need to update with the dropout. Dropout. Cool. Return embeddings. Nice. Here I'm just invoking these embedding class that we just wrote. And the embedding layer is just Now I need to take the size. Oops, sorry, I missed the super part over here. Otherwise, I would get an error. Yeah. And when I ran it in Colab, this is the result that I got of the size. And as expected, just like our previous output, we got 121,768, which is the expected size of these inputs.input IDs of the embedding layer. And now finally, let's put all of these together now by building the full transformer encoder, combining the embeddings with the encoder layer. So I will have a new class, transformer self and config again. So here I'm going to invoke the previous embedding class. And self.layers will be again the implementation of module list, because I need to get a list from this line. And this one will be transformer encoder layer, and that will have config, and then I need to loop through a range of config.number of hidden layers. So for range will be config num. Am I getting any option here? No. So that would be HIDDEN. Yeah, that should work. Let's just carry on with the forward function and then we will see. And now I have to traverse all the layers. That is this output of this module list, which is where my layers are. So for layer in self dot layers, x will be equal to layer x, return x. Cool. And also we need to check that this is actually working, just like our previous practice over here. And before checking that, just note that we can see that we get a hidden state for each token in the batch. This output format makes the architecture very flexible, and we can easily adapt it for various applications, such as predicting missing tokens in masked language modeling, or predicting the start and end position of an answer in a question answering project. Some example. And now let's just check this class quickly. Transformer encode. just like the previous line. Just going to print the size. All right, now take these two to my Colab. And again, after running these two cells, I get as expected. This is the output. 121,768 is a tensor size. So that's working fine up till now. So now the next step will be to build the transformer. So pretty much actually the whole architecture is built up to here, because now I have the embedding and encoder module combined in my final transformer encode. So I'm actually done with the almost by like 99% of the work for the entire architecture. And the part that is still due, that's relatively a small part, and that you can say that's like that can be called as a head of the architecture. So what I'm meaning is here that transformer models are usually divided into a task independent body and a task specific head. And what we have built so far is a body part. So if we wish to build a text classifier on top of this body, we will just need to attach a classification head to this body architecture. And that's what I'm going to do now. So now we have a hidden state for each token, but we only need to make one prediction. There are several options to approach this. Traditionally, the first token in such models is used for the prediction, and we can attach a dropout and a linear layer to make a classification prediction. So the class that I'm going to write now, that will extend the existing encoder for sequence classification. Let's name it transformer for sequence classification. Self.encoder will be coming from transformer encoder. Transformer encoder. What did I name this? Did I name this encode or encoder? Let me check. Oh yeah, I named it just encode. And in the dropout, and for the dropout, I am going to need a hidden dropout prob. So if I go to their documentation, that's what it is. So I'm looking at the transformer BERT config official documentation, and hidden dropout prob is a float value, the dropout probability for all fully connected layers in the embeddings, encoder, and pooler. Yeah. Dropout prob. It is going to be a dense, fully connected layer, hence an end of linear. And now I need to properly take the dimensions, everything from first dimension, 0, and everything from the last dimension. So this is selecting the hidden state of the CLS token. Let me put it comment. Select. And then the corresponding execution here, that is dropout and then classifier. So self dot dropout x, also classifier x, return x. Cool. And before initializing this model, I need to define how many classes we would like to predict. So let's just give 3 classes. Config.num labels, and define it to be 3. Then I'm also going to define the encoder classifier. That is going to be my transformer for sequence classification. Config. And lastly, encoder classifier. Sorry. Inputs IDs, and I'm going to measure the size. So let's take this both of them to actually Google Colab. Oops, I need to reconnect it. Okay, no worries. And after rerunning Google Colab, I just pasted the same code here, and after running this cell, I got torch.size of 1 and 3, and this is exactly what I have been looking for. For each example in the batch, we get the unnormalized logits for each class in the output. And that's pretty much where the encoder architecture gets completely built out. And I did not build the decoder yet. So here the encoder gets completed, but now the decoder needs to be built separately. But that I will do in a separate video later. So just to give you the perspective of the overall picture, that is where encoder and decoder fits in the overall scheme of things in transformer model. Let's take a look at another notebook that I prepared. So this is the representation of the encoder architecture. The encoder in the transformer consists of multiple encoder blocks, what you see here. An input sentence goes through all these individual encoder block, and from the last encoder, the output I get, that's the features, and that becomes the input to the decoder. And the decoder also consists of multiple decoder blocks, and each decoder block receives the features from the encoder. So let's take a vertical look at encoder and decoder. So if we draw the encoder and decoder vertically, the whole picture becomes looks like this in this diagram. And even a more compact view is here. That is the input sentence goes to the encoder that creates or generates features, and that features is fed into the decoder, and from that decoder I get the final output, which is prediction. So the decoder side has a lot of shared components with the encoder side, and only the main difference between the decoder and the encoder is that the decoder takes in 2 inputs and applies multi-head attention twice, with one of them being masked. And also the final linear layer in the decoder has a size equal to the number of words in the target dictionary. So anyway, the implementation of the decoder part and the architecture explanation, etc., will require a separate video altogether. So for this architecture of the encoder, I pretty much have to end it here. All right, that pretty much wraps up this video. If you have liked this one, smash the like button and also do subscribe, because I'm going to do many interesting NLP projects over the coming days and weeks. So see you in the next one. Thank you very much for watching. Hey everyone, how's it going? So in this video, I'll be implementing some baseline application of BERT. Specifically, I'm going to cover question answering and next sentence prediction, and also masked language modeling. And it mostly will be about the code implementation and with the relevant explanation. Let's start. First, a quick word on the architecture of BERT. So BERT is bidirectional transformer pre-trained using a combination of masked language modeling and next sentence prediction. The core part of BERT is the stacked bidirectional encoders from the transformer model, but during pre-training, a masked language modeling and a next sentence prediction head are added onto BERT. So when I say head, I mean that a few extra layers are added onto BERT that can be used to generate a specific output. The raw output of BERT is the output from the stacked bidirectional encoders. And the first step in my case would be tokenization for BERT models. So I am already in my Google Colab. I need to import BERT tokenizer. And then I need to let's define a random text as this, and then I'm going to do the get my encoding actually. Tokenizer dot encode plus. I'm going to use plus, and I'll tell you in a second what this encode plus is doing. The first parameter would be text. That is this one. 2022 would be a great year for all of us. Then add spatial token. Set it to true. I'm also going to set my truncation true, padding equal to max length. Oh, no, actually. That also, I'm setting it to true. And return tensor, I'm going to use PyTorch, so PT. Let's run this cell. Okay, this cell actually ran successfully. Let's print out this encoding. All right, so that's the tensor that I got after printing these encoded output. That is, after this encoding actually represent the tokenized text, and this is my text. Now about these parameters, the first one, I'm setting padding equal to max length, which will mean that the padding argument actually controls the padding of the tokenized form. So it's padded by zeros. to make all the text to the length of the max length. So it will pad to the length specified by the max length argument, or in this case, I have not specified separately a max length argument to be a number. That is my max length. I could have defined another parameter here where I will pass an integer for the max length. Here I have not specified that. So in this case, the padding will work like this, that it will pad up to the maximum length accepted by the model, that is whatever model you are using in your case. Also, I am using encode plus here instead of encode, and the encode plus specifically returns a dictionary of values instead of just a list of values, because tokenizer.encode plus can return many different types of information like the attention mask and the token type IDs. Everything is returned in a dictionary format, and if you want to retrieve the specific parts of the encoding, you can do something like this. Let's do the next steps actually. So in this case, what I'm going to do is that I want to retrieve the specific part of the encoding. So encoding encoding and attention mask. You can actually print this variable. Yeah, so all these zeros are because I have used padding equal to max length. That is, it is taking the maximum length accepted by the model and padding it all with 0 after my initial tokenized form. And another quick thing to note about the tokenizer is that you can specify to retrieve specific tokens if desired. For example, if you are doing masked language modeling and you want to insert a mask at a location for your model to decode, then you can simply retrieve the mask token like this. So you do tokenizer.mask token. Let's run this cell and I get this output mask. All right, now I am going to talk about the masked language modeling a little bit and then write the code. So masked language modeling is a way to perform word prediction that was originally hidden intentionally in a sentence. In simple terms, it is the task of filling in the blanks. And masked language modeling can be considered similar to auto-encoding modeling, which works based on constructing outcomes from unarranged or corrupted input. Let's start the actual coding. Some of the standard imports at the very first step. And then, yeah, I am going to actually use the same line. That is, my tokenizer will be just this: BERT tokenizer dot from pretrained BERT base uncased. And my model will be this: BERT for masked LLM dot from pretrained BERT base uncased return dict equal to true. And we have already imported this model from here in this line from transformer. So the masked language modeling works by inserting a mask token at the desired position, just like I was telling, where you want to predict the best candidate word that would go in that position. And you can simply insert the mask token by concatenating it at the desired position. The BERT model for masked language modeling predicts the best word or best token in its vocabulary that would replace that word. The logits are the output of the BERT model before a softmax activation function, which is applied to the output of BERT. That is, logits are the prediction scores of the language modeling head. That is, scores for each vocabulary token before softmax. And in order to get the logits, we have to specify return dict equal to true, which is what I have done here. In the parameters where you are invoking this BERT for must lm, and so otherwise, if you do not do this, you will get a compilation error. And return dict, actually, by setting it to true, the model will return a model output class instead of a plain tuple. And you can check Hugging Face, the official documentation for knowing what model output is all about. So yeah, so now my next line of code will be text equal to, so what I'm going to do, this is masked language modeling. So I will have a mask token here. So my tokenizer dot mask token, and you have already seen that what is the output of this particular expression, tokenizer dot mask token. That's this. Okay, so this is the place where I want to do kind of fill in the blanks by this BERT for masked LM model. The Opera House in Australia is in, then there's a blank and city. And I also need now I'm pretty much invoking the tokenizer dot encode plus, sorry, that's text, and return tensors will be PT for PyTorch. All right. So now in order to get the tensor of softmax values of all the words in BERT's vocabulary for replacing the mask token, we need to specify the masked token index. And this we can get using torch.where. In this particular example, I'm retrieving the top 10 candidate replacement words for the mask tokens. So what I'm going to do, let's do that in the next cell. Torch.where input, to that I will get input IDs 0. That should be equal to tokenizer dot mask token ID. So that's the that's the condition here for torch.where. Now, to know about what I just did, mask token IDs and my previous line over here, where is that? Here, tokenizer.mask token. So let's go to the official documentation of Hugging Face BERT tokenizer. So here it's clearly written, the mask token, this is a special token representing a masked token used by masked language modeling pre-training objectives like BERT, will be associated to self.mask token and self.mask token ID. And now I'm just getting the output from the model. And then the logits from the output. Yeah, that should work. Let's run this. Cool. Okay, so after we pass the input encoding into the BERT model, we get the logits simply by specifying output.logits, which is what we did here. And and after this, we can finally apply a softmax activation function onto this logits. So my softmax will be F dot softmax. We have already imported F, right? Yeah, torch dot nn import functional as F, right? F dot softmax logits dim will be -1. And so with this line, by applying the softmax onto the output of the BERT, we get probabilistic distribution for each of the words in BERT's vocabulary. So words with a higher probability value will be a better candidate replacement words for the mask token, which is what the purpose of this line. And now, in order to get the tensor of softmax values of all the words in BERT's vocabulary, for replacing the mask token, we can specify the masked token index, which we already have from this line, that is torch.where. So what I'm going to do is mask word will be softmax. From there, I get mask index and slice for everything in this dimension. Yep. And after getting this mask word further, because in this particular example, I am retrieving the top 10 candidate replacement words for the mask token. So I'm going to use a particular method of PyTorch called torch.topk. So my top 10 will be torch.topk mask word and dim equal to 1. From there, 1 and 0. And finally, after this, the process becomes relatively simple, as now all we have to do is iterate through the tensor and replace the mask token in the sentence with the candidate token. That is the top 10 tokens which has a top 10 highest probabilities. So let's run this loop for token in top 10. Tokenizer.decode. Now I need to decode it. That's my word, and the new sentence will be tokenizer.mask token. That's what I'm going to replace with the word, and then print the new sentence. Cool. And after running this cell, I am getting the very much expected result. So the very top probability, they are saying the opera house in Australia is in Sydney city. Okay, Sydney, there should be a space between Sydney and city. So let's just change this here. Because after my tokenizer.mask token, I'm just adding a single space. And from here, run it again, run after. Cool. Now it looks better. Yeah. So the first one obviously pretty much gives me the answer, and that's the top probabilistic output from my model. And note that here I actually use a top 10 candidate to get my new sentence. But actually in the practically, I just wanted to get the top one, that is the one with the highest probability, which will be my Sydney city. And in that case, I don't have to use the storage.topk, because if I just wanted the top very top probabilistic one prediction, then I could have just used something like this. So this would be my softmax, then mask word, and instead of top k, I'll be using the storage.argmax. That will be my top word. But here I use top k to get my top 10 words. So anyway, this solution would have given me the very highest probability prediction from the model, which is Sydney City. All right. All right, that's what the first part of this video, that is the base use case of BERT, concludes. And now I'm going to check out the next base case application of BERT, which is next sentence prediction. Let's put some text over here. So the next sentence prediction is a task of predicting whether one sentence follows another sentence, and I'm going to use this BERT for next sentence prediction model. It returns logits, which is a prediction scores of the next sequence prediction. So first, as usual, let's bring in my relevant imports. Import BERT tokenizer, which I already have imported earlier, and then BERT for next sentence prediction. Cool. And I already have torch and functional as f imported, so I can directly start with tokenizer. So my BERT tokenizer in this case will be, again, BERT tokenizer dot from pretrained BERT base uncast model. This time will be this one. And again, from pretrained cool. And I'm going to use two sentences. One is prompt, another one is next sentence. And then I'm going to encode both of them. So let's actually run this cell and let's see if it's fine. Yeah, it ran fine. And now, okay, sorry, now this. So my two prompts are, actually one is prompt and another one is next sentence. So this is my two inputs. So the prompt is, I came back from office in the evening, and next sentence, I opened my beer after office. And we are going to check if this is a good next sentence for this initial prompt. First, encoding. Encode plus, and I'm going to give prompt, then next sentence, return tensors equal to pt. Oh, I have not. Have I defined a model? Yes, I have. Here is my model for next sentence prediction. Yeah, so I can directly apply the model here to get my outputs. Softmax will be f dot softmax. Just print this softmax. Okay. Cool. Run this cell. All right. So I got these two as my final output, that is the probabilities of the first sentence and the next sentence. So to sum up, these next sentence prediction is a task of predicting how good a sentence is as a next sentence for a given sentence. In this case, prompt variable is the given sentence, and we are trying to predict whether next sentence is indeed the next sentence. And to do this, the BERT tokenizer automatically insert a SCP or separator token in between the sentences, which represent the tokens actually represents the separation between the two sentences and the specific BERT. For next sentence prediction model, it predicts two values. That is the final output from these BERT for next sentence prediction will be two values of whether the sentence is the next sentence. And these two values are returned in a tensor. The first, and which is what we got, that is this is my tensor. And in this tensor, the first value represents whether the second sentence is a continuation of the first, and the second value represents whether the second sentence is a random sequence or not a good continuation of the first. So unlike masked language modeling, which you did previously, we don't retrieve any logits because we are not trying to compute a softmax on the vocabulary of BERT. We are rather simply trying to compute a softmax on the two values that BERT for next sentence prediction returns, so that we can see which value has the highest probability. And this will represent whether the second sentence is a good next sentence for the first. And here is that tensor for me, and because here we can see that the first value, that is this 9.998e minus 0.1, this is considerably higher than the second value. So that means BERT believes that the second sentence follows the first sentence. That means, like we said, this represents a probability whether the second sentence is a good continuation of the first sentence. And because this value is so much higher than the next probability, that is the next value, we can very confidently decide that here in this case, this next sentence, that is this I opened my beer after office, is a good continuation of the first sentence. All right, there ends this segment on next sentence prediction, and the next and the last base case use of BERT that I'm going to cover in this video is question answering. And for this, I'm going to use a specific BERT model called BERT for question answering. So let's just import them first from Transformer. Tokenizer and BERT for this one, question answering. And from Transformers. Okay, and then I need to define my tokenizer just like before. Question. And inside, I have to pass the pre-trained model name, which in this case is this DeepSeek BERT base cased squad. And my model will be, as you can expect, this dot from pre-trained, and again the same name here. Cool. And now I am just first going to use two simple sentences as example, and then I will use a larger sentence for this question answering. So the mechanism here goes like this, that you will have two set of text. The first set is called the context, and then you also need to pass another text, which is a question. So the model will answer the question based on the context text. So my example text, that is the context text, will be, let's say, this GPT came in 2020, and example question is when did GPT-3 come? And now we can use our tokenizer, that is this one, to automatically generate two sentences. by that is two encoded tokenized sentences by passing these two text into the tokenizer. So what I'm going to do is tokenized inputs will be tokenizer. To that, I will pass first. I'm going to pass example question, and then the next one will be example text, and return tensors for this case is PT because I'm using PyTorch. Now let's print these tokenized inputs to see what exactly they print. No, I see I have made a small mistake here. The tokenizer that I defined here, this line is wrong. This tokenizer is not an instance of a BERT for question answering, but it will be just the original BERT tokenizer. So this is the correct one. Yeah, a BERT tokenizer dot from pretrained, then you pass the name of the model. Yeah, now it should work. Let's run this and see. Cool. So this is the output. That is a printed form of these tokenized inputs that I got here. And let's understand what I have here, and then we'll go through one by one each of them. So I have an input IDs here, which is this tensor up to here. And then the next key is token type IDs. And that is a tensor up to this. And the last key in this object, in this dict, I got is attention mask, which is this tensor. So that's the output of from my BERT for question answering, and definitely I recommend you go through their official documentation right here in the HuggingFace official website. That's for BERT question answering, and there all these parameters are detailed. So the input ID is what you got in the output. That's the indices of input sequences tokens in the vocabulary. So this is my input ID. So basically, these are this tensor, that is the input ID tensor. This is a tokenized text. That is my context. And then the next thing is this next key in this dict, that is token type IDs. Another important thing to understand, but to understand these token type IDs, first note that some models in BERT or in HuggingFace in general, or NLP in generally, some models' purpose is to do classification on pairs of sentences or question answering. So these kind of models require two different sequences to be joined in a single input ID entry, which usually is performed with the help of special tokens such as a classifier, that is CLS, and the separator. For example, if for this BERT model that builds two sentences and into a single form like this. So like this. So I have a CLS, then sequence A, then a separator, then another sequence B, and then another separator. So that's how two sentences become one for this kind of model, which require two input sequences. And in this case, the two input sequences were this example text, that is a context text, and the example question. And we used our tokenizer, that is this one, BERT tokenizer, to automatically generate this kind of sentence by passing the two sentences to tokenizer as two arguments. That is this line. Tokenizer, and then I pass the first sequence and then the next sequence. All right. So here, those two types of sequences are question and context. And when I get within the attention mask, I got this tensor 1, 1, 1, all these ones. Actually, sorry, I'm not talking about attention mask right now. Yeah, I'm talking about this token type ID. So I got in this tensor all these zeros and the ones. So these token type IDs is also called segment ID in BERT, and they are represented as a binary mask identifying the two types of sequences in the model. And in this case, these two types of sequences are represented as zeros and ones. All the Here the token type of 0 is for question part, and 1 is for the context part. All right, so that was my BERT for question answering on a single example text. But now I'm going to actually run this on a larger text and then raise a question, which should the answer of which is included within my context text, and then BERT will give me the answer. So let's do that. First, I need my question. So the text that I'm going to use for this case is this particular text. So the Vatican Apostolic Library, more commonly called the Vatican Library or simply the VAT, is the library of the Holy See, and so on and on. So what I'm going to do is this whole text I'm going to pass as context, and then my question will be to BERT, when was the VAT formally opened? And we can see that already looking at this, that the answer of that question is right here, formerly established in 1475. So let's just do it. So first I'm defining these two variable, text and question. And so this text is this entire, the one that we just saw. It is not getting wrapped in Google Colab. But anyway, and my question is, when was the VAT formally opened? And now I'm going to declare my tokenizer and model just like before. And then let's do a context management here. Torch dot outputs equal to model tokenized inputs. Let me see, tokenized inputs. Oh, sorry, I have to define the tokenized inputs again, because that was for a different text previous, for that is a previous example. So let's define my tokenized inputs again. That will be tokenizer. And this tokenizer, we can reuse it again because that was defined already here, and that's just the instance of this BERT tokenizer object. And from pretrained, deep set, BERT base cased squad 2. That's the name of the model. Yeah, so tokenizer here will be, to the tokenizer I need to pass the question. And my question here in this case is, when was the VAT formally opened? And then the second is text. And also I need to mention return tensors equal to patim. Cool, that should work. Model tokenized inputs. Okay. And now, okay, now another important concept is called start logits and end logits. Again, you can check the documentation. Basically, start logits is that defines a span where it starts a score before softmax. That is, the answer starts at that span, and end logits is where the answer ends at that span. So it basically gives me the indices where the answer kind of resides. And that's very much the job of the model. That is, I get the start logits and end logits from the output. And basically, the model will tell you at what start and end position of the input IDs the answer to the question will be located. That's kind of the simplest explanation of that. Okay, so you will see my answer start logits will be start index will be, I have to get it from the outputs dot start logits, and I have to apply argmax on that to get the max values. And similarly, my answer end index would be outputs end logits dot argmax. Cool. And now finally the predict the answer tokens. So predict tokens will be tokenized inputs dot input IDs. How did I get this input IDs? Because you already saw when I printed these tokenized inputs, I got a dict which has three parameter or three keys. The first one is input IDs, then I have token type IDs, and then lastly I also have attention mask. So I'm just here extracting the value of, grabbing the value of input IDs. And from there, I need to get 0 answer start index, then up to, sorry, that's a slice notation, answer and index plus 1. And finally, to actually see the result, that is to see the answer, I have to decode these predict answer tokens, because this is a tokenized form. I have to decode it to see the actual answer. So tokenizer.decode predict answer tokens. Cool, that should work. I just ran the cell, and that's it. That's my answer, 1475. What exactly we saw in the text, that is, this was my original text, and in the second line it clearly said formally established in 1475, and that's exactly the answer that BERT gave me from my question. So again, this question was, when was the VAT formally opened? And the simple answer to that is 1475. And we got this by decoding the predict answer tokens from this model, that is BERT question answering. And once more again, that all these are very well described in HuggingFace original documentation, official documentation. So this is their documentation. You just go to BERT for question answering, and there you can see all these parameters, what are input IDs, attention mask, token type IDs, etc. So if you go to token type IDs, I think this is the explanation here. It's given that exactly this is the thing that we just discussed. All right. Yeah, you should definitely go through their beautifully written documentation. And as a final point on these BERT question answering, also remember here I applied the model directly, but of course, just like any other Hugging Face model, you can do many fine tuning. Also, you can customize the these BERT question answering model to some extent to apply before applying it to your dataset to get better results. All right, that pretty much wraps up this video. If you have liked this one, smash the like button. And also do subscribe, because I'm going to do many interesting NLP projects over the coming days and weeks. So see you in the next one. Thank you very much for watching. Hey everyone, in this video we will do sentence similarity using cosine distance and using HuggingFace transformer library. And for that, first few words on how tokenization and embedding works in Transformer, which is very, very important to understand before we proceed to get our similarity vector on which we can apply the cosine similarity metric. So in this image, we can see a simplified architecture of Transformer. And this is at the very beginning, where a single sentence is passed to the whole architecture. And as a first step, the words or the text goes through the tokenization and which produces tokens. And then each of the single token produces a single vector which has a size of 768. Here the 768 number are the number of columns. Those 768 values contain our numerical representation of a single token, which we can use as contextual word embedding. Specifically note that for each of the token we have a vector of size 768. So for the totality, that is for the total sentence, we are actually looking at a tensor of size 768 by the number of tokens. So what is the input to BERT? Input to BERT is an embedding representation derived by summing token embedding, segmentation embedding, and the position embedding of the text. And here in this image, we can see this green is a token embedding. The yellow part is my segment embedding, and here the bottom one is my position embedding. So what are they? What are token embedding, segment embedding, and position embedding? So token embeddings are the representation for the word tokens of the text derived by tokenizing using word piece token vocabulary. For BERT base, the hidden size is 768. Thus, the token embedding created has a size of sequence length multiplied by 768. That is sequence length into 768. And probably you already know that the maximum sequence length for BERT is 512. So the size of my token embedding will be 512 by 768. And note that the token embedding also includes these spatial tokens called CLS and ACP. CLS stands for the classifier, and ACP stands for separator token. That is, it separates two sentences. Now, coming to position embedding, the position embedding is a representation for the position of each token in the sentence. For BERT base, it is a two-dimensional array of size sequence length by 768, where each nth row is a vector representation for the nth position. And finally, the segment embedding. The segment embedding identifies the different unique sentences in the text. And note that each of these embedding, that is token embedding, position embedding, and segment embedding, will be summed to derive the final input representation of the initial sentence, and that input representation has a shape of sequence length by hidden size. Here, for the case of BERT, the max sequence length is 512 and the hidden size is 768. So we have the input representation size, that is a shape of the tensor of the input representation, as 512 by 768. And the sequence length value can be changed and is decided based on the length of the sentences in the downstream task dataset. The sentences which have length less than the sequence length need to be padded, and the hidden size is decided by the choice of the BERT model. That is, you have BERT tiny, you have BERT small, you have BERT base, and then BERT large. So for BERT base, the hidden size is 768. And also a quick word on the limit of 512 tokens for BERT base. So normally for longer sequences, you just truncate the sentence to 512 tokens. And the reason for applying this 512 limit is that this limit is kind of derived from the positional embeddings in the transformer architecture, for which a maximum length needs to be imposed. And the magnitude of such a size is related to the amount of memory needed to handle text. Remember, attention layer scale quadratically with the sequence length, which poses a problem with long text. And that's one of the fundamental reasons why BERT has this 512 as a max token length limitation. And as to the plan of this video, I will have these random sentences, 6 of them, and what I'm going to do in this video is to check the sentence similarity between them. That is, I will just take the first sentence and check the similarity with the rest 5 of them. So at the end of the notebook, I'm going to print the similarity vector of cosine similarity metric. So first, just the regular imports. Okay, here for this purpose, that is to create my sentence vector of all these sentences, I'm going to use a transformer model from HuggingFace, and that's called these all MPNet base v2. So how did I choose it? One of the so initially I just searched by the sentence similarity tag, and then I sorted all the results by the number of downloads, and I saw this is one of the model that has been downloaded really high number of times, 1.2 million almost. And so this is a pretty popular model, and also the size of these is very manageable. Also, when you go to files and version, I can see the PyTorch model.bin file is only 438 MB. This is relatively small size compared to 1 GB plus models, so I can handle it pretty relatively faster. And also, after doing some other research, Google search generally, I found that people have found this model have normally produced good sentence embedding. That is the result, and the prediction from the model is reasonably good. So let's see what they are saying about the model. This is a sentence transformer model. It maps sentences and paragraphs to a 768-dimensional dense vector space and can be used for tasks like clustering or semantic search. Yeah, so this is the same 768 dimension that we are talking about. And initially, if you to use the model, you need to install the sentence transformer. So if you have not installed it already, just go ahead and run this pip install u. And also in the model card, they are saying the standard stuff, which is this is how you import. And then the important part is this line, that is to load the tokenizer and the model. You have to run this line. So I can just copy it from here and go back to my VS Code. Yeah. Yeah, now this is going to download the model. I'm running in my local machine, so this model was not already downloaded locally. So that's what it is doing right now. And then I need to tokenize the sentences. So here the downloading is over. Now I need to run a loop for my 6 sentences, but first initialize a dictionary that will contain the tokenized sentences. Input ideas will be a list. I'm just creating 2 keys that will hold the corresponding list. And the 2 keys for the tokens are, as we know, probably that it's input IDs and attention mask. That is all. Sorry. Yep. Now I need to run a loop over my sentence list. Sentences. Tokenize the sentence and append to a dictionary list. So let's new token tokenizer dot this model takes a max token length of 512. Truncation equal to true, just in case if you have larger than 512 tokens. padding equal to max length. And because I'm using PyTorch, I am going to return the tensors as PT. No, sorry, I'm still in the loop. So that's my new token. And then tokens, update the input ID field. Similarly, the attention mask field as well, I need to be updated. And now let's do, okay, before that, let's do one thing. Okay, before to explain that how I use this input IDs and attention mask, let's apply the tokenizer and tokenize one single random sentence. So here it's an example sentence. It's a sunny morning, and what I'm going to do, I'm going to just tokenize this sentence and see the result. So I just copied it, and instead of sentence here, I am going to replace it with example sentence. And then I'm going to print these new tokens. And let's see what kind of result I get. All right, so this is my tokenized form of a single random example sentence. And as you can see, this is a dict, and it's a very large tensor indeed. And I can see I have got one key here called input IDs, and which is a tensor. And I have got, okay, that is all. Okay, let's just, because it is not showing the entire thing, because of this output exceeds size limit, open the full output data in a text editor. So just click here, and here now I can see the full dict. So I have the first key as input IDs. And if I go down, I have another key, attention mask, that is also a tensor, and that has all these values. Okay, looks like that is all. So the point is that we have the new tokens. This tokenized form is a, that's what it is returning, and that has got two keys, input IDs and attention mask. If I want, I can actually print the keys like this, and we can see it's a input IDs and attention mask. These two keys we have, and that's the reason here I defined these tokens variable to be a dict, which has input IDs, which is a list, attention mask, which is another list. Actually, this list will be a tensor, and that's how I'm here updating. After I tokenize each sentence in this line, I am updating this input ID and attention mask list with these two lines. Okay, now let's proceed. Now I just want to restructure the list of tensor into a single tensor. Similarly for the attention mask. Attentions mask here. Okay. Yeah. Okay. Now let's proceed. Let's just check the shape of the input ID. Yeah, it's a two-dimensional tensor, 6 by 512. So the as we can see, this 512 is a number of tokens, and because we have selected padding equal to max length, and um so that means that even if my input sentences are not up to 512, it will for the extra part of the tokens, it will pad it. And yeah, so this is the vector size or shape of my tokenized input IDs. Now, a quick word on this method encode plus. So the encode plus and the encode function tokenize your text and prepare them in a proper input format of the BERT model. The main difference is stemming from the additional information that encode plus do provide you. So the encode on that is not the encode plus, only the single encode converts a string in a sequence of IDs using the tokenizer and vocabulary, while encode plus returns a dictionary containing the encoded sequence or sequence pair and additional information, the mask for sequence classification, and the overflowing element if a max length is specified. So the difference lies in the additionally encoded information, specifically the input mask. And so I needed here those additional information, and that's the reason I have used encode plus instead of just encode. Okay, now that I have the tokens, I can actually invoke my model. And as you remember, the model has already been defined at the top, so it will take my tokens. Let's define the output to be, okay, run this cell. I think this may take a minute. Oh, yeah, it ran relatively quickly. So this is my outputs. And this is a large tensor, three-dimensional tensor, we can see, and it says base model output with pooling, last hidden state tensor. So let's open this in a text editor again. Let's see. So this is the entire output, and I can see that I have one key called last hidden state, which is a tensor of 3 dimension. And if I go down, I have another key here, a pooler output, which is also a tensor, and that's a 2 dimensional tensor. Hidden states equal to none, attentions equal to none. Okay. You can actually also, just as usual, check the keys of the output. And I have two keys here, last hidden state and pooler output. Okay, now let's get the last hidden state. So outputs, let's call it embedding. Embeddings, DDINGs, okay. Yeah, so embedding is that 3 dimensional tensor we saw earlier, which is the last hidden state. So on the last hidden state, just a quick word that it contains a hidden representation for each token in each sequence of the batch. So the size of last hidden state is that's a 3 dimensional array, and that represent batch size by sequence length by hidden size. And on the other hand, these our second key, that is a pooler output, This contains representation of each sequence in the batch and is of size batch size by hidden size. You can see that it is a two-dimensional tensor, whereas the last hidden state was a three-dimensional tensor. So what this puller output basically does is it takes the hidden representation of the CLS token of each sequence in the batch, which is a vector of size hidden size, and then run that through the BERT puller nn.module. This consists of a linear layer followed by a tanh activation function. The weights of these linear layer are already pre-trained on the next sentence prediction task, because well, here I'm dealing with BERT, and as we know, BERT is pre-trained on two tasks, which is masked language modeling and next sentence prediction. So coming back to this last hidden state again, because this is very important and we will be working with this last hidden state. So this output is the sequence of hidden states at the output of the last layer of the model. And as we just saw that the last hidden states can be obtained from the output of the BERT model. And this is a pretty large tensor of size 512 by 768, that is sequence length by hidden state. This 512 sequence length, which is a sequence length, it's because BERT has the limit of 512 tokens. Normally for longer sequences, you just truncate to 512 tokens, and the 768 is the values that are the numerical representation of a single token, which we can use as contextual word embeddings. So each single token that is after the original word goes through the tokenization process produces a single vector which has a size of 768, and it's called the hidden states. Now I can check that my last hidden state, that is this three-dimensional, this tensor, is indeed of size 512 by 768. Let's see that. Embeddings.shed. And we can see that the 6 represent the batch size. So this three-dimensional tensor is of size, this is the batch size, then that's a max sequence length, and this is my hidden state. All right, now moving ahead, the next thing we have to do is called pooling layer. Now, to calculate the sentence similarity, we have to calculate a particular metric called mean pooling layer. And so the fundamental question is, what is the basic concept behind the pooling layer? So using pooling, we can generate from a variable sized sentence a fixed sized sentence embedding. That's kind of the very basic motivation of doing pooling. And we can also consider the last hidden state that we just saw as the average across the sequence length dimensions to get average or mean embedding. So about the mean pooling, BERT produces contextualized word embeddings for all input tokens in our text, but as we want a fixed size output representation, we need a pooling layer. Different pooling options are available. The most basic one is called mean pooling. We simply average all contextualized word embedding that BERT is giving us, and that's your mean pooling basically. This gives us a fixed 768 dimensional output vector, and which is independent of how long your input text was. And so for us in this case, we transform our last hidden state tensor, which is this three-dimensional tensor, into our desired vector, and we use mean pooling method for this. So each of these 512 tokens has separate 768 values. This pooling work will take the average of all token embeddings and consolidate them into a unique 768 vector space, producing a sentence vector. And that's pretty much why after we have produced our dense vector called embeddings, this variable here, we need to perform a mean pooling operation on them to create a single vector encoding. And to do this mean pooling operation, we will need to multiply each value in our embedding tensor by its respective attention mask value so that we can mask or ignore non-real tokens. The reason is that you should only take into account those tokens which are not padding tokens if you want to average them. So let's start doing that. So obviously, to multiply our last hidden state, that is this embedding vector with the attention mask, first we need to calculate the attention mask. And how do I get that? Just from tokens, we already saw that it has a key called attention mask. And that's it. Let's name it attention mask. And we can check its shape. Yep, that makes sense. 6 by 512. So this is batch size by max sequence length. Okay, so remember, before multiplying the embedding tensor with attention mask, I need to make sure that the size of both are same. That is the attention mask and embedding. And to do that, I need to expand the attention mask to the same size as embedding. And to start with that, first note that our attention mask is a two-dimensional tensor, but embedding is a three-dimensional tensor. So first what we have to do is apply unsqueeze on attention mask. That will give me an extra dimension. Let's do that. Attention mask dot skew on squeeze -1, and then expand it to be of the same shape or size as embedding. So expanded, you can definitely check the documentation of expand method. Embeddings dot size. That will be our new unsqueezed attention mask. So let's name it unsqueezed. UEEZED. Okay, and another quick thing I have to do is converting all to float. Actually, let's just name this unsqueezed thing to something different. Yeah, resized attention mask. And let's check their shape as well. Cool. So I get 6, 5, 1, 2, 7, 6, 8, which is exactly the shape of embeddings.shape. All right, now I can multiply it with the embeddings. And if you want to see how they look like, that is, what is this resized attention mask, just print this. Yeah, so it's a tensor, three-dimensional tensor, and the values are all between 1 and zeros. Okay. The next step is to okay, let's just quickly check one single element if it's coming out properly. 0. Yeah, so that's what I was talking about. Each of these tokens are out of 768 different values. It's a vector of 768 values. So basically, each vector here above represents a single token attention mask. Each token now has a vector of size 768 representing its attention mask status. And now I'm ready to multiply embeddings with attention mask to apply the attention mask on the embedding. So embeddings resized attention mask. Let's name it masked embedding. And the purpose of doing this again is that I only want to take the real tensor elements while calculating my Cosine Similarity matrix. because all the padding element, all the uh, padding values which are like non-real, they were just padded to make it equivalent to the max length dimension. Those should be masked, and that should not contribute to the calculation of sentence similarity matrix. Yeah, and cool. So this is my masked embeddings. Of course, after masking also, the shape should remain the same, which is batch size by max sequence length by hidden state. And now let's do another thing, which is just print this mask embedding to see if that makes sense. Yeah, it's a three-dimensional tensor, and all these are masked. So note one thing, now I'm getting so many zeros, but before, I think when I printed above somewhere, yeah, here, look, all of them have values because there it was not masked. So the entire three-dimensional tensor had actual real values. But now all the non-important element, that is all the padded ones, they are masked. That means their values are all zeros. And now for the mean pooling, I need to take the mean of all of the embeddings and turn them into a single vector of size 7, 6, 8. So to do that, I need to sum the embeddings across the dimension 1, that is across the sequence length dimension of 5, 1, 2. So let's do that. Summed, masked, torch.sum, masked embeddings across a dimension of 1. And also check this summed mask embeddings shape. Awesome. 6 by 768, and that's how I wanted. So here again, that because we summed across the dimension of 1, so that dimension will vanish and the other two dimension will remain in the output. And here again, I have to repeat it, the most important thing, that we had these 512 input tokens, which was a max sequence length, and each token is a vector of 768 values, and that's exactly what we are seeing here. The first element is called batch size here. Okay, now I need to, okay, let's quickly check how they look. Yeah, so that's my summed values. And now the next thing to calculate this mean pooling is to calculate our count of the mask tensor where it is 1, because this is our summed masked embedding, and we are targeting to calculate the mean pooling. That means we have to divide by the count of the masked tensor where it is 1. So I'm going to use a method called torch.clamp. You may be familiar with it. So torch.clamp is used to clamp all the elements in an input into a range between min and max. It takes 3 parameters, that is the input tensor, mean, and the max values. The values less than the mean are replaced by the mean, and the values greater than max are replaced by the max. Let's start, and then it will be become more clear. And also, I'm also going to use the normal Python summation method. Yeah, anyway, let's just go torch.clamp. And what I'm clamping is resized attention mask dot sum of 1. So I'm summing all the elements where it is 1. I'm sorry, this one here actually represent the dimension or the axis in this case. Remember, this sum here is not our torch.sum because we used torch.sum here, but this sum here is the regular Python basic sum operation over a matrix. So this one inside will make sure that it sums across the axis equal to 1, that is across the columns. And we already know that resized attention mask has only zeros and ones. That is all. If we just print this, we can see it here. All the values inside these are 1 or 0, only binary values. So what I'm doing across the column, when I'm adding across the column, what will happen is only those positions of the matrix will get added to the sum where there is an actual value. And what is that value? That is 1. So all the zeros will not get added up because they are just 0. So effectively what it's doing is that it will give me the count of cells where the cells should not be masked. All right, this line is not complete yet because that's where it's giving me the count, the total number of ones which is getting summed up. And because I'm using torch.clamp, I have to pass a mean parameter here, which is if any values are is less than the mean, it will be replaced with the mean value. And I'm going to give a very, very low value, which is 1e minus 9. Okay, and let's call the output of this as count of 1 in mask tensor. And if you want to check the shape, yeah, the shape remains as it is, 6 by 7, 68. All right. And if you just want to check the whole tensor as it is, just print it. And this is a tensor. It's a 6 by 7, 68 dimension tensor, and all these values are just the count of 1 inside the original resized attention mask. Okay, so this variable actually represents our count. So what we got to do to calculate the mean pooling is divide this summed masked embedding by this count of 1 in mask tensor, and that will give us the mean. So mean pooled is mean pooled, that is our summed mask embeddings divided by count of 1 in mask tensor. Let me quickly check again that they are of the same shape. Dot shape. Okay, that's 6 by 768, and also this one I think we already just checked, but I'm just checking anyway. Yeah, so they are of the same size, so this calculation will just work fine. Let's run it. Yep, and let's now see our mean pool. Yeah, so that is this tensor. Let's check their shape. 6 by 768 as expected. Okay, now we are almost done. Only the last thing remaining is the calculating the cosine similarity for sentence. So see this mean pooled, this variable now represent our similarity vector. It's a dense similarity vector, and all we have to do now is to apply the cosine similarity method, and to the cosine similarity method just pass two vectors one by one, and that will give the similarity between two sentences. Because now this mean pool tensor represents our original this corpus, these sentences corpus, and that the mean pool actually represent it as a similarity vector form. All we got to do is apply the proper method, which is cosine similarity, to get the actual similarity metric. So let's do that. So calculate similarity for sentence 0 with the other sentences. And the first thing I got to do is to import from sklearn.metrics.pairwise cosine similarity. And also now I got to convert from PyTorch tensor to a regular NumPy tensor for my mean pooled one. So my modified mean pooled will be equal to original mean pooled dot detach. That is, I'm detaching all the gradients tree dot NumPy. And now just calculate cosine similarity is equal to will be, so I'm passing it, I need to pass it two list or two arguments indeed. So the first argument is the sentence, but that is the base sentence on which I want to calculate the similarity with other sentences. So this is the base sentence, and the other sentences, so with relation to this sentence I will calculate the cosine similarity of the other sentences. So the first argument would be mean, sorry, what I'm doing, mean pooled 0. That's my first argument. And the second argument is all the rest of the sentences. So I can just use the slice notation, starting from the second element till the end. Okay. Just run this cell, and that's it. That's your final result. So we can see that for the first sentence, the similarity matrix for the second is 0.12, which is pretty low. Similarity of the third sentence is also low. Similarity of the fourth sentence is really, really low and in the opposite direction. Then the next sentence is also low, but this one is relatively large. So let's see why, if it makes sense. So if we go back to our original sentence, we can see the first sentence. This is our base sentence, and I was calculating the similarity metric with respect to this on all other sentences, and we could see that only with this last sentence there is a high similarity. And if you read that, it's obvious that the first sentence, it had been 16 days since the zombie first attacked. And this sentence reads, after the last zombie attack 16 days back, they are taking control of the city. All right, obviously these two sentences are relatively highly related. And that's what we saw in our similarity matrix calculation as well. This is 0.683. Okay, so that was a very basic implementation of cosine distance based similarity calculation using transformer. Alright, that pretty much wraps up this video. If you have liked this one, smash the like button. And also do subscribe, because I'm going to do many interesting NLP projects over the coming days and weeks. So, see you in the next one. Thank you very much for watching. Hey everyone, in this exercise I will look at the various decoding strategies while generating text with GPT-2. So what is decoding strategy? In language-based generation task, we typically build a model which outputs a set of probabilities to an array where each value in that array represents the probability of a specific word or specific token to be generated. And the job of the decoding strategy is to select the token from that array of probabilities. Now, an obvious answer is you can think of that when you have a set of probabilities in an array, you just choose the token with the highest probability. But it is not always as simple as that, because in that case, if you just choose always the token with the highest probability, you may face many problems. For example, your generated text will be very, very repetitive and boring. So there are quite a few strategy implemented in this space to generate the text with the correct amount of probability or with the correct strategy, and that's what we'll look into in this video. And a good decoding strategy that transforms the model's output probabilities into discrete tokens can improve the text quality significantly. Hence, finding the best decoding strategy requires some experimentation and a subjective evaluation of the generated text as well. And these are the main decoding strategies that we are going to discuss in this video, which are greedy search, beam search, and random sampling. So within the random sampling family, we have top P and also top K. Yeah, so this will include both top K and as well as top P, right? And all of these three functionalities can be used for autoregressive language generation models. In short, autoregressive language generation is based on the assumption that the probability distribution of a word sequence can be decomposed into the product of conditional next word distribution. And this is the mathematical representation of these. If you search for these autoregressive models, you will get many blogs explaining it pretty well, so I'm not spending more time. Just know that the very well-known GPT-2 and GPT-3 falls under these architecture. All right, with that, let's start with the actual code. Obviously, if you do not have Transformer installed already, you need to run this command, pip install transformer, to install your transformer in your machine. I already have this, so I don't need to run that. And importing my torch and auto tokenizer and auto model for casual LM, the regular imports. Device will be hidden. And the model that I'm going to use for this video is GPT-2 medium. This is obviously from HuggingFace. And there's another model, GPT-2 XL, but that's a relatively larger model, and it takes a much longer time to work with that model, and that's why I chose GPT-2 medium. But for your more serious case, you definitely should use GPT-2 XL, because that's, although that's larger, that's definitely a better model. All right, the first one is greedy search decoding strategy. So here, the simplest, this is the simplest decoding method, and which is to get the discrete tokens from a model's continuous output by greedily selecting the token with the highest probability at each time step. And this is a mathematical representation where P represent the probability and YT here, this T here represent the timestamp. So greedy search decoding is relatively rarely used for text generation task that requires diversity. It can be useful for producing short sequence like arithmetic, where a deterministic and factually correct output is very important. But then where you need diversity or a little bit of creativeness in the generated text, then greedy search decoding is definitely not your choice. All right, in below right now, I am going to implement greedy search kind of from scratch. And what I'm going to do that at each time step, we pick out the model's logits for the last token in the prompt and wrap them with a softmax to get a probability distribution. And after that, we will pick the next token with the highest probability and add it to the output sequence and run this process again and again. I'm just importing pandas here and also defining time steps and choices per step. And here I'm going to define a method for implementing the greedy search. And the reason that I'm doing it from scratch is to understand the working of the greedy search from fundamentally, that is what's happening under the hood. But in our GPT's model.generate method, we already have a parameter where we can directly mention whether I want greedy search or beam search or some kind of random sampling. So you do not really have to do it from scratch while you are actually working and implementing on a real data set. But here the motivation or the target is to understand everything from scratch. So let's proceed. Get next token greedy. It will take input text and also input IDs. Okay, so here I am going to run the decoding for 8 time steps. So first I'm going to declare a context manager with torch.noGrad because I do not need the grad here. These iterations dict that will contain the whole input tokens and also the predicted tokens in a dict format, and ultimately at the end of this function I'm going to convert this to a pandas data frame so we can print and present it in properly in a tabular form. So that's the purpose of these iterations. So iterations, now I'm going to include a key called input because that will hold the continuously updated input token. And then I'm also going to add, so input is like one column in the final data frame that I will have. And also I'm going to have choice 1, choice 2, choice 3, 4 and choice 5 as different columns, because here we are doing choices per step equal to 5. So I will have 5 columns for 5 choices with decreasing probabilities of the predicted token. So yeah, once we complete this function, it will make sense. Input will be my I'm just decoding from the tokenizer, and this tokenizer we have already defined it over here. And then if you print this, let's print it. Actually no need to print because I'm just going to take output.logits, but first I'm going to define my output. And then then I'm going to get output.logits like this. From that, I need to select the logits of the first batch and the last token. So that I'm going to do by selecting the first batch for the first dimension, the last token, and the last dimension also will be everything. Yeah, so that will be held in a variable called next logits. Okay, so this next token logits it is just a one-dimensional array. Remember these output.logits, this is a three-dimensional array. But next token logits is a one-dimensional array. So if we print these next token logits, so you will get a tensor something like this. So let's move on. Now apply, this is just the logit, so I need to apply softmax to get the actual probabilities. Okay, now I need to apply sorting. So I need to get the indexes of the sorted array from these probabilities array. So let's do torch.argsort to that class next. Descending and hold these in a variable called sorted indices of net token probability. Okay. And again, these sorted indices of next token probat, this variable is just a one-dimensional tensor, something like this. It just holds all the indices in this variable. Okay, next I need to run a loop because I have 5 choices per step. Here is 5, so I need to run a loop over these 5 choices, so to produce just 5 predicted tokens for each of the prediction. And that's token index sorted, and then I need the actual token probability. And actual token probability I can obtain from next token probability variable. All right. And now create a string with decoded text and corresponding probability. So this string will be the actual element value in my final data frame. So let's quickly see what I wanted to achieve through this function. I think I should have shown it earlier. That would make sense at what I'm doing with this function. And this is the output that I'm trying to achieve with this function. So ultimately at the end of this function, when I run it on an input text, it will produce this data frame where each of these choices are the next token predicted choices. And we can see that these values in the cells They represent the actual token that has been predicted and also the corresponding probability. So at the very first one, choice 1, that is, will be with the highest probability, then choice 2 will be the next best probability, choice 3 is the next best probability, and so on. And this is the input. So for example, the first input is Bitcoin will be, then the next token predicted is the. So that means because this is the highest probability, and under the greedy search we take the highest probability token predicted as the as my choice. So my next input will be Bitcoin will be, then I append this previous predicted the. And similarly my input will go on increasing because I'm adding with the previous input the highest probability prediction. And so in this line I'm going to define a string which will have the actual predicted token and also the corresponding probability as a percentage. And that's going to be a tuple. So this will be decode. Yes. So to the decode I have to pass the token index sorted, because that's a decoded predicted token. And next one will be the percentage of the probability. .2f. Now update the iteration. Plus IBX plus 1. With that I'm out of the loop. So now I need to append the predicted next token to input. Iteration. Finally return from the whole function pandas data frame. Now time to execute this function, but before that I need to define my input text, which in this case I am just choosing this particular phrase Bitcoin will be. And so input ID will be the tokenized form of this input text. So I need to make use of the tokenizer. input text. Module torch has no attribute arg. Oh yeah, this is arg sort. Where did I use that? Here. And just noted that I forgot another thing to add. Because in the final data frame that is in here, which is output, I need to update these input. That is, the input will continually be updated with the previous best prediction. That means what I need to do is create concatenated input IDs. That's what I have to do. And why concatenated? Because it will be concatenated with the previous highest probability token. And I get the previous one by from these arrays sorted indices of next token proba. This one, sorted indices of next token proba. From there I take non-zero and also none across deal of -1. Okay, now all looks good. Just run this cell. Yes, so that's my data frame, and this is what I wanted to show, the greedy search algorithm from scratch. So we can see that the absolute final sentence will be Bitcoin will be the first cryptocurrency to be, and check our initial input was Bitcoin will be. Then I have all the choices, and the highest probability choice is this choice 1, so I add the, so the next input becomes Bitcoin will be the. Similarly, my second output or the second prediction takes the previous input plus the highest probability output or highest probability token prediction, which is first, so I add first. And then my next highest probability is cryptocurrency, so I add cryptocurrency and I get this. Similarly, I go on down and I just take the choice 1 and append it with the previous input, and finally I get this sentence. So that was implementing this greedy search from scratch with this function. And now I'm going to check if I do the same greedy search implementation by taking the help of the inbuilt functionality of HuggingFace. So my input IDs will remain the same, which is tokenizer, input text, return tensor equal to pt, I take the input IDs, and now the important part, output here will be model.generate. This is the method which will give me the predictions, the generated predictions. So to that, the first argument is input IDs. Max new tokens, that will be my time steps. And what are my time steps? We already defined, that's 8. And another one I want to pass is do sample false. You can definitely check their official documentation to make sense of all these parameters. And I'm going to print tokenizer dot decode. what I'm doing, decode output. From output I take the first element. Okay, and when I ran this is my final output. Bitcoin will be the first cryptocurrency to be listed on the. Now look at my from scratch implementation result and the inbuilt Hugging Face implementation result. They are almost the same. Of course, my from scratch we ended it here, and up to this word or this token, each one pretty much matched. So Bitcoin will be, this was my absolute original input, and then this token matched the first cryptocurrency to be, and I also have the first cryptocurrency to be in my own implementation. Okay, so that was for showing the greedy search algorithm, how it works. And now I'm going to move on to beam search. Actually, before moving to beam search, I just want to define few more things, because we have to use it quite a few times in this exercise, which is I just want to define lengthier input text and generate the prediction from that input text. And then we are going to use the same input text through beam search, and then for top K sampling, top P sampling, and so on. So my input text, let me take it from a website. So this is an input text I took, and it reads, in a previous era of data engineering, data team structure was very much centralized, with data engineers and tech savvy analysts serving as librarians of the data for the entire company. Data governance was a siloed role, and data engineers became the de facto gatekeepers of data trust, whether or not they liked it. Okay, this is my input text, and based on this, I'm going to generate my generated text from GPT-2. And just like previously, we do the basic generation with our tokenizer. And for that, I'm going to define max length equal to 128, and otherwise I can just copy from here, because it is going to remain the same. So I'm tokenizing the input text, return tensor pt, taking the input IDs and moving it to the device, and then I'm outputting, that is a generated text, will be model.generate input IDs max new tokens equal to time step. Okay, in this case, not, I'm going to delete only this parameter because I have something else. Max length will be max, because I'm defining a max length of 128 here. And do sample remains false. Let's run this cell. Okay, now it's generating, and it is a lengthier text, so it is taking a little bit more time. Okay, so yeah, so this is my generated text, and if you read it, it says the generated part is here. But as the data industry has grown, so has the need for data governance. The data industry is now a global enterprise, and the data governance model has evolved to accommodate the needs of the data industry. Data governance is a complex topic, and it is not. Okay, so this is my generated part, and this was generated based on the greedy search. And now I'm going to do beam search. So the major drawback of the greedy search was that it misses high probability words hidden behind a low probability word. And thankfully, we have this beam search to alleviate this problem. So with beam search, at each time step, it generates all possible tokens in the vocabulary list. Then it will choose the top B candidates that have the most probability. Those B candidates will move to the next time step, and the process repeats. So instead of decoding the token with the highest probability at each step, beam search keeps track of the top B most probable next tokens, where B is referred to as the number of beams or partial hypothesis. The next set of beams are chosen by considering all possible next token extensions of the existing set and selecting the B most likely extension. In summary, whereas greedy decoding and random sampling calculates the best option based on the very next word or next token only, beam search checks for multiple word or multiple tokens into the future and assesses the quality of all of these tokens combined. However, because we are now back to ranking sequences and selecting the most probable sequence again, beam search can cause our text generation to again degrade into repetitive sequences. So with beam search as well, we can get repetitive generated text. But there's more solution on that as well. We'll look into that in a second. And now for the implementation, looking into the under the hood working of beam search. Note that transformer models return the unnormalized logits for the next token given the input tokens. So we first need to normalize the logits to create a probability distribution over the whole vocabulary for each token in the sequence. And we then need to select only the token probabilities that are present in the sequence. So let's write some function to do this. So this function that I'm writing will get me the log probabilities from logits for a single token. So I'm being explicit with my method name nomenclature here. Get log probs logits only token. Log probability will be equal to, I'm going to use f.log softmax. So this is not softmax, this is just, this is pretty much softmax, but this is, instead of being a regular softmax, I'm going to use log softmax because that's what is needed under the beam search techniques. And here I need to use torch.gather log p. Next argument is 2 label double EZA 2 LABELS and return me the log p label. Okay. So the above gives us the log probability for a single token. So to get the total log probability of a sequence, we just need to sum the log probabilities for each token. And also a quick word on these log softmax function. So the log softmax is simply a logarithm of a softmax function. The use of log probabilities means representing probabilities on a logarithmic scale instead of the standard 0-1 interval. And the use of log probabilities improve numerical stability when the probabilities are very, very small because of the way in which it's computed. So taking the product of a high number of probabilities is often faster if they are represented in log form. And that's pretty much the reason of using log softmax. And about this torch.gather, this function creates a new tensor from the input tensor by taking the values from each row along the input dimension. And in here, our input dimension is 2, that is dim equal to 2. And now I need to write the next function for the sequence log probabilities. And here, if I these output, I need to take the output.logits for the next steps. And if we print these output.logits here, that is, if I do something like output.logits.shape, then the result that I will get is it's a tensor of size 1 by 128 by 50257. So the first dimension here is a batch size. The next dimension is a sequence length, or the which we have defined here to be 128. Remember, max length 128. And the last one is the embedding vector size. So that's the total number of tokens in GPT-2 model that we are using here. Okay, so this was just for showing log probs is going to be equal to that method. The first one is the logits. So output logits. I need to take everything from the first dimension, then from the second dimension, everything but the last element, and for the third dimension, everything again. And the second argument of this method, get log probability from logits for single token, is the labels. So just pass labels. Okay. Note that in this formulation, we ignored the log probabilities of the input sequence because they are not generated by the model. We can also see that it is important to align the logits and the labels. Since the model predicts the next token, we do not get a logit for the first label, and we don't need the last logit because we do not have a ground truth token for the last logits. And that's why this adjustment over here. Now I just need to sum over the tensor. Sequence log proba. All right. Now let's use this function to first calculate the sequence log probability of the greedy decoder on our previous input text. So we already have this input text defined, and we also defined the output by using model.generate. Actually, this output is representing the greedy search algorithm. So let's just define it, output greedy. Okay, and this one as well. Okay, let it run that cell. By the time, let me write few codes here. Sequence log probability. So I'm going to use this method, and it takes a model which we already have defined, and the labels will be my output greedy, and input len, which is len of input IDs 0. What I'm going to do, print tokenizer the decode output greedy also print new line character log p dot to f. Yeah, let's run this. Sequence log okay, let me correct it. Because I did not run these two cells. And now after running this, I get this output and look at the log probability of 90.66, which is not too good. But now let's compare this to a sequence that is generated with beam search, because then we can actually make sense of the differences. So let's proceed. So previously I already had this output greedy, and now I need to do the same for output beam. And both output greedy and output beam are like a two-dimensional tensor. If you just print this output greedy, you get a single two-dimensional tensor. And I take the 0th element because I'm just 0th element because I'm just practically flattening it, because it's just you can see two square brackets here. Anyway, so my output beam also need to be of the same form. Let's start the coding for that. Output beam, and look at what I need to do to generate my output beam. Just pass one particular parameter into model.generate. So first argument remains input IDs, max length remain. So this is max length. Yeah, so this is the important parameter in model.generate. So only change you have to make is just pass this numBeams argument to produce your beam search output. That is all. And if you don't pass this, then by default it will produce the greedy search result. And finally do sample, which remains false. Log p will be equal sequence log prob and 0, and the last two I can just copy from here. It's taking a couple of seconds to run. Okay, so it ran pretty quickly, and now I get log probability of minus 27.22, and we can already see that we get a better log probability. That is this number, the higher it is better with our beam search than we did simply with greedy search. So with greedy search we got much lower, that is 90.66, and now with beam search I got much better, minus 27.22. But looking at the generated text here, we can see there are some repetitions. So this above result of minus 27.22 as a log probability, although it is not too bad, we have managed to stop the repetition to some extent, but we have not completely got rid of the repetition. So one way to address this repetition issue is to impose an n-gram penalty with the no repeat n-gram size parameter that tracks which n-gram have been seen and sets the next token probability to 0 if it would produce a previously seen n-grams. And for that, again, all we need to do is just change particular parameter. So I'm just going to copy this entire thing first, paste it here, and I need to pass here no repeat n-gram size. I'm passing it to be 2. Okay, and now let's run this again. Alright, and now I get a log probability of 60 minus 69.73, which is not as good as minus 27.22, but still much better than minus 90.66. So the above result, actually this result actually is not too bad. We have managed to stop the repetition, and we can see that that despite producing a lower score, the text remains coherent. Beam search with n-gram penalty is a good way to find a trade-off between focusing on high probability tokens with beam search while reducing repetitions with n-gram penalty. And it's commonly used in applications such as summarization or machine translation, where factual correctness is important. When factual correctness is less important, then the diversity of generated when factual correctness is less important than the diversity of generated output or generated text. For instance, in open domain chit chat or story generation, another alternative to reduce repetition while improving diversity is to use random sampling, and that's what we are going to look at next. And now random sampling with temperature. So sampling based family of techniques aims at increasing the diversity of the output and avoiding repetitions by introducing stochastic decisions during the generation process. Here the underlying basic principle is that we can utilize the probability of each token from the softmax function to generate the next token. The simplest sampling method is to randomly sample from the probability distribution of the model's outputs over the full vocabulary at each time stamp. And here is a mathematical expression, and this is actually the formula for random sampling with temperature. The temperature is denoted by this letter T, and the temperature is used to increase the probability of probable tokens while reducing the one that is not. And by tuning this temperature variable T, we can control the shape of the probability distribution. When T is less than 1, the distribution becomes peaked around the origin and the rare tokens are suppressed. On the other hand, when T is greater than 1, the distribution flattens out and each token becomes equally likely. And now I'm going to see the effect of this temperature variable on the token probability. So I'm going to define a couple of functions and then plot the basic plots, where I'm going to show different plots for different values of the temperature variable, starting from 0.5 to 1 and then 2. So first import this is a customized softmax actually, where I have a T variable representing the temperature. Logits divided by T, and what I'm going to return is divided by sum. That's all. Now define some random logits. sorted logits, np.sort logits, and from that I reversed that one. So for reversing, I'm going to use slice and -1. Okay, and my x variable just will be np dot. And now the plotting. And I'm going to plot a loop over three variables, three values of the variable t, which is 0.5, 1.0, sorted logic scheme. Labels will be, label, it's a string which will have t equal to the actual value of the t. Dot y label is just the probabilities. Yes, so that's my plot, and we can see there are three values of t, and that's how the sorted token probabilities will evolve over the values. And now to see how we use temperature to influence the generated text, let's sample with t equal to 2 by setting the temperature parameter in the generate model.generate method. So I go back to my the original method of model.generate. Input IDS. Max length equal to max. Output temp, yeah. And looking at these output, we can see that the output is clearly doesn't it's all producing some garbage words, and that's because we used a high temperature over here. And the high temperature, what it's doing is that it is accentuating the rare tokens, and thereby we have caused the model to create strange grammar and quite a few made up words. And now let's see what happens if we cool down this temperature. And so I ran the very much same two lines again, only changing temperature equal to 0.5, and this is the output that I get, and this is my generated text. And we can obviously see that this text is significantly more sensible output. And the main lesson we can draw from temperature is that it allows us to control the quality of the samples, but there's always a trade-off between coherence, that is low temperature, and diversity, that is high temperature, that one has to tune to the use case at hand. And another way to adjust the trade-off between coherence and diversity is to truncate the distribution of the vocabulary. This allows us to adjust the diversity freely with the temperature, but in a more limited range that excludes words that would be too strange in the context, that is low probability words. And there are two main ways to do this, which are top K and top P sampling. Let's do them. So top K and the top P sampling are two popular alternatives or extension to use temperature. In both cases, the basic idea is to restrict the number of possible tokens we can sample from at each time step. The idea behind top K sampling is to avoid the low probability choices by only sampling from the top K tokens with the highest probability. This puts a fixed cut on the long tail of the distribution and ensures that we only sample from likely choices. So in top K sampling, the K most likely next words are filtered and then the probability mass is redistributed among only those top K words. So let's take a look at this image over here representing the top K probability techniques, architecture, and how the probability mass is redistributed. So having K equal to 6, in both sampling steps, we limit our sampling pool to 6 words, while the 6 most likely words defined by this image here encompass only 2/3 of the whole probability mass in the first step. It includes almost all of the probability mass in the second step. And that's exactly what we mean that in top K architecture, the probability mass is redistributed among only the top K probability words. Now let's just implement it with model.generate, and again I only need to change a single parameter in my model.generate to implement it, and that's this top K parameter. So here in this code, I'm just using a top K equal to 50, and let's run this. And this is the output. We can see that the repetition is much lower in this case because these kind of algorithms specifically deal with not to have repetitions. And now the next and equivalent almost close concept to top K is top P or nucleus sampling. So here what happens is that so this is a pictorial representation of top P probabilities. Now we are no more looking at top K but top P. So instead of sampling only from the most likely K words, the top P sampling chooses from the smallest possible set of words whose cumulative probability exceeds the probability P. The probability mass is then redistributed among this set of words. This way, the size of the set of words, also known as the number of words in the set, can dynamically increase and decrease according to the next word's probability distribution. And so that's the fundamental concept here. So again, to understand how top P works, let's say we set the value, that is a P value, to be 95%. We then order all tokens in descending order by probability and add one token after another from the top of the list until the sum of the probabilities of the selected token is 95%. Thereby, we are choosing the top words whose cumulative probability is 95%, and we focus all our attention only on those words, and that's how top P works. And to implement it, probably you have already assumed, we only need to change one parameter, which is here top P, and there you specify the probability that you want, and here I'm specifying 0.90. That means it will choose only those words whose cumulative probability is 0.90, and only those words will be concerned. So just run this cell, and here's the output that I get from my top P decoding strategy. Alright, so those pretty much were the discussion points in this video, and if you are thinking which decoding method is the best, well, unfortunately, just like many machine learning algorithms, there is no universally best decoding method. Which approach is best will depend on the nature of the task you are generating text for. If you want your model to perform a precise task like arithmetic or providing an answer to a specific question, then you should lower the temperature or use deterministic methods like greedy search in combination with beam search to guarantee getting the most likely answer or most accurate answer. But if you want your model to generate longer text and even be a bit creative, then you should switch to sampling methods and increase the temperature, or use a mix of top K and top P sampling. Alright, that pretty much wraps up this video. If you have liked this one, smash the like button. And also do subscribe, because I'm going to do many interesting NLP projects over the coming days and weeks. So, see you in the next one. Thank you very much for watching. Good evening, everyone. In this video, I will do topic modeling with BERT-based sentence transformer model. And also at the end, for labeling the topics, I will implement a particular technique called automatic cluster labeling, which was proposed in a paper in 2021, where I will concatenate the most common verb, direct objects, and top two nouns from each text cluster for labeling the topics under the techniques as proposed by this paper. It will be a long coding session, so be patient, and of course I will put the link of the source code in the description of the video. And for the data set for this project, I'm going to use this one. It's pretty popular and pretty large real world data set called Steam Review Dataset, and the dataset contains over 6.4 million publicly available reviews in English from Steam Reviews portion of Steam Store run by Valve. Each review is described by review text, the ID of game it belongs to, review sentiment, positive or negative, and a number of users who thought review was helpful. This is essentially an extension to previously released Steam Review dataset. The resource is provided. All right, so this is the source of the dataset. I will put the link of this in the description as well, so you can download it in your local machine or your cloud machine. All right, with that, let's get started. So I have already downloaded this dataset in my local machine. And that's why I'm referring to the CSV file. It's a single CSV file of 2 GB, 2 gigabyte, quite large file. And this is here. I'm reading the dataset with pandas, and look at the particular way I'm reading it here with a lambda function with skip rows, because it's a large dataset, and for the purpose of running this notebook relatively quicker, I'm only reading by randomly selecting 0.4% of the rows. So my p-value here is 0.004, and then with the lambda function, all I'm doing is that if I greater than 0 and rn.random greater than these p-values, only those rows I'm reading into pandas. And let's run it. Even 0.4% of the dataset, taking a little bit of time. Yeah, so this is I'm just printing the dataset df-reviews.head here, and you can see that I have the app ID, app name, and review text, review score, review votes. So for the purpose of this exercise, where I'm going to do topic modeling on the actual reviews, the two most important columns that I will be working with for almost all the notebook is these two: review text and review score. So review text has all the entire review, and review score is just two numbers, so there's 1 and -1. Let's do a quick count plot to check the count of the dataset. Yeah, so I have -1 and 1, and note that here we are referring to only 0.4% of the dataset. So this distribution may not be representative of the whole dataset, but I just wanted to quickly check here. Okay, now convert some basic pre-processing. Let's quickly do. So first I'm converting the review text to string. Similarly, review votes. And also, let's strip all the extra spaces, df. Review text. And I'm also going to drop the reviews with null score. So let's define a new data frame name. Actually, it will be score. And finally, I want to change the scores from 1 and -1. Sorry, from 1 and -1 to 1 and 0, just to be consistent with the regular machine learning projects numerical values, because here -1 actually represents 0. So I have this binary representation of the review score. All right. Yeah, okay, some basic pre-processing was done. And now I am going to do a word cloud. The word cloud, I personally don't get much information from the word cloud generally, but just to quickly see, uh, I normally sometimes do word cloud, but it doesn't have too much of informational power indeed. Review for reviews. I can actually do reviews too. We already imported this word cloud module at the very top, so now I can just pass the configuration. Oops, sorry. Background color. Maybe do 700. bilinear. A max font size. Oh yeah, I missed the comma. Okay, it is building the word cloud, and that's my word cloud. And obviously, as you can expect, game, early access, review, these are kind of big words. Okay, now let's move on to do some more data pre-processing. Let's remove a few of the column in review text as early access review comments. Let's remove them because these are reviews with no comments written by a human or human reviewer. So I'm going to just remove those columns. Not equal to review. And also I'm going to review in from the review text column all the nan not a number values. So I'm going to make use of the tilde operator here. This tilde operator works as a not operator in this scenario. So df is en now let's check the shape of, and also drop duplicates if there is any. So what happened? Didn't I run the previous cells? I think I did not run the previous cells. Let's just restart and run everything previous. Okay, I got the result here. Next, just quickly check the head of this data frame. All right, now that's how the data frame is looking like right now. And I found that all of the F words and similar words such as shit, etc. are replaced by multiple these emoticon, love emoticon in the original text, and this is a source of confusion to the model that we are going to use to get the text embeddings. This symbol, that is this heart symbol, is a symbol of love, while they appear in the negative comments, and therefore it will impact our classifier. So I'm going to replace them with 4 asterisks, which seems token close to the F words. So let's do that. Define a util function, and for my next few pre-processing, I'm going to define quite a few util function and apply them one by one on the data frame. So So this will do a substitution, return the string obtained by replacing the leftmost non-overlapping occurrences of the pattern in a string by the replacement. REPL can be either a string or a callable. If a string / escapes in it are processed, if it is callable, it's passed the match object and must return a replacement string to be used. Okay, so the first argument needs to be the one that is going to be replaced. So I'm just going to kind of copy it from here. Can I do that? Yep. Okay, that's my first argument. And I'm going to replace it with okay. Okay, so that's my first util function. And next function I have is for to remove all the emojis. So for removing all the emojis, I have a util function. I'm just copying it from my source. Yeah. So this is just using this regex pattern to substitute those emojis. And that's pretty much it. So the first is for emoticon, the second is for symbols and pictographs, third is for transport and map symbols, and the last is for flags in iOS. Okay, now I need to do some more cleaning of some basic characters. Again, I'm going to use this re.sub with regex pattern, and this will, as probably it's very clear that for example this regex it will remove the greater than sign. The first one will remove the hyperlinks and markup and so on. And now I need to remove numeric characters. So let's define digit characters. So \d plus with an empty space, with actually nothing. Text. And the next one is a function to remove, function to unify white spaces. So unify white spaces and Alright, and then I need another function to remove symbols. Okay. Next one, another util function to remove punctuation. dot join. Within the not in, I have to pass all the punctuations. So I have I want to include question mark, period sign, comma, then slice notation, all of them. Okay, cool. And now I need to remove stop words. And for that, I am going to use nltk.corpus stop words, all these standard modules. Stop words dot words. So I already downloaded Porter Stemmer. Yeah. And also I need to define lemma. Word lematizer. And now to remove the stop words, another util function. Word. Cool. And next is function to use stemming to normalize words. So I need to get nltk.corpus and then snowball stemmer. So now I have to get each of the words from this word tokens variable and stem it. So I'm going to use this. Okay, And now finally I'm ready to apply all the cleaning util or pre-processing util methods on my data frames, a particular column. So another util function which will take the data frame and a column name, and quickly check what was the status of our data frame. Okay, so it has got review text, and this is the column that I want to clean. But for the clean column, I will create a new column names. I'm going to create a new column named cleaned review text. Okay. So I'm just first I don't want to touch the original df, so let's create a copy. And here is where I'm creating a new column from the original data frames, and the original data frames column name was review text. And now this is where I'm going to apply all my pre-processing util methods. Actually, let's name it pre-processed. Oh, okay, df processed is just fine. Next method will be replace hearts with pad. Actually, here I wanted to do this. Okay. Remove punctuation. Unify white spaces. Here, they were all. And the new column name that I am going to give to the clean column is review text clean. All right. So now I'm just printing the head after doing all these cleaning. Yep. So now we can see we have these new column review text clean, and we can see all these oh, something is wrong. These hearts were not replaced with 4 stars. Let me fix what happened. And I figured that this remove symbol, this method over here, remove symbol, that's actually replacing those asterisk symbols. star signs. So for now, I'm just commenting out these remove symbols. Just let me just delete this line. Yeah, I do not want that remove symbol method, so I can keep these asterisks instead of the heart symbols, because this kind of is meaningful to the model. Okay, let me remove this and remove that. Okay. All right, so now that's a situation on the structure of our data frame. And from now onwards, we can kind of forget about this review text, because this is the original review text that was there. We will work only with this review text clean, this column, because that's a pre-processed text. Okay, now let's select around 2000 negative samples randomly using if you want to use more data, definitely you should use it, but I just wanted to run this notebook while recording, and that's why I'm choosing 2000. But definitely for real world cases, if you can, select the whole data set. So DF processed. So I'm selecting those review text clean as a list, and now I'm going to print this negative reviews dot web. Yeah, makes sense. And I'm also going to check out the head. Yeah, all looks fine. So this is my all intents. So the all intents is coming from this line here. It's a huge list because it has all the text from my review text clean, that is this column. Okay, so this one I just wanted to check, but I can just clear the cell output here for now. Okay, now I am going to split the comments or reviews into sentences, and because some of the Steam reviews are very lengthy, it is not surprising to see multiple topics in one reviews, and that's why some of them are really lengthy. If we pass the whole lengthy comments through a sentence encoder, we will not see a nice and clean clustering outcome, and hence I am going to ignore these noises and less important sentences by splitting the reviews into many sentences. So what I do is, and what I'm going to do here is to remove the noises, is to include only the sentences with more than 4 words. You can do with 5 or 6 words as well to play around to see what gives you the best result. So I'm going with 4. I'm tokenizing these individual intent. All sense dot Sorry. I'm updating the all intent to be equal to all sense. That is len. Okay. Next, now I'm ready to pre-processing is almost done. It's actually done. So now I will bring in sentence transformer and do my sentence embedding. Okay, so here there are quite a few models that you can use with sentence transformer, and the one that I'm going to use is called all MPNet base v2, and you can check their HuggingFace page to know more about the model. And actually, that all MPNet base v2 is a sentence transformer model which maps the sentence and paragraphs to a 768-dimensional dense vector space, and normally are mostly used for tasks like clustering and semantic search. So that's what I am going to use. Small util function here for embedding. And also, I think I already mentioned in the first part of the video that I referred to a very popular blog, which the description of which I will give in the code in this notebook. And in that blog as well, they used I think all MPNet base v2. So I got guidance from that blog as well, but for this model choice. In that case, embeddings will be in yes. Oops, sorry. This is double equal. Sentence. So the name of the model is all MPNet base v2. And remember that in sentence transformer, right now I'm not using the GPU, and I'm not going to use a GPU, and in that case I have to mention the device as equal to CPU. Otherwise, by default, that is, if I do not mention the device argument here in this line, then by default it will try to use the GPU. So I am going to mention device equal to embeddings st1 will be st1. So I can just copy this thing from here. All intents. All right, now running this cell will take 3-4 minutes, but let's just start the running. And after the model inferencing was over, I get this embedding underscore st1 as the output from the model, the embedded vector. And here I print the shape, and we can see it has 2000 rows, 768 columns, that is 768 features, you can say. It's a vector. And so now, and this is expected because, as we discussed, this all MPNet base v2 model, as was clearly mentioned in HuggingFace official model card documentation, that it produces a 768 dimensional vector. And hence, now the next question is how do we reduce this dimension? Because here the purpose of this exercise is to do topic modeling. And if it was for some other purpose, for example text generation or question answer generation, etc., those are different motivation where dimensionality reduction may not always be very important. But here in this case, dimensionality reduction is important indeed. So for cases like topic modeling, it is recommended to reduce the dimension of sentence embeddings into smaller dimensions before performing clustering. For more details, you can check some of the papers in this space. And the method that I'm going to use is HDB-scan. It's a super popular dimensionality reduction method. Which has benefits to the topic modeling. It has some features like the probability score that help us to automate the optimum number of clusters, which is a big trouble in an unsupervised topic modeling. Now, before going into more details on the HDB scan, a few more quick words on the dimensionality reduction case here. So a manifestation of the curse of dimensionality is that distance measures such as Euclidean and Manhattan needed for clustering become meaningless at very high dimension. Here in this case, our dimension is more than 500, 768. So at this high dimension, those distance metric becomes kind of meaningless. Now, while some of the sentence transformer pre-trained models were created in a way to preserve the usefulness of some distance measures, dimensionality reduction before clustering will still greatly improve your result. To prove this to myself, I briefly explored using different clustering algorithms and embeddings without dimensionality reduction first, and I got kind of worse results. So, and here I'm going to first implement UMAP, or Uniform Manifold Approximation and Projection for Dimension Reduction, which was introduced in 2020 and has quickly grown in popularity as a very popular dimensionality reduction technique. UMAP is much faster and more scalable than t-SNE, while also preserving the global structures of the data much better. This makes it useful for both visualization and as a pre-processing dimensionality reduction step to use before your clustering. So let's start using that. And now I'm just going to import all the libraries for dimensionality reduction and also for clustering. And they are these. So UMAP here is for the, as we just discussed, it's for dimensionality reduction. HDB scan for clustering, and I'm also importing this hyperopt. We are going to discuss about this hyperopt in a moment, but just know for now that this is a super popular package to handle Bayesian optimization for searching the optimal hyperparameters. Alright, now few words on HDB scan, our clustering algorithm of choice. And this is indeed one of the most sophisticated algorithm used in many projects. So a cluster analysis is the task of arranging a set of similar data points into groups. It is an unsupervised machine learning task that can discover patterns or identify related groups from a dataset. There are many different algorithms proposed for cluster analysis. The one and the most common one that you probably will see if you do search for, and this is rather classical or traditional algorithm, which is k-means. So the k-means algorithm is commonly used for clustering since it is fast and easy to understand. However, there are some potential problems with this algorithm. First, the number of clusters or partitions need to be provided as input to the algorithm. Number of clusters that may be present in a new dataset is, however, not always known. So you have to put a number based on your assumption. Another problem with k-means is that k-means is more of a partitioning algorithm than a clustering algorithm, since it partitions all the data into groups by minimizing the distances between data points. These problems are also existent in other clustering algorithms. For example, the affinity propagation and spectral clustering algorithm are partition they partition all the data into groups, so even outliers or noisy data points are included in the cluster. Another well-known algorithm is agglomerative clustering, which, like k-means, requires a number of clusters to be provided as an input to the algorithm when a threshold parameter is not used. So these were the original some of the issues and problems with the traditional algorithm, and that's where HDB scan comes into the scene to solve some of them. So the HDB scan clustering algorithm is a density based algorithm. Unlike k-means, it does not require that every data point is assigned to a cluster, since it identifies dense clusters. Points not assigned to a cluster are considered as outliers or noise. For our current exercise here in this video, it is preferable to use an algorithm that does not require specifying the number of clusters upfront and can also tolerate some noisy data. So that's where our solution depends on HDB scan. Because density based algorithms, which is what HDB scan is, they are a good option here, as they do not require specifying the number of clusters and are indifferent to cluster shape. So I use HDB scan here. The full form of HDB scan is hierarchical density based spatial clustering of applications with noise, and they have this has become the most popular since it has fewer and more intuitive hyperparameters than dbScan and is robust to variable density clusters. The HDB scan documentation provides a very helpful comparison of different clustering algorithm. I definitely suggest you go through them to understand it more better way. Alright, with that, let's start with implementing HDB scan for creating or generating our clusters. Number of neighbors, NEIGHBORS. So I definitely suggest going through the documentation to understand and making sense of these arguments. The documentation is very well explained indeed. Am I spelling it correct? NEI. Yeah, there's a mistake. NEIGH. Sorry. Yeah. Next is number of components. So the what these function will do is that it will return the HDB scan object of clusters, meaning this function returns HDB scan objects after first performing dimensionality reductions using UMAP, which I'm going to include in a second. And in terms of the arguments, the first one, message embedding, this is the embedding to use. Then in neighbors is the it's an hyperparameter for UMAP. Also in number of components, that's also for UMAP, which is a hyperparameter. Mean cluster size, this is for HDB scan, that is the hyperparameter for HDB scan, and also mean sample and random stat. So first I am going to generate a UMAP embedding. UMAP and that will take all these arguments. In neighbors will be in neighbors, cosine distance, yeah, looks all right. And to that I need to apply the fit transform. Actually, let's take all these util function to a separate util.py file, because otherwise this main Jupyter notebook will become too much noisy. So I'm just going to cut it from here. This is my utils Python file. Yeah, it looks better and clean. All right, so my UMap embeddings, trans transform. This spell checking, yeah, quick fix, add UMap, okay. Alright, so my UMap embeddings are ready. Now next thing, I need the clusters from HDB scan. And here again, I need mean cluster size equal to samples. Metric, I'm choosing here Euclidean. Gen mean space tree. Yeah, let it become true. Cluster selection method. That for me is EOM. So this cluster is going to fit my earlier defined UMap embeddings. Yeah. Okay, this function is done. Yeah, and now I'm going to use this package HyperOpt, and so let's quickly see what is HyperOpt actually. So HyperOpt is an open source Python library created by James Bergstra in 2011. HyperOpt is a tool that allows the automation of the search for the optimal hyperparameters of a machine learning model, and it's based on Bayesian optimization supported by SMBO methodology adopted to work with different algorithms such as tree of Parsen estimators, that is TPE, and also adaptive tree of Parsen estimators, that is ATPE, and lastly the Gaussian process GP. So the approach of Bayesian optimization focuses on a probability model, that is a probability of a score given a configuration, this kind of thing, which is updated through an iterative process of querying a history age whose objective is the maximization of the score given a configuration. So HyperOpt takes Bayesian optimization as its premise by making some variations in the sampling process, the definition, and then narrow down of the search space and the algorithm for maximizing the probability model. So let's start building the basic util function for HyperOpt. Score clusters. So this method will return the label count and cost of a given clustering. And the arguments here are this cluster, which is the return value from the HDB scan clustering object, and probability threshold. This is a float number. This represents a probability threshold to use for deciding what cluster labels are considered low confidence. And at the end of the function, it will return a label count and also the cost. Label count will be the number of unique cluster labels, including the noises, and the cost is which is a fraction of data points whose cluster assignments has a probability below the cutoff threshold, which kind of represent the cost of clustering. So first I need cluster labels. Cluster.labels. So these cluster.labels underscore, this syntax is coming from the library itself. So this cluster object knows and stores the result in an attribute named labels underscore. That's what it is. And it is an array with an integer for each data sample. So it just represents an array, something like this. Okay. Yeah. So the samples that are in the same cluster get assigned the same number, and the cluster label starts at 0 and then count up. That's how it works. Cluster labels, and then I need a label count. Cluster labels. Total number will be cluster.labels and now the cost. Like I said again, that the cost is the fraction of data points whose cluster assignment has a probability below the cutoff threshold. And what is our cutoff threshold? That's this probability threshold, which is equal to 0.05. So I need a conditional statement here, np.count non-zero. Clusters.probabilities is less than the probability threshold, and it needs to be expressed as a fraction of the total number. Okay. So the HDB scan library implements soft clustering, where each data point is assigned a cluster membership score ranging from 0.0 to 1.0. That is 0.0 to 1.0. A score of 0.0 represents a sample that is not in the cluster at all. That is, all noise points will get the 0.0 score, while a score of 1.0 represents a sample that is at the heart of the cluster. That's significance of these cluster threshold score. I'm going to return the label found and okay, that's this function is done. I need the next function, which is my objective function for hyperopt. So this objective function is for my package hyperopt, which will be used to get the optimal hyperparameters. And this objective function is part of the kind of recommended way to use hyperopt. As mentioned in the documentation, it takes the first argument as param, which is a dict, and that will contain the values for the various configuration part of hyperopt, which is number of neighbors, number of components, minimum cluster size, and random state. So yeah, param and then embedding. And these embeddings is just the vector embedding of the text, and lower these label lower and label upper, they are the lower end of range of number of expected clusters and the upper end of range of number of expected cluster respectively. We are going to use this generate cluster that we have defined here. And that takes embeddings, then in neighbors, which will be equal to, I'm going to get it from the param dict. Any IGH BORS. Next one is actually I should just name this param as S. Oops. Yeah. And this random state is just random state as well. Okay, and next I need label count and cost from my the score cluster method. Probability threshold, I'm passing as 0.05. Cluster. Or maybe just add a S to both of them. And now I'm going to add a penalty on the cost function. So this penalty is kind of an extra cost when when this is outside of the desired range of groups. So you can choose different numbers. It's kind of an hyperparameter, and I'm choosing 100% penalty on the cost function if outside the desired range of groups. So label count is less than label lower, or penalty equal to 1.0, else in the loss function, the loss of value will just be cost plus penalty. Okay, and what I'm going to return from this method is dict status. Okay. All right, so this method is also over, and now my next method is for doing the Bayesian search. And now a quick word on the hyperparameter optimization with Bayesian search. So normally in machine learning, we have these four, the most common technique to do hyperparameter based hyperparameter search, which is manual. Manual is probably never used. Then I have grid search, random search, and lastly Bayesian model based optimization. And this is the one that we are going to use in this project. So in one sentence, the Bayesian hyperparameter optimization is about building a probability model of the objective function and use it to select the most promising hyperparameters to evaluate in the true objective function. So the main difference between Bayesian search and the other method is that the tuning algorithm optimizes its parameter selection in each round according to the previous round score. Thus, instead of randomly choosing the next set of parameters, algorithm optimizes the choice and likely reaches the best parameter set faster than the previous other two methods, that is better than a grid search or random search. Meaning this method, that is a Bayesian method, chooses only the relevant search space and discards the ranges that will most likely not deliver the best solution. Thus, it can be beneficial when you have a large amount of data, or the learning is slow, or you want to minimize the tuning time. So in contrast to random or grid search, the Bayesian search keep track of past evaluation results which they use to form a probabilistic model mapping the hyperparameters to a probability of a score on the objective function. And this is the official documentation of these hyperopt package that I'm going to use. And this is a GitHub page. I definitely recommend you go through them. So what they're saying is hyperopt's job is to find the best value of a scalar valued, possibly stochastic function over a set of possible arguments to that function. Whereas many optimization packages will assume that these inputs are drawn from a vector space, HyperOpt is different in that it encourages you to describe your search space in more detail by providing more information about where your function is defined and where you think the best values are. You allow algorithms in HyperOpt to search more efficiently. So the way to use HyperOpt is to describe the objective function to minimize the space over which to search, the database in which to store all the point evaluations of the search, and also the search algorithm to use. The most basic tutorial will walk you through the, okay, they are giving some basic defining a function to minimize. So this is the important part, and we have already defined that. This is that objective function that will be minimized by HyperOpt. And that's what they're talking about. HyperOpt provides a few levels of increasing flexibility, complexity when it comes to specifying an objective function to minimize. The question to think about as a designer are, do you want to save additional information beyond the function return value? Blah, blah, blah. Okay, so the next few section, yeah, so this is the most common syntax of implementing HyperOpt. The simplest protocol for communication between HyperOpt's optimization algorithm and your objective function is that your objective function receives a valid point from the search space and returns the floating point loss, aka negative utility associated with that point. So I need to define this fmin. Then I need to define the space, algorithm, and max values. Okay, is there anything important, more important here? The trial object. Okay, this trial object we are also going to use to really see the purpose of the returning dictionary. Let's modify the objective function to return some more things and pass an explicit trials argument to fmin. Okay, so we have already imported this fmin, tpe, and hp. Yeah, let's just go and complete the function. So this is our trials, and now I'm going to define the fmin. So this space is the actual search space, and that will contain later when I am going to execute this function. I need to provide this space, and that will contain all the in neighbors, in components, minimum cluster size, etc. We will see that in a second. Let's complete the function first. I'm going to use TPE here. And what is this space eval? We already have imported it at the very top. This one, HyperOpt. From the package HyperOpt, we imported fmin, TPE, HP status OK, spatial eval, and trials. Pretrained. Best. I'm also going to print some more thing. So, best trials. Result. Yeah, that should do. Well, I'm getting a syntax error. Let me see. I'm going to use generate cluster. This method, what does it return? Let me see again. In generate cluster, return me the clusters. So this is where we implement our UMap for actually doing the dimensional reduction, and then I get my clusters with HDB scan, and that's what is returned in this generate cluster. So that's what I need. And for the arguments to this method, I have all of these message. Let's just copy them, and later I am going to change it down here. So message embeddings, that will become only embeddings here. In neighbors will become best params. Here, similarly in components, and the rest of all the things actually will be coming from best params. And what it will return is okay. With that, now I'm going back to, so this is my utils file. Now I'm going back to the main Jupyter notebook, and here I have already imported all the methods from the utils file, so I can. Now I'm going to define the H space. And what is H space? This is this parameter space. So Bayesian search takes this argument, and that's what I'm going to define over here like this. So I'm just doing hp.choice, and then in neighbors range 3 to 32, in components also range 3 to 32, and level lower, level upper, I'm just defining 10 and 100 respectively. And that HP is coming from the module from HyperOpt. So we have already imported HP from HyperOpt. Cool. And now I'm ready to do my Bayesian search method implementation, and that's this. Let's run these few cells because yeah, the Bayesian search is not defined. Did I made a mistake in Bayesian? And I just had to restart the kernel, and it ran just fine. So with this, my Bayesian search is now executed, and next I am going to print the sentences of a given cluster. Let's do for cluster 11. Or place best clusters. And these best clusters use obviously is coming from the output of the after running the Bayesian search, because that's what I get: best params use and best cluster use and trials use. I just have to pick all the intent from that particular cluster. All intent index. Okay, let's run this. Yeah, this is the result for this particular cluster, and obviously it is supposed to be a very long text, because I'm getting all the text for this cluster number. List index out of range. Why did I get that? Let me fix. And I think I can just change these cluster number here to get rid of this problem. Yeah, so that's my all the text for this cluster. And the next thing I'm going to do is automatic cluster labeling. And for this purpose, for automatic cluster labeling, that is, we use Spacey library to get the words POS, that is parts of speech. From each cluster, we concatenate the most common verb, direct object, and top two nouns to build the cluster topic label. That's a core idea here. Now, this particular idea is coming from a rather recent research paper. Let me quickly open the paper. And this is a paper that I'm talking about. It was released in December 2001. Name of the paper is Open Intent Discovery Through Unsupervised Semantic Clustering and Dependency Parsing. So let's quickly go through the abstract. Intent understanding plays an important role in dialogue system and is typically formulated as a supervised learning problem. However, it is challenging and time consuming to design the intents for a new domain from scratch, which usually requires a lot of manual effort of domain experts. Okay, this paper presents an unsupervised two-stage approach to discover intents and generate meaningful intent labels automatically from a collection of unlabeled utterances in a domain. So what they're saying is, in the second stage, the objective is to generate an intent label automatically for each cluster. We extract the action object pair from each utterance using a dependency parser and take the most frequent pair within each cluster. For example, book, restaurant. This is a single action object pair as a generated intent label. We empirically show that the proposed unsupervised approach can generate meaningful intent labels automatically and achieve high precision and recall in utterance clustering and intent discovery. So this is the core idea in this paper, and kind of that's what I'm going to use. The problem of unsupervised open intent discovery involves two tasks: automatically discovering the intents from a corpus of raw conversational data, and two, automatically assigning each utterance in the corpus to the discovered intent. We generate the intent label that are interpretable using the most frequent action object pair within each cluster. We found that the experimental results on the SNPs dataset are surprisingly good, where the discovered intents match with all ground truth intent labels, and the task of assigning each utterance to the appropriate intent achieves a high F1 score of 93%. The contribution of this paper are threefold. Anyway, so yeah, so that's so what we need to build now is this action object pair, and following pretty much this underlying concept, and that's the core idea here. And what is to use the Spacey library to get the words parts of speech, and from each cluster we concatenate the most common verb, direct object, and top two nouns to build the cluster topic or cluster labels. So I need to import a couple of things. Let's close this. Yeah. And my data cluster will be, yeah, data cluster will be a pandas data frame. So this is where I'm going to zip my all intent, all this intents, and best cluster use. And I need to wrap this as a list. Okay. Label one. All right, so these are all the intents, that is all the text, and these are all the label st1. So let's quickly check. Data clustered. Yeah, so I was just checking a single label st1 equal to 2. Let's check another one, maybe 24. Yeah, looks all right. Okay, now next I'm going to find the IDF of every word. So inverse document frequency, or IDF, looks at how common or uncommon a word is amongst the corpus. IDF is calculated with this formula right here, where T, that is this single letter T, is a term or word we are looking to measure the commonness of, and N here is the number of documents, D is the corpus. The denominator is simply the number of documents in which the term T appears in. And the reason behind calculating the IDF in this case is that, as we discussed earlier, that we pick the most common verb, nouns, etc. to build the cluster labels. But sometimes the most common word or verb in a cluster is not the best choice. For example, for this particular case where the dataset is Steam reviews, we will see the words play or game in most of the clusters or comments. To balance that, I use IDF part of the TF-IDF concept. If a word appears, the fundamental reason here is that if a word appears in all the clusters or all comments, it is probably not that important. Think of equivalence of stop words, because they're everywhere. So, in contrast, if a word is not everywhere, we pay more attention to it, and that's the whole reason for doing IDF here. And later, when we look for the most common words, we give more weight to low frequency words and less weight to high frequency words which have lower IDF score. And another point that I could have used the TF-IDF vectorizer function from scikit-learn, but I did not use that in this case because the scikit-learn implementation includes some regex check, regular expression check within its function, which I do not want in this case because I pretty much here want to capture everything between two blank spaces, including all symbols or punctuations. And since later we will use a lemmatized and lower-cased version of the words for cluster labels, I regenerate now the reviews with the lemmatized and lowered case version of the words that we are interested in, that is verb, noun, adjectives, etc. We use this list. We will create a list here, and I'm going to name it as sentence with word lemma to find the IDF scores next. Oh, sorry, that is 4. So for the parts of speech tagging, I'm going to search for verb, noun, and adjectives. Or direct objects from the dependency. In that case, just append it to temp sentence. Lower and add a single space. Finally, add these temp sentence, or append this temp sentence to send with word lemma. All right, let's quickly check our first 3 of them. And now I'm going to define the IDF method. I'm using this counter again. So counter in a single word, it's an unordered collection where elements and their respective counts are stored as a dictionary. And here I just need exactly that. That is, I need each of the element and their counts. We will see the result in a second. Documents. Update the word count with my word set. I'm also going to print. Okay, let's leave it for now. All right, next I need. I'm just going to print the word count. Okay. I need the total, which is a sum. Excuse me. Which is the sum of word count dot values. And now finally my word IDF. So this word IDF will be a dictionary whose keys are the words and the values are the IDF score. So that's the dictionary, and key will be let's actually first define what are key and the value. So for k, v, and okay, and inside I need to implement the log method, log formula kind of. This is the formula that I'm going to use. It will be slight changes on the denominator. So let's say log base 2 total divided by v. That is all. I need to pass send with word lemma. Print this word IDF. Okay, let's run this cell. Yeah, so that's the result of my word IDF. So actually it's just giving me for each of the words, it's giving me the IDF score. And later, why I need that? Because I want to give a different weights to different words. We will see that implementation in a second in the very next cell indeed. Yeah, so and let's also quickly check this word count here. I just want to see that if word count is what I want. Right. So this whole thing is my counter object. We can see it starts with this word counter, and this counter object, it's just a dictionary where each word and the number of times they appear. And we can obviously see these game, play, get, all these things are like the really high frequency words, because this is a review of games. So this particular word game in this particular exercise, in this particular case, is not too important because they pretty much appear in almost every comment, every review. So they are not that significant. And to capture these differences in significance of different words based on their frequency of appearance in the whole corpus, that's why I created this word IDF. Because a very high frequent word like game need to be given a very low weight in my model, because they are not significant, they're not very meaningful in this particular exercise. Okay, let's move on. So now back to our automatic cluster labeling, and as we discussed earlier, what we are going to do here is this. Here we will concatenate the most common verb, direct object, and top 2 nouns from each cluster for our automatic cluster labeling. So quite a few util functions here that first I'm going to write. I can actually write those in utils. Okay, forget it. I am just going to write it in the Jupyter Notebook itself. First one I'm going to write is a function to return documents of a single category. So this function will take a data frame and a category column and a category as 3 arguments and return me the documents of a single category. That single category will be df category column and that's this function. And the next function is to get the most common words in a list of words. And here again, I'm going to make use of the counter module. Collections.counter. To that you pass list. It will produce a dictionary with each item and also their value, their count, the number of counts as their values. So if for k in list, counter k equal to 1, that is, it appears only once, then I should ignore it, because in that case as well this is not significant. So just pass else counter k, multiply that with the IDF, multiply equal to word. Okay, so this is where I'm making use of that weighting factor, or this is where I'm giving different weightages to different words. The basic idea is that if the word appears more than once in the entire cluster, repeat that word IDF times in our bag. If a word is a low frequency word, it has a high IDF value. So with this technique, we give more chance to this word to show up in the list of most common words. That's the very idea. Okay, so that's where I'm done, and I can return from counter dot most common. Yeah. All right, and now the last method in this regard, that is to implement automatic cluster labeling, is another function where I will be extracting labels from documents in the same cluster by concatenating most common verbs, objects, and nouns. Here we will concatenate the most common verb, direct object, and top 2 nouns from each cluster for our automatic cluster labeling. It will be a slightly longer function, but the function is rather very simple. We will see that in a second. Extract labels, and it will take category doc and another boolean parameter. Let's name it print word counts equal to false. Okay, now I need to I'm just going to declare some variables here, that is few empty list and few empty string. Verbs, direct objects, noun, adjectives, all are list. Similarly, I have verb, direct object, noun 1, noun 2 as empty string. Now for each document, what I need to do is append verbs, direct objects, nouns, and adjectives to a running list for the whole cluster. So for I, category doc, let me put some documentation or doc string here. So these first argument, category doc, this is a list of documents all from the same category or cluster. So category doc is a list of strings like this: fun, game, small amount, time, unless, lifer, etc., etc., separated by comma, of course. So it's just a list of strings. And print word counts, this is a boolean, as we discussed. True will print word counts of each type in the category. So here in this line where I am actually looping through the category doc, that means I'm looping through the each element, that is each of these strings within category doc. Okay. I can do like this because it's just a list. And then for is a stop word. Len of token if this is greater than 0, only then everything will make sense, otherwise no point. Okay, so what I'm doing in this line is ignoring if it is a stop word or the length of the stripped token is less than 1. And if it is not, then all the below logic will make sense. Token the position. Extend. Lower, okay. So that was verb. Next is direct object. Token.lemma.floor. Yeah, this will kind of get repeated for the next one. So direct object is over. Next one is a verb. I can just copy this. Here. Next one and the last one is adjective. Yeah, cool. And at this point, if I just print these most common verbs and pass the number of words to be 1, I get the output like this. Actually, yeah, like this. So most common, as we remember, most common is this method that we wrote earlier, which will get me the most common words in a list of words. And first, it takes the first argument is a list, and the second argument is a number of words, which is a number of top common words to return. And that's what I'm doing here from the verbs list. the most top common words to return, and that's a kind of output I get. Okay, what because I needed to see the structure of this output once again here for the next part of my code. And the next part is, so right now I'm going to use these print word counts. Okay, now I just want to print this counter. And now let's take the most common words of each form. Yeah, so we saw the structure will be returned from the most common like this. So that means verb equal to, I need to get the 0 and then 0 again. Okay, so I need to repeat this pattern a couple of times. Verbs and the objects, direct objects. The JS. Similarly, I need to do for noun 1 and noun 2. Yeah. Now concatenate the most common verb, direct objects, noun 1 and noun 2 if they exist. That's kind of the last step here. Label J. I also need to concatenate the nouns, but I'm not going to concatenate all the nouns just like that. I need to run an if loop. That is, if the nouns are not already there in label words, only then concatenate them. So forward in label words. Only in that case. Finally, if join with an underscore. Return level. And now it's time to check the execution of the function, and I just put a random current category text as a list and run these extract levels, and this is what I get: aim time, game live. So what it's producing is the object action object pair from the phrases in each cluster as a cluster label. So like we said that these probably is not making much of sense because we are just picking randomly from the reviews. But just to give an example, the one that we discussed previously, that action object will be something like book, flight, so on. And that's following the paper's recommended technique of automatic cluster labeling with dependency parsing. And now I'm going to check the output from my get group method, and I will pass a data frame, category column, and a category and a label for this. So the df, the data frame, will be my df cluster that we already defined. Where is it? Yeah, that's the one. DF cluster is our data frame that on which we are working currently. So this one has a text column and has a label st1 column. Okay, so that's what I'm going to use here. Get group. First, it will take the DF clustered. Then the name of the column is label st1. Why it's saying so this is data clustered, and the last one is just a single label randomly I'm choosing, and let's run it. Okay, so this one produces a data frame where I have all the label STs value as whatever I've given here, 18. So I need to convert it to a list. So let's do a list like this, and then pick only the text. Yes. So now I get only the text columns values as a list. So this is what I'm going to work with currently. All right. Now, yeah. So let's go on and check my next method. Because right now the method that this is the final kind of method for this whole exercise, and this method will present the whole summary in a single data frame, and it will assign groups to original documents and provide group counts. So actually what I'm trying to do here, let's just something like this I'm trying to do. So I want to have all my label st values, their counts, and also the final topic or the main label of the entire reviews of each of these reviews. So for example, this is coming from this long method that we wrote implementing our automatic cluster labeling, that is extract labels. This method will do the automatic cluster labeling technique and give me the actual labels with action object kind of meaning, and that's what these column represent here. So this is the kind of output I want to see, and that's what I'm going to write a function for now. First, get all the unique numerical labels that was generated by the sentence transformer model. That means I have to apply, I have to get it from these data frame and applying unique method on this. And then create a dictionary of the numerical category to the generated label. So this is where I'm going to use the same thing that we just did. This list is what I need. So this will just produce a list of strings for a particular label. And the only thing I need to change in this expression is change this label st1 to, and because this is looping through each of the label names, so label values, so just label. Label dict, label. Extract labels. This is where I'm using my long extract label methods. Okay, with this loop, my label dict will be completely updated. Now I'm out of the loop, and so now I'm going to create a summary data frame of numerical labels and counts. Group by category call and then text dot count. Yeah. Text count. Sending equals false. Lastly, apply the generated labels. Label dict x. Now let's finally execute this method and produce the result. Data clustered. And that is it. That's the result that I got. So I got for each of the label, I got the final outcome of my topic model, and this is following the automatic cluster naming technique. So this is each of these labels, each of these topics actually are action object. That's how it is. And this column gives a count of each of these labels. So for 31 label, I have 50 count, and the 31 label is actually recommend game time. And once again, if you are not sure that what this automatic cluster technique is, we referred this paper that was published in 2021, which named Open Intent Discovery through Unsupervised Semantic Clustering and Dependency Parsing. And the main thought here is this, that the objective is to generate an intent label automatically for each cluster. We extract the action object pair from each utterance using a dependency parser and take the most frequent pair within each cluster, for example, book, restaurant, which is action and then object. And exactly we followed here. We took spaCy to do the dependency parsing and got the noun, verb, dependent objects, and then took the most frequent dependent objects, and then concatenated the noun, verbs, and the dependent objects, the direct objects, to form our labels. And that's what we see here. These final labels are the final topics, and they represent the action object as advised in the paper. Alright, that pretty much wraps up this video. If you have liked this one, smash the like button. And also do subscribe, because I'm going to do many interesting NLP projects over the coming days and weeks. So, see you in the next one. Thank you very much for watching. Hey everyone, in this video I'll be looking at this live Kaggle Competition Feedback-Prize English Language Learning, where I will be working with DistilBERT large V3 model, which is a pre-trained model and available in HuggingFace, to predict the English language essays written by students. And that is the very target of these live Kaggle competition. And remember, again, this is a live one. That means if you win this competition, you will win a prize money of $55,000. Anyway, so that about we have got 3 data sets here: train CSV, test CSV, and sample submission. The most important ones are these two: train and test. The training set comprising the full text of each essay identified by a unique text ID. The essays are also given a score for each of the 7 analytic measures above: cohesion, etc. These analytic measures comprises a target for the competition. And for the test CSV, for the test data, we have only given full text. Okay, so let's look at the train CSV first. It will make sense then. Okay, this is our train CSV, and one second. And what we got here is a unique ID for that kind of represent each student. And then I have a full text, and then the different heading under which this text is measured and the scores given. So one heading, for example, is cohesion, and this particular writing got a score of 3.5. Then syntax 3.5, vocabulary 3.0, and so on. I have got even more heading. Phraseology, grammar, and conversational, what is that? Conventions, okay. And so that's my train CSV, and in the test CSV, I have only got unique IDs and the text, and the job here is to look at this text and predict those other scores under those different headings. And what are those headings again? And these are the headings. And if you are interested of what exactly these headings means, the competition host has given a document here, Google Doc, where all the definitions of those headings are mentioned. For example, the cohesion represent a text organization consistently well controlled using a variety of effective linguistic features such as reference and transitional words and phrases to connect ideas across sentences and paragraphs, appropriate overlap of ideas. So very much these are the metric by which that text will be rated or scored under the cohesion heading. Then let's look at grammar. It's obviously command of grammar and usage with few or no errors. Then, for example, the syntax, flexible and effective use of a full range of syntactic structure, including simple, compound, and complex sentences. There may be rare, minor, and negligible errors in sentence formation. Okay, so that's how those heading means and the significance of those headings, and these are the various scores that these writings have obtained. So and that's what I'm looking at train CSV, and those scores will need to be predicted under the test CSV. That's the whole purpose. All right, with that, I am already inside my Kaggle kernel. The first cell, I'm just importing all the libraries, and specifically to mention that I'll be using DistilBERT V3 large, and that's why I'm importing all these transformers and related modules. And also I'll be using PyTorch for this. And here also I'm importing some more libraries. And here in this next cell, I'm just defining all the root directories or necessary directories. So my base directory is Kaggle working. then ds train path, which has a train CSV, ds test path, which has test CSV, sample submission path, which has sample submission. Now, save directory is where my model, my some other models that I have used, pre-trained models, those are available, and also DistilBERT v3 large offline path. That's where I am saving the HuggingFace model, because in this kernel I am not using internet. If you know that in Kaggle kernel you may switch on or switch off the internet uses. So if you are not using the internet, that means you need to save the model actually in a path, and that's where that's this path means. And when I'm running pwd, that means present working directory, that will just show Kaggle working. And here I'm just printing all the available data sets or models for this particular notebook. Remember, if you want to add a data set, you need to do it from inside the kernel. And for that, you just open up these right side menu, you go into your data, and here you click on add data, and there you can choose whatever models or other data you need to add. So in this case, I'm using some pre-trained model which are saved, and these are those models. So this one is obvious, DistilBERT v3 large, which is HuggingFace DistilBERT v3 large model. And then I'm also using another one, DistilBERT Dhankar v20. This is another pre-trained model that was used by many other Kagglers who have scored high in this competition. So I am also making use of this model, and this is a pre-trained one. You can just search by this name and you will get that. And the first one is obvious. This is the actual input data of this competition. And I will give a link of these two other models that I'm using in my notebook and in the source code. You will get that in the GitHub link down at the description section of the video. And otherwise, I'm obviously using the GPU because I need that. Okay, so yeah, so now when I'm printing the all my files that are available inside my working directory, that is Kaggle input, these are those files. Okay, and here you can see my train CSV, test CSV, submission, sample submission, and these others are the pre-trained models. And then also this DistilBERT v3 large, this is also my pre-trained model. So with that, this is all the things that I need to work in this video, in this notebook indeed. And then this small class is a config class. So all I'm doing here is defining all the configurations for my model. So base directory, device, seed of 69, dataset path. I have quite a few dataset path here. And then tokenizer parameters, truncation 2, padding false, max length 512, model name, I'm using Microsoft DistilBERT v3 large. Target columns are just the different column names that we need to predict. Learning rate 0.1, batch size 5, epoch 5, and folds 5. Okay. So that's my configuration, and I'll be using this configuration many times. And just a quick, just to see the data, as we already saw this in the actual CSV file, but here I'm just printing the head with as a data frame by reading it with pandas data frame, and this is the data set. So I have the text ID, which is unique. Then I have the actual text, full text column, then cohesion, syntax, vocabulary, phraseology, grammar, and convention, which are the different headings under which these texts are scored. And I'm supposed to predict these scores for the test data set. Now time to do some basic EDA here. First, I'm just going to do a heat map for checking the correlations. All right. Uh, yeah. Kind of many of them are on the higher side of the correlation among them. Okay, now I am going to make use of some plotting of histogram. So of the various target values, that is cohesion, syntax, vocabulary, etc. Trained here full text. Discrete. Color discrete sequence. I need a particular color code, hex code. That's this. Plotly dark. Finally, I want to use color. I need the hex code, which is this. Histogram got an unexpected keyword argument title here. The spelling TITLE. Cool. So that's my plotly histogram of full text string length. And we can see that the concentration is towards 2000 to 2200, something like that. Okay, now I want to do the same histogram for each of the target, that is each of the features in my data frame, which are, what are they? They are cohesion, syntax, vocabulary, I think phraseology, etc. So first define the colors for the 6 heading, 1, 2, 3, 4, 5, 6 here. So I can just put the, let me copy the column names. Original for the previous plot was, I think, box, yeah, and this one I want to use violin. Name GIG is not defined. Where is that? Cool. Now they just drew the histogram for all the 6 targets. So cohesion, syntax, vocabulary, phraseology, grammar, conventions. Okay, cool. And now pre-processing before starting the model configuration, etc. And during the pre-processing part, first I will have few util function to deal with the encoding error. So the first one is replace encoding with UTF-8. Error of type here, and that actually will give me so about this encoding and decoding, you can read further in the Python's codex page. This one, you can just go to library codex.html. That will give you more details about these various encoding methodologies, decoding methodologies, etc. So next I'm going to replace decoding with CPL1252. See. And then I need to now register the encoding and decoding error handlers for UTF-8 and CP1252. Codex.register error. So what was this name? Copy this whole thing. Similarly, And now I need to resolve the encoding problems and normalize the abnormal characters. So the last util function in this regard errors. Then I need to pass here replace decoding with CP1252. Next here is replace decoding here. You need decode. All right, now the trend will be just read CSV train path. Similarly, I need to do for df test and df submission. Df trend dot head. Yeah. So now I need to apply to these df, actually to all the df train test and ss, these Unicode resolving methods. So, and I need to apply these only for the text column. So first one is resolve encodings and normalize. What is that here? df test. Config dot and now finally I am ready to define my tokenizer. What was the name that we defined? Yeah, DistilBERT of v3 large path. Run it. Okay, so this is our data frame. Now define a utility function named tokenize. tokenizer, and then we'll get text. DFI. All the target columns from our original data frame. That will be my tokenized labels. So config dot that will be input IDs. Okay. And so now that my tokenize is ready, I need to do a little bit of things here to check the proper data set from pandas is obtained here. So from pandas, this df test has already been defined earlier. Let's quickly see. Df test, yeah. So df test is just pd.readcsv of my ds test path. That looks good. So now, so that's what I'm reading here, and then ds will be. So this map function is coming, it will take the tokenize and also a couple of configuration like badged, description, etc. So tokenize badged equal to false. This map function is actually coming from HuggingFace because I'm reading a HuggingFace data set here. Or description equal to, yeah. And a quick word on this map function here, because this is a very useful function and will be used very often when you are working with HuggingFace dataset. So the primary purpose of map is to speed up processing function. It allows you to apply processing function to each example in a dataset independently or in batches. This function can even create new rows and columns. In this case, for example, this map function is applying the tokenize method that we just defined here on each row of our data frame. All right, with that, let's proceed with here. So after my dataset is defined and properly, this tokenize is properly applied to each rows, now I'm going to save to disk. And here, this is where it is going to be saved, data.dataset. based here pkl. Pickle.dump pf test fp. Okay. Now at this moment, if you just want to see what these HuggingFace dataset for us looks like, just print this dataset. So as expected, this dataset is in a special type of structure. This is specific to HuggingFace dataset, and what I'm getting is a dict with features and number of rows. So for the features, I have full text ID, full text cohesion, syntax, vocabulary, phraseology, all of them. And you can actually print only the keys. DS0 will give you the full text. So let's just print the keys. Yeah, so that's my that's all the keys in the dataset: text ID, full text, cohesion, syntax, vocabulary, phraseology, grammar, convention. Up to these we already know because these are our features in the original dataset, and then I am getting the specific things which are specific to HuggingFace, particular way it saves dataset. I have input IDs, token type IDs, attention mask, labels, and length. Okay. And next, before our modeling, the most important thing we have to do is to take care of pooling. And we are going to use mean pooling and max pooling here. So before understanding pooling, you need to understand what is the difference between token embedding and sentence embedding. So sentence embedding play a completely analogous role to token level embeddings, with the main difference being that, as the name suggests, that there is only one embedding for the entire sequence rather than one embedding per token. So the process of converting a sequence of embeddings into a sentence embedding is called pooling. So intuitively, this entails compressing the granular token level representations into a single fixed length representation that is supposed to reflect the meaning of the entire sentence. And that's the job of pooling. And this image fundamentally shows the architecture of the pooling mechanism. So essentially, sentence BERT adds a pooling operation to the output of BERT or Roberta model to create a fixed size sentence embedding. And the fixed size sentence embedding is the key to producing embeddings that can be used efficiently in downstream tasks such as inferring semantic textual similarity with cosine similarity scores. And the sentence BERT does this by a pooling strategy. The default pooling strategy of sentence BERT is mean pooling strategy. There's also another pooling strategy called max pooling. So now what's the difference between mean pooling and max pooling? So under the mean pooling, if we obtain a sentence representation by applying mean pooling to the representation of all the individual tokens, then essentially the sentence representation holds the meaning of all the words or all the tokens. But under max pooling, that is, if we obtain the sentence representation by applying max pooling strategy to the representation of all the tokens, then essentially the sentence representation holds the meaning of only the important words. Alright, that was about the theory of mean pooling. Now I'm going to code it, and for mean pooling there's some boilerplate code indeed available in the documentation of HuggingFace and also TensorFlow and few other packages. Basically, I'm going to extract the attention mask, unsqueeze it, and change the dimension or view the dimension with expand method, and then apply averaging to the sum of the embeddings. Let's just define that. And this code, this particular code, or rather this technique of calculating mean pooling, will be used in many projects in NLP wherever you are trying to do sentence embedding. This is here I'm using PyTorch, and that's why this is an init module here. So I can get all the methods from an init module. Diff tension mask dot unsqueeze. Expand it to view it in a particular with a particular size, and that size will be last hidden state, that size, and then apply float. Now sum of all the embeddings will be last hidden state, multiply that with input mask expanded. Clamp it with torch.clamp between values of sum mask and finally my mean embedding will be sum embeddings divided by sum mask. That is all. And the next method that I'm going to, the class that I'm going to write is going to be the longer and the main class for our training, for our applying the DistilBERT pre-trained model on my data. But before proceeding further, quick word on this last hidden state here. What we see here that we are getting these, we are applying this expand on the last hidden state. And what is this last hidden state? So the BERT model without any heads on top outputs two things: last hidden state and polar output. This last hidden state contains the hidden representation for each token in each sequence of the batch. So the size of this last hidden state is batch size by sequence length by hidden size. And this last hidden state is the sequence of the hidden states at the output of the last layer of the model. All right, now let's move on to our main class. DistilBERT large. What was the name? I think no, I need to pass a dict here, and that dict will be output, hidden state, hidden dropout probability, all these things here. Attention probes dropout, that's 0. Add pooling layer, false. Okay. Transformer. This is where I'm loading the DistilBERT v3 large model. Again, I need to pass the path here. We have already defined this model config right here. So again, because this notebook in Kaggle I'm using without internet, and that's why I have to pass a local path to this DistilBERT model, and also for this config I'm passing this local config.json file. But if I was connecting to internet, then I would not do this. I could get the config something like this. Sorry, not this one. I could get the config. 1 second. So actually, let me type that. In that case, it would be transformer model equal to and path would in that case would be the original path, whatever, like Microsoft DistilBERT. And for the config, I will just do config equal to self.model.config. Yeah, and this one will actually fetch the config.json file from the internet. That is from the original models hosted in HuggingFace. But here I do not have internet, so I am not using this line. Okay, so my model is defined. Next one is I need to define the layer norm. So I can make use of PyTorch nn.layer norm. Transformer model.config. I need to get the hidden size. Multiply that by 2. Okay, this is important here. Note that I'm multiplying by 2 is because we will see in a second that we will be concatenating the mean and max pooling. So that's why I need to multiply the hidden size by 2, because I'm using both mean and max. And next is self.output. That's a linear layer. The first one will again take this whole thing. Actually, I can just copy self.transformer model.config.hidden size multiplied by 2. Yeah. And the next is my length of the target column. Target COLS. And this I'm getting from my original config, which has been defined right here. Target calls all the feature names in the data frame. Okay, that's output. Next one, I need to define hidden layer weights. That would be parameter. Oops, it's not there. Torch.zeros. So that model config. Layers. And that I need to view, change the view with -1, and the rest are all 1. 4-dimensional tensor it is. Okay, and next I need to define a dropout layer. And for that I'm going to use a module list. So drop out should be module list. And to that I will pass a list, which will be nn.dropout multiplied by I in range 5. So these nn.module list is just like Python list. It was designed to store any desired number of nn.modules. And normally it may be useful, for instance, if you want to design a neural network whose number of layers is passed as input. So why we use module list instead of normal Python list? And that's because if you use a plain Python list, the parameters won't be registered properly and you cannot pass them to your optimizer using model.parameters. And that's why you will see a lot of use of module list in a neural network architecture. Okay, so where I'm doing this here, 0.1 multiplied by I for I in range . So smooth L1 loss is what I'm using. Reduction operator. Alright, with that, my this initializer constructor function is done. Next, I need to define the all-important forward method. Output, let's name it output backbone. Transformer model. Now extract the hidden states. And now I am going to do a min max pooling over hidden layers and then concatenate with pooler. So tuple, and for the hidden states I need to do minus I minus 1 I in range len hidden stats, and then minus 1. Need to define the dim as well, dimension across, dimension of 0. Hidden layer. Torch.sum, sum over the hidden states multiplied by layer weights. Hidden states. And now finally concatenate with pooler, that is concat the mean and max pooling. Output backbone. Out mean and out max. And similarly, backbone output backbone. Then from here, I'm going to take everything from the first dimension, 0 from the second dimension, and everything from the last dimension. Now, configure for multiple outputs. Dropouts. Self.output. Output backbone. Remember what was our output? That was a linear layer. This line right here. So logits in this case will just be equal to self.output. Else self.output. Okay, that's it. Now return logits. Okay, now next I need to just define two quick functions, which is train data loader and validation data loader. Oops, data loader, and also okay, and now I need to define a helper function to differentiate the parameters that should receive weights decay. So basically now I have to take care of the optimization process with differential learning rate, etc. So define this method called get weight decay, keep it at 0.01 as a default value. Yes. And now I need to define a list where where they are not subject to weight decay. So this list is this bias layer norm.bias and layer norm.weight. Finally, I should be able to define optimizer parameters. This will be a list of PARAs. Transformer. If not any, very important. If not any, then N for ND in no decay list. All right. And the learning rate is actually this one will be weight decay, WE. Okay. And the next one, I can actually copy this thing, then change few things. P4 np in self.transformer dot name parameters. And now it will be the opposite. If any nd in n for nd in no decay list, right? And in this case, the learning rate is encoder LR, weight decay is 0 and 0. Sorry, 0. Okay, and finally copy and paste again and change few things here. P4 NP okay, this one will be self dot named parameters if, okay, let me just change it here. Okay, and error is decoder error with decay is 0.1, 0.01 indeed. And another function in this respect is to for the configuration of the optimizers. And now define a warm-up step. So the idea of warm-up steps is to use some warm-up steps to increase the learning rate gradually up to a certain point, and then only then use your normal learning rate decay afterwards. Warm up. I need to divide epoch steps by batch size. And here I'm going to use the function that we imported earlier, which is get polynomial decay schedule with warmup. This is one of the strategy to decay the schedule, to decay the learning rate from the PyTorch library. So you can definitely go and read about it, what it does. So basically this method, okay, we will discuss that later actually, because now let's complete it first. First one it takes is the optimizer. And power, oops, sorry. Okay, that's my scheduler. Now my learning scheduler config. And finally, we return from this method a dict with config. All right. Okay, now coming back to this get polynomial decay schedule with warmup. So this creates a schedule with a learning rate that decreases as a polynomial decay from the initial learning rate set in the optimizer to end learning rate defined by the LR end after a warm-up period during which it increases linearly from 0 to the initial learning rate set in the optimizer. That's how it works. Okay, now we are done with that. Now I need to define a predict function for evaluation that will take data. Config that device. And what else? Zero val.reshape -1 dot 2 eval in okay. Now output inputs. From there I take input IDS inputs false. Let's extend this tensor, prediction tensor, with outputs dot number. So basically what I did in this method is I'm looping through the batches, and for each batch I'm getting the inputs from the batch.items. Then from that inputs I'm actually then passing that inputs to my model, and how I'm passing, because to the model I need to pass the inputs, then input IDs, and also the attention mask. So both of these input IDs and attention mask I'm getting from the inputs tensor that when passed to the model produces my outputs. And then I am doing prediction.extend and then passing the outputs as a pure numpy after removing the gradient from it. And then so that was a single batch. Now after all the batches are done, I'm just doing a vertical stack of all these predictions to produce my final predictions, and that's what I'm returning from the function. Okay, now finally time to run these training and derive the predictions. Data. Define a set of columns to keep this is where I'm removing some of the columns which are not in keep calls. Okay, and now yes. I'm creating the data loader for feeding into the model with testds. This is where I'm using this collator that we defined right here. Okay, that's my test data loader, and now model. And I'm loading from the checkpoint. We already imported some of the pre-trained model and dataset, so that's what I'm going to use now. And that this was saved in the save d that we defined in the config, so I need to get it from there. Config dot save dir, and then comes Microsoft DRTA DistilBERT of v3 large. That's how the saved model was named. That is DistilBERT of v3 large underscore the fold number, and also .ckpt because it's a checkpoint. Okay, then train data loader will be none, and validation also none. Config equal to config. Okay, now finally my preds tensor. So here I'll be using the predict function. To that I'll pass the test data loader and the model. And look how we did the predict function. It will give me the prediction as the vertical stack of individual prediction from each of the batches. So from this prediction, now I need to run a little if condition. Hold. Parents plus equal to. Okay, and finally I can just delete some of the variables which I don't need. Model, test, data loader. Cool. And after this, so now this is my training and the final predictions from the model. And then I'm going to use these final preds, this variable in the next cell, to create my submission data frame. Because as we remember, in the test data set, there were only unique IDs and the text, and I'm supposed to predict all the columns. So that's what I'm going to do, and create my data frame for submission. SDS config.basediv. database here, and then data set. I text. Okay. Let's just print it to check the shape. And now my final submission data frame. So one columns just for the test IDs. Text ID. And now add another column with all the target column names and the scores for all those features or target columns. Configure target calls. That's it. My data frame should be ready now. Let's just check the head of this. So I'm back in the Kaggle kernel, and here my training code ran. So this is where the folds were running, and yeah, so after all my folds ran, I ran this code here to create my data frame, and this is the final data frame ready for submission. So after this, I just run these two CSV method on these from this data frame to create submission.csv, which I will submit to the Kaggle competition. And with this submission, I got a public score of 0.44 in the competition's public leaderboard, which is not too great because all the top scoring from all in the leaderboard was 0.43 or better. So, but remember, this was a very baseline submission. I did not do any data pre-processing that much or any tricks or any feature engineering. It was just a direct application of DistilBERT model on these dataset to create a baseline submission. So, so on top of these, there are many ways to improve, many strategies to implement, but that's a subject of a totally different project. This exercise was purely to check what a baseline implementation of DistilBERT v3 large could produce for this kind of competition. Alright, that pretty much wraps up this video. If you have liked this one, smash the like button. And also do subscribe because I'm going to do many interesting NLP projects over the coming days and weeks. So, see you in the next one. Thank you very much for watching. Hey everyone, in this video I will do text summarization with GPT-2, BERT, that is BART, and Pegasus. So I am right in my Google Colab session, and first you need to install all these packages, transformer, sentence piece, and datasets. Then this package Sacre Blue is for calculating the Sacre Blue score on your predicted or generated text. Then also RogueScore to calculate the RogueScore, and Pi7ZR package as well. And then you just import that, the just a regular code, nothing to explain here. I'm just importing the transformer and all the other rest of the modules. And for the dataset, I am going to use the CNN Daily Mail dataset that's available in HuggingFace Hub. This is the official page of the dataset, CNN Daily Mail. So the summary of the dataset is like this. The CNN Daily Mail dataset is an English language dataset containing just over 300,000 unique news articles as written by journalists at CNN and Daily Mail. The current version supports both extractive and abstractive summarization, though the original version was created for machine reading and comprehension and abstractive question answering. So let's look at this dataset. So this is the version 3 of the dataset, which is what I'm going to use in this exercise. So the main thing is this article column has a full article, and the highlights column has the highlights of them, that is a summarization, and that's what is important for this exercise, because what I'm going to do, first check what the different models are doing on this data set on there, and what kind of metrics, evaluation metrics, the 3 models that I'm going to use, they generate on these data set while working on the test set. So right now I'm looking at the train set, and there's a test and validation set. So if you go to test set, this is the test set, and as you can also go to validation. Just the row numbers are different. So I'm going to do the evaluation metric calculation on the test set on those 3 models, that is GPT-3, BERT, and Pegasus. And yeah, so let's go back to my code here. And in this cell, I'm just importing the load dataset module from datasets, and then loading the CNN Daily version 3. And also I'm printing the features by doing dataset, then taking the train part, and with dot column names that will print your all the column names, that is a feature names. So it may take a couple of minutes to download because the dataset is slightly not too small indeed. And the features are just what we saw in the HuggingFace documentation, that is article, highlights, and ID. That's what I got, article, highlights, and ID. All right. Now in the next cell here, I'm just printing the 500 characters from the first row of the trained dataset. So basically I'm just printing one element of the dataset, or one news article, and excerpt of the 500 characters, and also the length of the highlights. And this is what I get, that is a summary length is 281. That is a number of characters, but the excerpt of the 500 characters total length is 4051. So you can see that the summary length is quite a bit smaller compared to the original articles, and that's obviously that's expected, and that's a summary. But this the size of the summary, that is the length of the summary, gives you the kind of extraction you have to do from the original article. All right, and now the actual text summarization pipelines. So first, as a first step, what we are doing is we are collecting, I'm just taking a sample text of the first 1000 rows only. Remember the original dataset has, let's go to the dataset card. So what they are saying is that the CNN daily dataset is just over 300k unique news articles. So total 300,000 unique news article. But for my purpose to generate and calculate the summarization, I'm only taking the first 1000 as my sample text. And then I'm creating a dict of summaries, and that will just this will collect the generated summaries from each of the model in these dictionaries. And the models, again, I'll be using 3 main models, which is GPT, Pegasus, and BERT, B-A-R-T. But first, a baseline model I will generate so that I can see what kind of improvement my evaluation metric shows compared to a baseline, almost manual kind of calculating summarization. So for the baseline, I'll define a little util function. New line. And with that join, join the 3 sentences taken from the text corpus. Before that, I need to define a sent tokenizer. Let's define my sent tokenizer. Actually, the send tokenizer I am importing from the analytical library at the very top. So that's my nltk.tokenize import send tokenize. So that's what I need to tokenize my sentences. So let's go back to the util function. Send tokenize, just take the text and take the first 3. That is all my baseline summary generator. Now what I'm going to do, update these dict that we have already defined here, these summaries. To that I pass the sample text. Okay. And let's print this as well. Yeah, so that's my baseline. Behind the scene series, CNN correspondents shared their experience in covering news and analyze the stories behind the events. So this is just a manual summarization with my baseline. And now, next one, I'm going to use our very first model, which is GPT-2. Now, there's in HuggingFace, there's actually 3 models for GPT-2, which is GPT-2 large, GPT-2, and GPT-2 medium. Now, for any serious case, you should use GPT-2 large because that's relatively larger model with many more parameters. But collab session would not support that because that will need more than 12 GB or 16 GB of RAM to run. So I'm going to use, just for the sake of showing some result, GPT-2 medium, which is comparatively much smaller than the large one. Pipeline. Now these HuggingFace pipelines are just a great and easy way to use models for inference, and that's what I'm going to use. You have to provide the configuration to the pipeline here, text generation. That's what I'm giving, and that will return a text generation pipeline. Model is the name of the model. Now, probably you already know that GPT-2 is mainly for generation of new text, but we can use GPT-2 to generate summaries by simply appending TLDR at the end of the input text. The expression TLDR means too big, didn't read, is often used on platforms like Reddit to indicate a short version of a long post. And we will start our summarization experiment by recreating the procedure of the original paper with the pipeline function from Transformers and passing that TLDR at the end of the input text. So sample text, then at the end of the sample text, I need to pass the TLDR. That's the expression. That's tokenization. Let's just run it. It may take a couple of minutes because it needs to download the model. While it's still downloading, I just let me go to the next slide. Oops, model keywords are not used in the model cleanup tokenization spaces. So I think I must have made some spelling mistake here. Let me see. Yeah, that's right. There's a S at the end of it. So run it again. Pipe out. It's trying to generate the text, and this time it is not downloading the model because it was already downloaded while I ran it the last time. So right now it's just going through the model and generating it, and still it's taking longer than I expected. Alright, the running got over, and I'm just printing this pipe out, this final variable, and that's the generated text. And it very clearly shows, it gives me a whole list, but within the list I have this dict, and that dict has a key of generated text, and this is my generated text. All right, for my sample text, what was my sample text? And that was the first 1000 elements, or the first 1000 news article. Okay, so that was GPT-2's output from my piping, but I need to actually summarize it. So what I need to do is pipe out, take the 0th element, because that's the only element it has, the list, and after that generated text. Query. So this GPT-2 query is where I use the TLDR. That's how we produce summarization from GPT-2. And let's run it. Okay, so that's my produced or generated summaries from GPT-2. Okay, now update my summary dict that we defined earlier, that is this one, with the output of the GPT-2 summaries. Actually, I can just copy entire thing. Okay, so that saves the output or the summary output from the GPT-2 model in this dict. And the next one I'm going to use is T5. This is a very well-known text-to-text transformer, which is used for text generation, text summarization. It is a transformer model that is trained in an end-to-end manner with text as input and modified text as output, in contrast to BERT style models that can only output either a class level or a span of the input. So this text-to-text formatting makes the T5 model fit for multiple NLP tasks such as summarization, question answering, machine translation, and classification problem as well. So how is T5 different from BERT? That is, I'm talking about BERT. So both T5 and BERT are trained with MLM. Remember, the MLM means Masked Language Modeling Approach. And what is MLM? MLM is a fill-in-the-blank task, basically, where the model masks part of the input text and tries to predict what the masked word should be. And that's pretty much it. And the only difference is that T5 replaces multiple consecutive tokens with the single mask keyword, unlike BERT, which uses mask token for each word. And that's pretty much the difference between T5 and BERT. And T5 expects a prefix before the input text to understand the task given by the user. For example, token prefix means it could be summarize for summarization, then translate English to Spanish for machine translation, just as an example. And in this case, because we are doing summarization, so we are going to use the prefix as summarize. But because we are using pipeline here, that is HuggingFace pipeline, in this case, I can directly load T5 for summarization with the pipeline method, because pipeline takes care of formatting the inputs in the text-to-text format. So we don't need to prepend the term summarize while you are using pipeline. Pipeline summarization model this time is T5. Again, I'm using T5 small is because that's what I can accommodate within the collab session. You can definitely use many other forms of T5. In HuggingFace, there are T5 large, T5 11B. T5 11B is really large model. So yeah, depending on your on the hardware of your machine, so you can use the larger ones, and those definitely will give you better result. Pipe out will simply be pipe, then sample text. That's all. Run this cell. Again, it's downloading the model, T5 small model. So let me just pipe out. That should give me the summary text. Yeah. So I got a list just like previous case, but in this case I got the keys text is summary text. Remember, for GPT-2 the key text was generated text. That's the only difference. Otherwise this is summary text and this is the whole summary. All right, and now I just update my summaries dict T5. Tokenize pipe out 0 summary text. That is all. Run this cell. Okay, the next one is BERT. So BERT is a denoising autoencoder for pre-training sequence-to-sequence models. It is trained by corrupting the text with an arbitrary noising function and then learning a model to reconstruct the original text. It uses a standard transformer-based neural machine translation architecture. That means it uses a standard sequence-to-sequence or NMT architecture with a bidirectional encoder like BERT and left-to-right decoder like GPT. This means the encoder's attention mask is fully visible like BERT and the decoder's attention mask is causal like GPT-2. which also means that a fine-tuned BERT model can take a text sequence, for example, English, as input and produce a different text sequence at the output, for example, in French. This type of model is relevant for machine translation, question answering, text summarization, or sequence classification. Another task is sentence entailment, which, given two or more sentences, evaluates whether the sentence are logical extension or are logically related to a given sentence. And for our case, I'm just going to follow the same pipeline way of bringing in BERT, run this cell. It's downloading 1.63 gigabytes, so it is going to take a few minutes. In the meantime, I'm just updating my other codes, that is updating my summaries with the output of the BERT model. All right, and now I can print this pipe out, that is a summarization, and it produces my summary text. So this is my summary text with the key of summary text. So I'm updating my summaries dict again here, that is with the output of the BERT model. And okay, that got updated. And now my last one is Pegasus, very popular model for text summarization. So this Pegasus model's pre-training task is very similar to summarization. That is, important sentences are removed and masked from an input document and are later generated together as one output sequence from the remaining sentences, which is fairly similar to a summary job. So in Pegasus, several whole sentences are removed from documents during pre-training, and the model is tasked with recovering them. The input for such pre-training is a document with missing sentences, while the output consists of missing sentences being concatenated together. The advantage of this self-supervision is that you can create as many examples as there are documents without any human intervention, which often becomes a bottleneck problem in purely supervised machine learning system. Okay, and now I am going to do the same pipeline way of producing my summary from the Pegasus. Pipeline, to that I pass summarization. And the model in this case is called Pegasus CNN Daily Mail. Okay. Sample text. Let it start downloading. Yeah, it's a slightly larger model, 2.2 gigabytes. So it is going to take 2-3 minutes. After this was completed, just print my pipe out. And this is my summary generated from the Pegasus model. And again, the key here is summary text. So let's update my summary dict just like previously. Pipe out 0, summary text, replace, only change here I'm doing is replace this syntax with a new line syntax. Okay. Okay, so that was all the text generated from the three models. Now let's do one quick view all the generated models together by comparing different summaries. Okay, so what I'm going to do, I'm going to first print the ground truth, that is actual summary from the model, and the highlights from the, not the model, the data set, because my data set has these highlights column as well. So I'm just going to print the first highlight and then compare the summaries generated from these four models that I used here. So first print ground truth, and that would be dataset train take 1 highlights. Yeah, and then I'm going to loop through the models for actually summaries. Okay, and yeah, that should do. Cool. So what I'm getting, the first part is my ground truth, then the baseline, and the baseline summary is this. Then my GPT-2 model, the summary is this. Then T5 summary is this whole thing. Then BERT, this is a summary from BERT, and lastly Pegasus, and this is the summary from Pegasus. So basically what what you can see by just looking at the summaries, that the GPT-2 did not produce any good result at all. Instead of giving summary from the text, it summarizes, that is, a GPT-2 model summarizes the characters. Because often GPT-2 model kind of invent some facts, and that's expected, because GPT-2 specifically was never created for model summarization. It was mainly for text generation, but summarization is just kind of a byproduct of it. So GPT-2 did not produce anything good result. But otherwise, by these BART, Pegasus, and this T5 kind of produces, looks like, at least by just eyeballing, that they produces some meaningful result. But we are actually going to check it by calculating some evaluation metric on the generated text, and for that I'm going to use Sacre Bleu. That's kind of the most often used metric in text summarization task. So Sacre Bleu provides hassle-free computation of shareable, comparable, and reproducible Bleu score. First, you need to import from dataset, import load metric, and then Bleu metric is your load metric, Sacre Bleu. That is where you pass the name of the score that you want to use. So this Bleu metric object is an instance of the metric class and works like an aggregator. You can add single instances with the add method, or the whole batches via add batch method. And once you have added all the samples you need to evaluate, that is, then you can invoke your compute method and the metric will be calculated. So let's do that. Before that, I just need to import. Okay, no, I think I'm good. Dot add, that's what I'm adding. So basically, this prediction is, I just took the Pegasus prediction and for the reference is actually the human reference, because our dataset train has a highlight column, so I took the first row from there. So now that's so between these prediction and reference, now I'm going to calculate the blue metric. And just to make sure that I'm taking the correct one, yeah, so this is our original data set and I took the highlights column first value. Now I'm converting these to a pandas data frame just to represent the result properly. Okay, so that's the precision and the count and the score, all these things are showing from the blue metric. And okay, so that was blue metric, but blue metric has quite a few drawbacks, like it doesn't consider the meaning of a sentence or the similarity between sentences, etc. So that's why yeah, a slightly more advanced and a slightly better metric, which is also very popular, is Rogue, R-O-U-G-E. That's considered, and that's what we are going to implement here. So the main difference between Rogue and Blue is this: that Blue measures precision, how much the words and or the n-grams in the machine generated summaries appeared in the human reference summaries. But Rogue measures recall, that is how much the words and or n-grams in the human reference summaries appeared in the machine generated summaries. And Rogue score was specifically developed for applications like summarization, where high recall is more important than just precision. The approach is very similar to the Blue score in that we look at different n-grams and compare their occurrences in the generated text and the reference text. The difference is that with Rogue, we check how many n-grams in the reference text also occur in the generated text. For Blue, we looked at how many n-grams in the generated text appear in the reference. Okay, so for Rogue metric, I need to again get my load metric from HuggingFace. That is all that you need for defining the Rogue metric. And here another thing is that with Rogue metric is actually a series of different metrics. So I have Rogue N, Rogue L, Rogue L sum, etc. And here is a quick definition that I've given. So with Rogue N, this n represent the n-gram that we are using. For example, Rogue 1, we would be measuring the match rate of unigrams between our model output and the reference. Rogue 2 and Rogue 3 would use bigrams and trigrams respectively. Now Rogue L. So Rogue L measures the longest common subsequence between our model output and reference. All this means is that we count the longest sequence of tokens that is shared between both. And in HuggingFace datasets implementation, there are two variants of these Rogue L. So one calculates the score per sentence and averages it for the summaries, that is Rogue L. And then the other calculates it directly directly over the whole summary. That's called rogue L sum. And we are going to check rogue 1, rogue 2, rogue L, and rogue L sum for our model predictions. So what I'm going to do, first define a list like this, which has all the different metrics of rogue names. Data set. That's highlights here. I'm again running a loop for each of the model name in my summaries dict. Reference remains the same. So for rogue metric, and I have to bring in dot mid dot f measures. So the meat in rogue metric is that rogue metric in the datasets library of HuggingFace also calculates confidence interval by default the 5th and 95th percentile. The average value is stored in the attribute called mid that we just used here. And the interval can be retrieved if you want with low and high attribute. Well, I'm not going to use low and high here. I'm just using mid. And then print. Just want to check that it's printing the correct things. Recall. Okay. Summaries.case. All right, after running this cell, this is the result I get. And so this is our dict that we are printing inside the loop. So for each of my model, because here I was using 5 models, so it has printed the dict 5 times. Each of the model, I got rogue 1, rogue 2, rogue L, and so on. And finally, this is the data frame where I can see the 5 models that we used: baseline, GPT-2, T5, BERT, and Pegasus, and the various rogue measures. All right, now for the interpretation of these scores for the various rogues, these results obviously not very reliable as we only looked at a single sample. But we can compare the quality of the summary for that one example. The table confirms our observation that of the models we considered, GPT-2 kind of has has worst performance. This is not surprising since it is GPT-2 was never built really for text summarization. And on the other hand, I can see that Pegasus and BERT really scored high. So yeah, that's something to note. Pegasus especially really performed very well. And now evaluating the baseline on the test set of the CNN dataset. So I'll have a little util function for calculating this evaluation score on the baseline. Test DS. Items. And now I'm going to invoke these evaluation metric function to calculate my evaluation metric on the test dataset. But here's a quick point that I am going to use only 1000 samples from the test dataset, and that's because the test dataset consists of roughly 10,000 samples. So generating summaries for all of these articles will take a lot of time because every generated token requires a forward pass through the model. That means generating just 100 tokens for each sample will require 10,000 multiplied by 100, that is 1 million forward passes, and that's a lot of forward passes. And if we use beam search, this 1 million number will again be multiplied by the number of beams. So right now, to be able to do this in collapse session, I'm going to do it only for 1000 articles or 1000 rows. Range 1000. And rogue metric. Score Rn rogue detect, and I need to transpose it. All right. And that's the result I got, and this is for the baseline. So I got this rogue metric, the different rogue metric series, rogue 1, rogue 2, rogue L, and rogue L sum for the baseline. And next is I am going to do the same, that is calculate the rogue metric on the test dataset, but for all the other models. And for that, I am going to write another util function, because now I need to do some extra operation for calculating the rogue metric. So the strategy for right now is first we split the dataset into smaller batches that we can process simultaneously. Then for each batch we are going to tokenize the input articles and feed them to the generate function to produce the summaries using beam search. And then we use the same generation parameters as proposed in the paper, that is there will be a new parameter called length penalty, which will ensure that the model does not generate sequences that are too long. So let's just go ahead. Decoding. Oops. CUDA if torch dot CUDA batch sized generate batch sized chunks. This is the name of my util function, and that will take a list of elements and the batch size. So basically this function will only generate batches given a whole data set. So in the list of elements will just be actually the column text for the whole data set. And from that, this method is going to create chunk sized batches. So for I'm going to range over 0 and batch size. Yield list starting from I 1 plus batch size. Okay, now the next main function is to calculate the metric on the test dataset. That next function will actually calculate the rogue metric, but that function is going to use this function first to generate the batches. Calculate metric on test ds. Batch size and long list of arguments here. And the first thing I'm going to create the batch. Column, yeah. Column summary. And now inputs. All right. So now basically, given these inputs, I am going to generate the corresponding summaries. Input IDs. Attention, nice. Okay. Next one is length penalty. Okay, and here again, this length penalty parameter ensures that the model does not generate sequences that are too long. Okay, and now finally, so I have got my inputs, I've got my generated summaries, and now finally we decode the generated text. And yeah, so that would be the decoded text, decoded summaries indeed. Decode. And I need to do it for each in summaries. For S in summaries, okay. This does just as the name suggests, which is keeping special token. And the next one, another parameter I want to pass is clean up tokenization spaces. Clean up tokenization spaces equal to true. Okay, that's my decoded summaries, and in the decoded summaries I also want to replace some character. Let's see. Raise d dot so it's just an empty space. All right, now I need to restructure this function because this was the overall flow of things I want to do in this function, but I need to do that for each batches. So I have to run a loop for the batches. So let's just cut it from here and for article batch, the article batch, target batch in TQTM. I need to zip the two batches, article batches and batches. Article batches. Okay, so that's my loop, and within this I will do all these things that we just coded. Okay, here. So my decoded summaries are done here, and now after the decoded summaries are properly done, I need to do metric.add batch. Predictions. Because these decoded summaries are just the predicted summaries indeed, because they are generated from the model. And I also need to pass the actual ground truth, which is references. Target batch. Okay, so after I come out of the loop, score will be metric.compute. That's all. Yeah, that is all for this function. And then time to invoke the function or execute the function to calculate the actual metric scores on the first let's do it on Pegasus model. So for that I need to import two things from the transformer: auto model for sequence to sequence LM, because Pegasus is a sequence to sequence language model. And then I also need to define the model checkpoint. Not baseline. This will be on test, yes. Row metric. Pegas awareness. Oops. And here I'm just representing the data in a proper pandas data frame, just as we did previously. PEGA. Cool. And after some time, took quite a few minutes to run through the evaluation, and this is the score that I got for various rogue on the Pegasus model for the test dataset. And the score suggests they are not too bad. Yeah, so that's my various evaluation score on the test dataset. And remember, rogue score are more interpretable than blue score. So here for the rogue one, I got 0.434. That means that recall is equal to 43.4%, which means that 43.4% of the n-grams, in this case 1 gram, in the reference summary are also present in the generated summary. Here the reference summary means actual ground truth, that is the summary done by human, and this generated summary is the one that machines the models generated, in this case generated by Pegasus model. Alright, that pretty much wraps up this video. If you have liked this one, smash the like button. And also do subscribe, because I'm going to do many interesting NLP projects over the coming days and weeks. So, see you in the next one. Thank you very much for watching. Hey everyone, in this video I will do fine-tuning of Pegasus model for text summarization, and then apply that fine-tuned model on a famous HuggingFace dataset called SumSum dataset. Let's quickly look at the dataset here. Alright, so this is the dataset on which I will apply the fine-tuning model to do my evaluation. So just a quick look at the dataset. You can see the first column is just unique ID, then I have the actual dialogues, and then summary of the dialogues. So these dialogues, it can be some e-commerce website chat dialogue between consumers and the help desk. So that's kind of the way to make sense of this dialogue, and then the summary of the whole dialogue. And about the dataset, the SumSum dataset contains about 16,000 messenger-like conversation with the summaries. Conversations were created and written down by linguists fluent in English. Linguists were asked to create conversation similar to those they write on a daily basis, reflecting the proportion of topics of their real-life messenger conversation. The style and register are diversified. Conversation could be informal, semi-formal, or formal. They may contain slang words, emoticons, and typos. Then the conversation were annotated with summaries. It was assumed that summaries should be concise, brief of what people talked about in the conversation in third person. Yeah, so that's the point important. The SumSum dataset was prepared by Samsung Research and Development Institute, Poland, and is distributed for research purpose. Okay, so that's the fundamental of the dataset. So here, the basic purpose or the basic motivation of creating summarization of this chat conversation is that generating accurate summaries can help improve customer service and detect common patterns among customer requests. So it has quite a bit of commercial application. And so I am right in my notebook. Obviously you need GPU, so first I'm just checking with NVIDIA SMI what's the GPU I have, and I was running it in Colab, so I got a T4 with 16 GB GPU. And you need to install these transformer, sentence piece, dataset, then rogue score for calculating the evaluation metric, and obviously you have to import all these regular modules from the transformer. And then I am loading the dataset with this load dataset module of HuggingFace. These are all pretty standard and boilerplate code that you see here, right here. So I'm just defining the device, then the model checkpoint, defining the tokenizer by passing the model checkpoint, which in this case is Google, Pegasus, CNN, Daily Mail. And then I am creating my model by doing auto model for sequence to sequence LM from pretrained model checkpoint and passing that to device. Now here I have two function here, two little util methods which are important. And just before this video and the immediately preceding video I did on text summarization and evaluation metric of my generated text. So these two functions, their purpose is to calculate the evaluation metric, specifically the rogue score. So the first method is we'll just generate a batch, and then the next method, that is calculate metric on test ds, will use this first method to generate a batch and then ultimately create a score, that is a rogue score. So the strategy here is pretty simple. First, we split the data set. That is, in this method, we split the data set into smaller batches that we can process simultaneously. Then for each batch, that is, now I'm coming in this method, for each batch, because so these two lines, I'm just generating two batches, article batches and target batches. And here article means actually the whole text. In this case, you can imagine these whole actual dialogues, and the target batches are the summaries, that is this column right here. Okay, and so these two lines will just create two batches, and then I am going through batch by batch, that is, I'm looping over the batch and creating my tokenizer. That is inputs equal to tokenizer, and passing the article batch and the other parameters like max length, truncation, padding, etc. Creating summaries. So these summaries is actually the model generated summaries, because I'm doing model.generate and passing input IDs. From there, I'm taking inputs, input IDs. And so we use the same generation parameter as was proposed in the original paper, and then you will see a particular penalty here I'm doing while generating the summary, length penalty. So this what this penalty does is that it will apply a penalty to ensure that the model does not generate sequences that are too long. And ultimately, from these second method, calculate metric on test dataset, ultimately I will, so basically I am creating inputs, tokenizer, I am generating summaries, and I am then decoding the summaries, and then I'm applying the metric.add batch. I'm applying this metric from HuggingFace to generate my rogue score by comparing the predictions and the reference. So the prediction is my generated summaries, and the references are actual summaries. And then in this cell, all I'm doing, I'm just printing an actual dialogue, an actual summary. So you can see that, and I'm doing both of these on the test dataset. So first I'm printing from dataset Samsung test and 0, that is the very first dialogue, and also the very first summary. So this is how the dialogue goes. You can see that two people are talking, Hannah and Amanda. So Hannah is asking, hey, do you have Betty's number? Amanda says, let me check. Then Amanda says that, sorry, she doesn't have the number. And ultimately, Amanda advising Hannah to check with another person for the number. And the summary very succinctly creates a single sentence for the whole conversation, and it says Hannah needs Betty's number, but Amanda does not have it. She needs to contact Larry. So this is exactly and very correctly the summary of this whole conversation, and that's my actual real summary from the dataset. And now the job of this fine-tuning is to train my Pegasus model and create this summary from my trained or fine-tuned model. Alright, that was enough of the initial starting of the project, and now just keeping my head down and coding the fine-tuning of Pegasus. So I'm using pipeline of HuggingFace to create this summarization. First, we will run the summarization pipeline with Pegasus to see what the output looks like. So pipe out. Data set. Quickly check, that's the name of the name of the column here. Pipe out. Let's just print pipe out and see what I get. So when you print pipe out, this is the output that you will get. You get a list, and the list contains a dictionary, and that has a key of summary text and then the whole text. And there are quite a few of these this particular token over here. So I need to replace this with just a new line character. So let's go to my VS Code. So what I'm going to do, actually just proceed to calculate my rogue score for now. No, actually just let's just remove these, replace this with new line character and see my summary text in a very clean format so that I can make sense. Yeah. So when I print pipe out the 0th element, that is this whole dictionary, and then take the summary text, replace these character with new line, I get a finely formatted conversation like this: Amanda, Hannah, Amanda. Yeah, that looks good. And now I will move to calculate my rogue metric. So I'm just calculating rogue 1, rogue 2, rogue L, and rogue L sum. And what are they? I have already discussed in my immediately preceding video, where the focus was on to understand the evaluation. The focus was on generating summaries from a long text, and then doing all this evaluation metric and what these different rogue scores represent, etc. So if you have not already, do see the previous immediately preceding video, and then these will be much clearer. All right, I need to define rogue metric. Data set. Rogue metric. And column summary would be and then if measure for Rn so this will loop through all my rogue names. That is, I want to on these four different rogue metrics, and then take the mid.f measure and produce a dictionary out of that. And I just want to print this in a nice speed pandas data frame. Rotate. Pegasus. Okay. And next, what I want to do is actually, all right, but before proceeding, this is the pandas data frame with the row score. And as you can see, these scores are actually quite low. They are not good at all. And that's expected because these Pegasus model that I'm using, that's not properly trained for this particular Samsung dataset. And that's the whole purpose of this exercise right now, that I am going to fine tune this Pegasus model further for this data set so that the row score becomes much more sensible and much more accurate. And so that's the whole reason that I printed this row score before fine-tuning the model at all, so that I could see that these scores are really bad before fine-tuning. And next, I just want to create a histogram of the length of my dialogues and the summaries. So I need to plot a histogram, and the reason that I am doing this is just to check that what is the average kind of length of the token for dialogue and summary, and what is the maximum what is the range of token length where the maximum occurrences are happening for both the dialogue and summaries. For this, first I need to calculate the dialogue token length. So DIALO, that would be len of tokenizer train LOGUE. LOGUE, yeah. And I need to do the same for the summary. Summary. Define a subplot. Subplots. One row, two columns. That's how I want it. SHAREY, that's the one I want to choose. Give it say 0. And a few other things I need to set, like title, X label, Y label. Okay. And oh, I did not set these X is 0 haste, the most important line. So the first plot is about dialogue token length. Beans of 20. Edge color. And I also need to do the similar thing for the summary. That's axis 1, histogram summary. The rest of the things remain same, and here as well I need to do this. Okay, and when I run this, this is the output I get. And so looking at this plot, we can see that most dialogues are much shorter, relatively shorter actually, with 100 to 200 tokens per dialogue. Similarly, the summaries are shorter as well, with around 20 to 40 tokens, the average length of probably a tweet. So let's keep this observation in mind, because now when I define my training configuration, these numbers will be important, because here I can see that probably there is no more data after like 700 length. So while configuring my model training for fine tuning, the maximum length I will set at 1024 for the dialogues and 128 for the summaries. And now I'm going to write a little util function for converting the examples to features. So this function will return me the input IDs, attention, mask, and labels as a dict. Get the input encodings just by implementing or invoking tokenizer that I pass the actual text of the dialogues. DIALOGUE. Yeah. With okay, now I'm going to define a context manager, and I will talk about this particular context manager that here I'm going to use in a second, but let's just complete the code. And this context manager is tokenizer as target tokenizer. Tokenizer dot and this context manager is only for getting the target encodings. Because now I'm concerned about the target, that means I need to capture the summary column. Maximum length, as we discussed, I will set it to 128, and okay, now just return a dict which will have input IDs, encodings, and then inside I should have okay. Now I also need attention mask. And the last one is labels. Now I'm going to, the function is over. I'm just invoking this function now. So let's define the result of invocation of the function as data set sumsum pt, which will be equal to And now coming back to these context manager as target tokenizer. So this temporarily sets the tokenizer for encoding the targets. It's useful for tokenizer associated with sequence to sequence models that needs a slightly different processing for the labels. The as target tokenizer method is specifically for sequence to sequence model in order to separate between the source and target tokenizers. You don't need it for other kind of models, like not needed for Roberta. It just doesn't do anything for models that are not sequence to sequence. So with this tokenizer as target tokenizer, I am pretty much setting the context here because some models require special tokens in the decoder inputs. So it's important to differentiate between the tokenization of encoder and decoder inputs. In the with statement, that is a context manager, the tokenizer knows that it is tokenizing for the decoder and can process sequences accordingly. So that's very much the reason for using this context manager. And now I am going to define the data collator. So I'm just importing the data collator for sequence to sequence in the first line, and then invoking that class by and creating an instance of this class by passing tokenizer and model to my data collator. Now, what is a data collator? It's just data collators are just objects that will form a batch by using a list of dataset elements as input. These elements are of the same type as elements of train dataset or eval dataset. And in order to be ready to build batches, this data collator info classifier may apply some processing such as padding, or for some data collator also actually apply some random data enhancement as well on formed batches. And now finally my training configuration for the fine-tuning. So I'm just going to import the training argument and the trainer class, and then define all the configuration. Training args, training arguments. So here my configuration that I'm going to pass are quite a few. They are this: output dir, number of train epochs, warm-up steps, per device train batch size, per device eval batch size, wet decay, logging steps, push to hub true, evaluation strategy. Remember, push to hub true. If you do not want to push to hub true, you can just omit it. Something like this. Evaluation strategy is steps, evaluation steps, save steps, and finally gradient accumulation steps. And after this, you just have to invoke the trainer class. There as well, I need to provide all the arguments. So these are my arguments: model, args, tokenizer, data collator, train dataset, and eval dataset. Okay. And after this, just run your training. Trainer.train. Okay. And after the training, I also need to get my score. So I'm going to use the very first function we defined, which is calculate metric on test DS. And that takes dataset. Because I'm calculating the metrics on the evaluation dataset, that is test dataset. And also I'm going to use rogue metric to be returned from this function. Model, tokenizer, maybe just 2. Dialog column summary will be summary. RN, and then I need to get the score. So these meet.f measures, these we have already discussed in my immediately preceding video, which was initial video on text summarization and doing basic evaluation by measuring the rogue score for 3 different models, that is Pegasus, GPT-2, and BERT. So you can, if you have not seen that video, do watch that one first, because that will clear some of this concept here, that how these scores are calculated, what this rogue score means, the interpretation of rogue score, etc. Rogue names. Syntactical mistake here? No, it's all right. Yeah. And lastly, I just want to represent this rogued dictionary in a pandas data frame properly. So pandas t rogue date Pegasus Pegasus. And finally, when my training is over, this is the rogue score I got. That is rogue 1, rogue 2, rogue L, and rogue L sum for my fine-tuned Pegasus model. And as we can see now that these scores has improved quite a lot from before the fine-tuning. So before the fine-tuning, because Pegasus is not really suited for the Samsung dataset that we are using, so the rogue score was really bad when we calculated the rogue scores on the test dataset. But after the fine-tuning of the model, when I calculated the rogue scores, it has really improved substantially, and that's the very purpose of doing my fine-tuning. But before moving forward, a quick word on these particular parameter in my training arguments, which is gradient accumulation steps, and I'm setting it at 16. So since this model is quite big, I had to set the batch size to 1. That is, both my per device eval batch size and per device train batch size are set to 1. However, a batch size that is so small like 1 can hurt convergence. To resolve that issue, we can use a nifty technique which is called gradient accumulation, and that's what this argument is all about. So as the name suggests, instead of calculating the gradients of the full batch all at once, we make smaller batches and aggregate the gradients. When we have aggregated enough gradients, we run the optimization step. Naturally, this is a bit slower than doing it in one pass, but it will save you a lot of GPU memory, and that you will quickly see it's a super important parameter while deciding your training parameters. Alright, so finally I am ready to test the fine-tuned model on the test dataset. So here's that code. Basically what I'm doing, I'm just first with this line I am defining the keywords for the fine-tuned model, and their length penalty, number of beams, max length, and then this is my actual sample text from the dataset. This is the actual reference from the dataset again, and as you can see, what I'm doing is I'm picking the test dataset, taking the first row, that is the first element or the first input value among the many, and taking the dialog columns value. That's my sample text. Similarly, for the reference, I'm doing exactly the same, that is taking the first row only from the test dataset and only the summary columns values. All right. And then with the pipeline, I am just defining this little pipeline over here, because this is a summarization task. I need to give the summarization as a first argument to pipeline, and the model, I have to define the model that I'm using. And then that's pretty much it. And all I'm doing in the next couple of lines, first I'm printing the actual dialog, then I'm printing the actual reference summary, and finally with the pipe method, I am printing the model generated summary. That is all. And for generating the model generated summary, all you have to do is to the pipe, you pass your sample text, you pass your generated keywords, then take the 0th element and summary text. Okay, let's see the result. Okay, here is the output of that code. So first, this whole thing is obviously the actual dialogue from the dataset, and this is the reference summary of this whole dialogue, but this summary was the actual one that was already given in the dataset, and it was written by human. And then finally, the most important part, the reason that we fine-tune the model is this one. So this is the model generated summary of this whole conversation. Okay, and let's see the difference. So the reference summary says Hannah needs Betty's number, but Amanda doesn't have it. She needs to contact Larry. And the model generated summary is Amanda can't find Betty's number. Larry called Betty last time they were at the park together. Hannah wants Amanda to text Larry's instead of calling Betty. Beautiful. This is absolutely beautiful. So these 3 lines pretty much summarizes exactly what happened in these dialogue. And that's our fine-tuned Pegasus models generated result. Alright, that pretty much wraps up this video. If you have liked this one, smash the like button. And also do subscribe, because I'm going to do many interesting NLP projects over the coming days and weeks. So see you in the next one. Thank you very much for watching. This video is a quick summary and discussion about this paper, BERTScore, Evaluating Text Generation with BERT. So, BERTScore is an automatic evaluation metric used for testing the goodness of text generation system. Unlike the existing popular methods like Rogue and Blue that compute token-level syntactical similarity, BERTScore focuses on computing semantic similarity between tokens of reference and hypothesis. The authors of the paper tested it on machine translation and image captioning tasks and found it correlated better with human judgments. So generally, the machine translation evaluation is itself a surprisingly difficult task. The reason is that we are not able to explicitly algorithmically check if 2 sentences carry the same meaning in all relevant aspects. We know, or at least assume, that people can do this assessment even though they don't know how to do it. We just treat the whole machine translation as a kind of behaviorist simulation and ground the metrics that we use for machine translation evaluation in human judgment by measuring the correlation of the metrics with human judgment. So in the BERTScore, one of the key starting point is that getting the BERT representation for the translation hypothesis and the reference hypothesis, and the authors mentioned it very succinctly here in this. That is a token representation. So what they're saying is that we use contextual embeddings to represent the tokens in the input sentence X and X bar. In contrast to prior word embeddings, contextual embeddings such as BERT and Elmo can generate different vector representation for the same word in different sentences depending on the surrounding words, which form the context of the target words. And this is the image representing the architecture of this BERTScore method. So basically the steps are like this: that get the BERT representation for the translation hypothesis and the reference text. Then number 2 is compute a matrix of cosine similarities of all words from the hypothesis and from the reference sentence. Number 3, for each word from the hypothesis, find the most similar word from the reference and compute the average of the maxima over the hypothesis words. This number tells us how much on average each word was matched with a word in the reference. So in the paper they call this precision, and then we do the same with swapped hypothesis and reference and compute the recall, and finally compute the F1 score, which is the harmonic average of precision and recall. And as to the achievements of this paper, the results are most interesting in the evaluation of isolated sentence pairs. The correlation with human judgment is around 0.5 with most of the currently used metrics, but with BERTScore, this correlation with human judgment goes up to 0.7. Now, the more significant fact for achieving the 0.7 correlation with human evaluation is that recently there are many evaluation metrics that achieved high correlation with human, which are based on supervised learning from previous manual evaluations. This makes these matrices dependent on how the machine translation outputs look like these days and pose a risk that they won't work well with newer machine translation systems in future. But BERTScore is independent of how the system outputs currently look like, which makes it more robust for future as well. Another important factor in this paper that was proposed is the author of this paper also introduced the notion of weights for each word similarity calculation. So here is what they are explaining, that previous work on similarity measures demonstrated that rare words can be more indicative for sentence similarity than common words. And BERTScore enables us to easily incorporate importance weighting. So they stick with IDF, that is inverse document frequency weights, which they derive based on a large amount of offline text data. So if a word has a very high IDF weight, then this is not a very common word that is used across multiple documents. So it might be something worth for you to compare it against while doing the similarity calculation, unlike words with low IDF. That is, low IDF represents common words mostly. So this weighting is an important part for calculating the similarity matrix, and which was nicely implemented in this paper. Alright, I'm coming back to this image again because this image very much represents the whole paper in a nutshell. So here what's happening is that we take both reference, that is a ground truth, and candidate, that is generated once, and pass them through the pre-trained BERT model to generate contextual embedding for each word at the output end. Once we have the final embeddings for each of these words, we do n-squared computation by calculating similarity for each of the words from reference to each of the words in the candidate. We find and pick most similar words from reference to the candidate 1 and calculate precision, recall, and F1 score among them. So overall, the improvement that was mainly achieved in BERTScore compared to the traditional approaches like BlueScore is that in BlueScore, the n-gram approaches do not capture the positioning and the context of the word and simply rely on exact matching for evaluation. But in BERTScore, this computes the similarity using contextual token embeddings. So it helps in detecting semantically correct paraphrased sentences. And it also captures a cause and effect relationship that the BlueScore cannot detect. And for the actual implementation of BERTScore, it's already there in the HuggingFace metric module. So currently I'm looking at the official doc of HuggingFace. So as I say, how to use BERTScore takes 3 mandatory arguments: predictions, reference, and either lang, a string of 2 letters indicating the language of the sentences, or model type. And this is an example code here. You just import from evaluate import load, and then BERTScore is just load BERTScore. That's all. And then you pass these 2 sentences, prediction and the reference, and the actual results of the score is BERTScore.compute. Predictions, you pass the reference and pass a language. Here, for example, they are passing EN for English. And yeah, so output values, BERTScore outputs a dictionary with the following values: precision, the precision for each sentences from the prediction plus reference list, which ranges from 0 to 1. Then recall for each sentence from the prediction plus reference list, which ranges from 0 to 1. And finally, the F1 score for each sentences from prediction and reference. Alright, that pretty much wraps up this video. If you have liked this one, smash the like button. And also do subscribe, because I'm going to do many interesting NLP projects over the coming days and weeks. So, see you in the next one. Thank you very much for watching. Hey everyone, in this video I will do token classification by fine-tuning a BERT model, and for the model I will choose these BERT base uncased. This is like one of the most popular model in the HuggingFace repository with the download last month of 33 million. And then I will apply this fine-tuned model to predict my tokens, that is NER tokens, that is named entity recognition tokens on these dataset, ConLL 2003. So this dataset is the summary of this dataset is written right here. The shared task of ConLL 2003 concerns language independent named entity recognition. We will concentrate on 4 types of named entities: person, location, organizations, and names of miscellaneous entities that do not belong to the previous 3 groups. Shared task data files contain 4 columns separated by single space. Each word has been put on a separate line, and there is an empty line after each sentence. So let's look at the dataset right here. So this is the train part. I have 4 columns: NER, post tags, chunk tags, and NER tags. And these are the tokens. And then I have a POS tags, that is positional tags, then chunk tags and NER tags. So what is a token classification task? This generic task encompasses any problem that can be formulated as attributing a label to each token in a sentence, such as named entity recognition or NER, where we find the entities such as persons, locations, or organization in a sentence. This can be formulated as attributing a label to each token by having 1 class per entity and 1 class for no entity. Then I have POS, that is parts of speech tagging, where we mark each word in a sentence as corresponding to a particular parts of speech, such as noun, verb, adjective, etc. And lastly, chunking, where we find the tokens that belong to the same entity. This task, that is chunking, can be formulated as attributing 1 label to any token that are at the beginning of a chunk, which are called B dash, that is beginning of the chunk. Then attributing another label to tokens that are inside the chunk, which is attributed as I dash, and then a third label, which is O, to represent tokens that don't belong to any chunk. And here are the main tokens, the way it is represented. O means a word does not correspond to any entity. B PER or IPER means word correspond to the beginning of or is inside a person entity. B-org or I-org means a word corresponds to the beginning of or is inside an organization entity. Then I have B location or I location, just similarly like the previous one. And then B miscellaneous and I miscellaneous means a word correspond to the beginning or is inside a miscellaneous entity. All right, with that introduction, let's start the actual coding for these fine-tuning tasks that will be the subject of this video. So initially you have to install all these libraries: pip install transformers, datasets, tokenizer, seq-eval, and these are just regular libraries that you have to definitely install for any Hugging Face related or transformer related project. All right, and then I need to import all these libraries, that is dataset, numpy, then the relevant modules from transformers. So here I'm importing BERT tokenizer, data collator for token classification, and auto model for token classification. And the dataset we are using is ConLL 2003, and that's why I'm doing datasets.load dataset. And then here I'm just printing the dataset, and this is Hugging Face dataset dict. So this is the structure it follows. So I have 3 segments: train, validation, test, and within each segment I have the features, which are ID, which is a unique ID, and then 4 feature columns, actually: tokens, pause tags, chunk tags, NER tags. And for the number of rows, I have 14,042 for train, 3251 for validation, 3454 for test dataset. And if I print shape, that's how it will be printed. And that is, you will see the exact shape that it has. All right, now I'm going to print an actual train element. 2003. Yeah. I'm taking it from the train. And that is the actual element. And if you compare it with the actual dataset, you can see it matches exactly. So the ID is 0, which is what you got, 0. Then for the tokens, you reject pause tags, chunk tags, NER tags. And that's exactly what we got. So this actually prints the first row of the data set. Okay, now what I'm going to do, just print the in-year tags. So features in-year tags. So that's how you will get the feature names. I have names as 0, B person, I person, B org, etc. From the dataset, you can also get some metadata. So you can do something like this: description, and that will give you the entire description that you saw in the HuggingFace data official page. The shared task of CONL 2003 concerns language independent named entity recognition. So that's exactly what we saw in the official page. Yeah, so now I think that's enough about the introduction of the data. Now let's define my tokenizer. BERT tokenizer fast, that's what we imported. And now we will apply this tokenizer to tokenize an example input from the dataset and see a particular problem which we need to solve before proceeding the fine-tuning model building. So I'm just tracking the first row's value from the trained dataset, and the tokenized input will be tokenizer. To that I have to pass example text and tokens. Words equal to true. And here again, I took the tokens because that's the column name of our dataset. As you can see right here, this is the con LL 2003 dataset, and token is the column name that I'm interested in. And the tokens will be tokenized input. Actually, no, tokenizer dot convert IDs to token. Tokenized input IDS. I also need the word IDS. Now let's print the length of the example text in-year tags and the tokenized input IDs. So what I mean is, let's run this cell first. Okay, let's print this right, and also I just want to print the length of the in-year tags in my example text and the length of the tokenized input IDs. And as you see the problem here, and the problem is that and this is called the problem of subtoken. So the input IDs returned by the tokenizer are longer, that is 11, length is 11, versus the labels that our dataset contains. And our dataset contained the in-year tags of only 9 of them. And why it is happening, to understand that, you need to understand first that the transformers are often pre-trained with subword tokenizers, meaning that even if your inputs have been split into words already, each of those words could be split again by the tokenizer. This means that we need to do some processing on our labels because the input IDs returned by the tokenizer are longer than the list of labels our dataset contain. And this is mainly happening because because some special tokens might be added, for example CLS and separator token, and then because of possible splits of words into multiple tokens. Now, to align these, to resolve this problem, we need to depend on these word ID methods. And we can see the output of this word ID is that it outputs a whole list, and all these elements, that is which are not none, that is the same number of elements as our processed input IDs. But then the special tokens, that is at the beginning probably it's a CLS token and at the end it's probably a separator token, the special tokens are mapped to none. And based on this output of word ID methods, I am going to resolve this. And in the HuggingFace official documentation also, they propose a similar kind of solution to resolve the situation of special token being mapped to none. And the strategy for the solution is like this, that here we are going to set the labels of all special tokens, that is which are mapped to none, to -100, because the -100 is the index that is ignored by PyTorch during training. And the labels of all other tokens we will be mapping to the label of the word they come from. And so that's pretty much the strategy I will follow in my next method. So this function method name is tokenize and align labels, and this function mainly will have two jobs, that is set -100 as a label for those special tokens, and then number two job is mask the subword representation after the first subword, and then we align the labels with the token IDs using the strategy we just talked about. So this method will take my example, which is a dataset, and another Boolean argument. Tokens. Again, I'm choosing tokens here because that's what our dataset has. True, and is splitting towards true as well. Yeah, so that's my tokenized input. Okay, I just forgot to mention another thing when I was explaining this problem here, that the problem we are trying to solve here, which is the input IDs returned by the tokenizer are longer than the list of labels our dataset contains, which is this. Our list of labels the dataset contains is 9, but the input IDs returned by the tokenized input is 11, and that's a problem we are trying to solve with this method. Now, before, if you want to see that why these 9 became 11, how these special tokens got added, which we saw that special tokens are mapped to none here when we are printing these word IDs, but to see the actual tokens, you need to see these output of this tokens variable, because that's why I defined this tokens variable, and you can get the tokens by applying this method convert IDs to tokens on the tokenizer, and that's what I did in the tokens variable. I'm just running it here again and printing my token. Yeah, so that's the reason I got 11. So you see that all these inside they are number 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. And that's the number of NER tags we have in this particular data element. But two special token, they have been added at the beginning and at the end. The CLS token for the classifier and the separator token. And these tokens are what? Mapped to the word or string none, which we see when we print the output of word IDs. So tokenized input dot word IDs will just print the these actual classes of the tokens, and that's a problem. That's why we got 11 for the length of the tokenized input IDs, but the original dataset contain only 9. And that's the problem we are trying to solve here in this method right here. Labels will be a new just a new list that will hold the labels later. And now I start the looping. Any tags, because that's the column name that the original dataset has, and that's what I am looping over. So here word IDs comes to rescue. The word IDs method in tokenized inputs. So my word IDs will be equal to batch index equal to I. So what this is doing is that word IDs will return a list of mapping the tokens and list of mapping the tokens to their actual word in the initial sentence. And it returns a list indicating the word corresponding to each token. And now I start my second loop. X over word IDs. So we have already seen the word IDs output will be something like this: none, 0, 1, 2, 3, 4, 5, 6, 7, 8, none. So this word IDs is just a list mapping the tokens to their actual word in the initial sentence, and that's what I'm looping over. And if word ID X is none, then set -100 as a label for these special tokens. Sorry, 1 second. And why -100? That's because, again, this will be ignored by PyTorch during the training. Label IDs dot append. Okay, and now if that is not the case, elif X is not equal to previous word index. That is, if the current word index is not equal to the previous word, then it's a most regular case, that is. And in that case, I'm just going to add the corresponding token of the word as it is. Label IDs dot append label and word IDX. Why I'm getting label IDs is not defined, but oh yeah, so yeah, okay. And so two conditions are taken care of. I just have a last condition that is to take care of. So the last condition is for the subwords case. So we will see what it does. So this is to take care of the subwords which have the same word index. In that case, set it to -100 as well for them, but only if label all tokens, this argument is false. Otherwise, set it as it is. So in this case, label IDs x else minus 100. Cool. And after these loops, I have to update my previous word index to make it equal to word in idx. Okay, come out of the loop, labels dot append, tokenized. So I'm just for the tokenized input, I'm creating a new key now, which is labels. Cool. And now I'm going to invoke this method. Why these extra spaces? Yeah. Tokenize. Train, I'm just taking from 4 to 5. Trained here. Okay. Let's run from here. Cool. So this is output from the tokenized and aligned labels. So now just note one thing here, that if I printed the tokenized input variable before applying this method, then this dictionary will have only 3 keys, that is input IDs, then I will have token type IDs, and then attention mask. But after this method, a new key has been added in this line here, which is labels, and that's a new key that has been added to the tokenized input variable after the method, and that's the key whose values are properly aligned. All right, because we can see these 100 minus 100 has been added here for all the special tokens. Now let's print some of the tokens and labels to see them side by side. So I'm going to loop over tokenizer, Q, and a 0, Q, labels 0. Token. And also the label. What happened? Let me fix. Yeah. So here we can see the actual tokens and their corresponding labels. So CLS has minus 100, separator has minus 100. That's exactly what I wanted. All right. Tokenized data set now will be so. Let's apply that method across the ConLL 2003 with the map function. It's a pretty powerful and pretty useful function from HuggingFace, where I can apply a particular method across all the input, all the elements, all the individual rows in a single line. Okay, and line labels. Cool. Now let's define my model. Auto model for token classification from pretrained BERT base on. Okay. Because we have 9 classes, so num labels equal to 9. Let it run. It may take a minute or so. Yeah. Cool. Okay. Now I need to define the training argument parameters. Transformers, import training arguments. Training arguments. And they are my training arguments. Let's run this cell. Okay, I also need to define the data collator. For token classification and pass tokenizer. So these data collators are objects that will form a batch by using a list of dataset elements as input. These elements are of the same type as the elements of trained dataset and eval dataset. And to be able to build batches, data collator may apply some processing like padding. Some of them, like some of the data collators, like data collator for language modeling, also apply some random data augmentation on the formed batch. So data collator actually automatically pads the model inputs in a batch to the length of the longest example. These bypass the need to set a global maximum sequence length, and in practice leads to faster training since we perform fewer redundant computations on the padded tokens and attention mask. My metric is seqeval, seqeval. Features and take the linear tags. Let's run it. Feature names, that would be, that's just feature.names, I think. Yeah, these are my feature names, okay? And now calculate these metric on a single example, and that example will be just this one. That is the very first element from the data set. And for that, what I need to do, I need to get the labels from that example. That is, label means the NER tags as a list. Label list I. Example NER tags. Yeah, so in the first example, I have these named entity recognition tags, that is B organization, O, B miscellaneous, etc. Now let's calculate the metric. Metric.compute. I'm passing the same labels to predictions and reference. and that's how you will get your result of the metric. And here I got the precision 1, recall 1, all these. The very ideal score is because I passed the same list to both my prediction and reference. But anyway, this was just for checking that metric.compute is working, and now I am going to define the actual compute metrics method, which will be passed to my training configuration. So the prediction logics will just be obtained by applying numpy.argmax, because the logics and the probabilities both are in the same order, so we do not need to apply softmax here, just the argmax. Right, logics across the axis of 2. And now I need to remove all values where the label is -100. Predictions. So before passing to the metric.compute, just as we saw here, I need to pass a list to both the predictions and the reference. To both this argument, I need to pass a list, and that's why here right now I'm going to do is create my predictions list and also the true labels list to be passed to the reference. Okay, now that will be prediction label list heads for zipping of my prediction label if L is not equal to -100. Okay. Prediction label in zip, that would be between pred logics and similarly true labels. Yeah, so this will be, I have to get my list element from the true labels. That means label list here, instead of eval preds this L for eval preds L and zipping of prediction and labels. So this label is my true label. So it's coming, this label is coming from these labels variables actually, what we defined here, and we will see that in a second for the next zip. If L right, prediction zip let's name it predictions. Reference is and from this I'm just going to return a dict taking the various key values from my result, and that will be just this. Cool, that should work. And now I need to define my training configurations again in the next cells. So trainer equal to model, args, training dataset is tokenized dataset, train, tokenized dataset validation. So everything is defined. I can actually train my model right now. That is going to take quite a bit of time. I mean, if you are running in Colab with GPU, it should not take more than maybe 6-7 minutes. I also need to write the code for saving the model. Save, pretrained. Tokenizer. Okay. And also need to define two variables here for converting my ID to label and label to ID. stri. That's my key here, and label list. Similarly for label to ID. For I, label in enumerate label list. Cool. And config. Sorry, import. NER model, because that's my model name. Just loading the config after the training. Remember this NER model here by this line, it's completely pre-trained, this NER model here is completely fine-tuned, because we started with the pre-trained model from HuggingFace, and then we trained it right here with this line, and after defining all the training configuration. So at this model, this NER model is coming from this model.safe pre-trained, this line. So at this point, this is a completely fine-tuned model. And why I'm doing this? Because I'm going to test my fine-tuned model on evaluation text, that whether that creates a proper kind of NER tags. Okay, and here config ID 2. That will be my ID to label. Similarly, config label to ID. These are all standard code. If you follow HuggingFace tutorial and their documentation, these are very much well written over there. Config.json w. Now load my pre-trained, fine-tuned model. So let's name it model fine-tuned. Auto model for token classification. Model. Okay. And so this is the output that you get for your this model fine-tuned. Okay, so model config, BERT config, name or path NER model, architecture BERT for token classification, attention prob, dropout prob, all these ID to labels are given here properly. Okay, so that's our fine-tuned model. And now I'm going to test this model on a example text. And there I have. First, I just imported pipeline so that I can use this pipeline method for getting the inference from my model. And then I'm just defining pipeline, passing NER for telling the pipeline that I'm trying to do named entity recognition. And for the model argument, I pass my model fine-tuned, which is my fine-tuned model. Tokenizer remains tokenizer. And for this is example text. Bill Gates is a founder of Microsoft. And all I do is NER result equal to NLP. And within that, I pass the example text, and this is my NER result, that is the inferencing from my fine-tuned model. And look at that, this first Bill Gates, it's obviously B person. A model has correctly predicted score with a score of 0.99, that is with a very, very high probability. Then word Bill, entity I person. Okay, so the first one was Bill, and that's this one, and the second one was this, and that's the word gets, and that's also I person. The next word is Microsoft, and that also it has correctly identified as beginning of organization with a very high score. So looks like this inferencing, this was a very baseline inferencing. I just ran the training for 4 epochs and it produced a very good result indeed. Alright, that pretty much wraps up this video. If you have liked this one, smash the like button. And also do subscribe, because I'm going to do many interesting NLP projects over the coming days and weeks. So see you in the next one. Thank you very much for watching. Hey everyone, in this video I will do fine-tuning of DistilBERT for multi-class text classification, and the dataset I will choose for this one is called BBC text. We will see the dataset shape and the contents of the dataset in a second, and I'm giving the link of the dataset over here, and obviously the notebook link, that is a GitHub link, will be given in the description of this video. And as expected, you need to first install transformer package for pretty much all HuggingFace project, and then you need to import the relevant modules. So here, because I'm doing this whole project with TensorFlow, so and also using DistilBERT model, so if there are some classes that you need to import, which are DistilBERT tokenizer, then TF DistilBERT for sequence classification, and also text classification pipeline, because at the end during the inferencing I'm going to use this pipeline methodology. And the rest of the modules is pretty much standard: TensorFlow, Pandas, NLTK, and Seaborn, Matplotlib, etc. Let's first read the dataset. So I have already, from this link, I have already downloaded the dataset into my local machine, and this is the dataset when I'm just doing pd.read.csv and then just printing the head. So the dataset is pretty simple. It has got only 2 text columns. One is the actual text of the news, that is it's BBC News, and the category represent the main topic of that news, that is a whole text. For example, the first whole text of the first row, the main topic is technology, and then for the next one the main topic is business, and so on. And let's check out the shape of the data set. Yeah, so we have got 2225 number of rows and 2 columns. Okay, the first thing I will do is quickly plot a histogram to see the count of the text. Eight and 8. Oh, I think I need to first include another code, another lines of code to get the count of each of the text. Let's do that. Yeah, that should give me the count. Let's run this cell. And also now check. Yeah, now I have a count of the text. Okay. And yeah, so now I can plot the counts. Yeah, that was just count. I also need plt.title and plt.show. Okay, so that's my dist plot, the number of words of the distribution, and below we see the number of words. So we can see that most of the words are concentrated towards, most of the numbers in a particular text is concentrated towards these, like for example maybe 150 up to all the way up to maybe 500. Okay, so it's a good news for our BERT modeling, because DistilBERT can tokenize up to 512. That is the max length of token acceptable by DistilBERT is 512. Okay, next one I want to do is do a bar plot of each of the news category. Okay, so category, count dot index. Let's see, category. All right, so these are my categories: sport, business, politics, tech, entertainment, 5 of them. And yeah, now let's plot bar plot. Add subplots. On the X, I want to show the category counts. And what is our category count? Let's quickly see what this. Yes, so this is this little thing: sports, business, politics. Okay, we got this from category count.index. Yeah, so on the X, my category count dot index, and on the Y, and then I just want to for the plotting, I want to annotate the plot a little bit. So you can go, I'm just enumerating through ax.patches, and then adjusting the heights with getX, and then getWidth and getHeight with all these methods. You can just go through the plotting methodologies and official documentation of SNS or Matplotlib to understand this. And then I just need to add the X level, Y level. Let's run this. Cool. So that's my plotting. So yeah, so it's pretty balanced data set, because pretty much all the categories are well represented in the overall scheme of things. Okay, now I need to get DF. Quickly check one thing. Category. Actually, it will print the same thing, that is all the names of the category columns, unique values. And then create now I need to create new column and encode the category labels. Because these categories are text, we cannot feed them into the model. Any machine learning model will not take text directly. We have to somehow encode them and get the numbers. So what I'll do is I am going to make use of cat.codes. Let's see, df new column name is encoded text. As type category. Now cat.codes. Cool. So now all my text have been encoded with these 5 unique numbers, because I have 5 categories. So the encoded text here also represent 5 unique numbers, 0, 1, 2, 3, 4. To understand how that cat.codes work, you can check out the categorical data official page in Pandas documentation, and here they say that all values of categorical data are either categories or np.nan. Internally, the data structure consists of categories array and an integer array of codes which point to the real value in the categories array. So this is what I accessed in this line and set that cat.codes to be my new column encoded text. Okay. And now another thing I need to quickly do, which is data feature list, and also encoded cat to list. Okay. Sorry, the new column name I said encoded text, so that would be encoded text. Okay. And so this is just a list of values that I created or extracted from the data frame. You can just quickly print my data labels. Yeah, so this is just a whole list of values. That is all. And note that these data text still has to be converted or converted to a tokenized vectors before we can use the machine learning model. And we will do that in a second. But before this, let's do another thing, which is very important: train test split. So that's a train and validation text. Now I also want to keep some data for the inference for testing. So I'm going to split the train part again. Actually put S to all of this. keep 10% of the data from my this train text portion as a validation or evaluation set. So 0.0 actually keep it 0.01, very small percentage, because here the total number of data rows are not too big. We have like 2400 or so, so I'm not wasting too much of data into the test part. All right, now model definition. And for our model choice, we are going to use DistilBERT base uncast. And since we want to use DistilBERT for classification task, we will use DistilBERT tokenizer for the tokenizer class to tokenize our text, and then use TF DistilBERT for sequence classification class in the next cell for the pre-training of the model. And if you want to check out the HuggingFace official documentation for DistilBERT, that's where it is. So what they're saying is this model is distilled version of the BERT base model. It was introduced in this paper. The code for the DistilBERT process can be found here. Okay, so for the model description, DistilBERT is a transformer model smaller and faster than BERT, which was pre-trained on the same corpus in a self-supervised fashion using the BERT base model as a teacher. This means it was pre-trained on the raw text only with no human labeling them in any way, which is why it can use lots of publicly available data with an automatic process to generate inputs and labels from those text using the BERT base model. And more precisely, it was pre-trained with 3 objectives: distillation loss, masked language modeling, and cosine embedding loss. So the distillation loss is a model was trained to return the same probabilities as a BERT model. Anyway, so intended use and limitation: you can use a raw model for either masked language modeling or next sentence prediction, but it's mostly intended to be fine-tuned on a downstream task. That's what we are going to do. We are going to fine-tune it for a downstream task. And note that this model is primarily aimed at being fine-tuned on tasks such as whole sentence to make decision, such as sequence classification, token classification, or question answering. For tasks such as text generation, you should look at model like GPT-2, obviously. And for the how to use, this is how they are giving the example. Okay, now let's get back to. So first, we are going to define the tokenizer. So the DistilBERT tokenizer will generate input IDs and attention mask as outputs. This is what is required by the DistilBERT model as its inputs. So when we pass text through the tokenizer, the generated output will be in the format expected by the DistilBERT architecture. And now to this tokenizer, I will pass the train and validation set. Text, and then truncation equal to true, and also padding equal to true. So when I say truncation equal to true, that means they will truncate the text according to the value set by max length for the respective model. And for the padding, if set to true, the padding takes quite a few different argument. So here I'm using the boolean. It also takes longest. For example, if I set it at longest, then the pads to the longest sequence in the batch. So here is a documentation for the padding. So true or longest means pad to the longest sequence in the batch. No padding is applied if you only provide a single sequence. And false means do not pad, no padding is applied. Okay, so here I am just doing true. That means it's equivalent to the longest sequence. Well, text, and the rest will just be the same. Okay, and then I also, before moving on, I also need to convert our input encodings and labels into TensorFlow dataset object, that is tf.data.dataset object. So train dataset, that's data.dataset. Yeah. No, sorry, from, because we are getting these data from tensor, so I need to use from tensor slices. And to that you pass a dict of val encodings and then also val labels. Cool. Sorry, so this is my train, so it would be train encoding and train labels, that is all. And for the validation, I will have a different one, which is this. Okay, now I am ready to do my fine tuning. So what I'm going to do is that I'm going to use the trainer class. So I need to import from Transformers, import TF. Actually, I need to import both TF DistilBERT sequence, TF trainer, and TF trainer argument, like this. Transformer. Yeah. And then I just need to update my configuration. So that's my training arguments, all the parameters. And now I need to define a little context manager that would be with training args dot strategy dot scope. And under this context manager, I will define my trainer model, which is this one, from Pretrained, and to that I pass the same thing, which is DistilBERT base uncast. And our number of classes or number of labels are 5, so num labels equal to 5. Cool. And so we are done with that one. Then just the final TF trainer class that I need to define because I already have the args defined. So the final thing that I need to define is a TF trainer. That's it. That will take model as this trainer model, args from this whole args train dataset and val dataset. Then just run trainer dot train. Sorry. Trainer.train, and also after the training I need to do trainer.evaluate. Okay, and when you run this cell trainer.train, that will start the training, and because I'm training for 7 epochs, it will take something like 15 to 20 minutes with a 16 GB GPU in your Colab or Kaggle. So while it's training, I've already put it on training in the Kaggle in Colab session. So while it's training, let's define my saving and after the post training loading of the model variables. So they will just be, let me save it, and then model dot save the trend. Save pretrend, that will take the save directory. Also need to save the tokenizer. Yeah. That is also save directory. And then also the relevant code for loading the pre-trained model. Tokenizer, I'm naming the fine-tuned tokenizer as tokenizer fine-tuned DistilBERT tokenizer dot. So you pass the same class, that is DistilBERT tokenizer, but here only change is that now the from pre-trained, this will, instead of taking the name of the model checkpoint like we did while it was loading directly from the HuggingFace model hub, right now, because I'm loading my fine-tuned model, so I've just passed the save directory where my fine-tuned models are saved. Similarly, model fine-tuned will be TF DistilBERT for sequence to sequence classification to that dot from and save directory. Cool. And now for testing, I will define a test text, taking it from test text. But let's just take the very first row or the very first text from my test text one. Let's quickly print it. Okay. And so when you run this cell, this is what I get. So this is the very first row from the news article of my test dataset. So dollar hovers around record lows. The US dollar hovered close to record lows against the euro on Friday as concern grows about the size of the US budget deficit. Okay, so that's a whole text that I'm going to test my fine-tuned model on. So let's write the code for that evaluation of my fine-tuned model. So for the predicting, first what I need to do is predict input. This is only inferencing code, remember that. So I need to give tokenizer fine-tuned dot encode. First I need to encode this test text, pass truncation, padding equal to true, return tensor is TF because I'm using TensorFlow. Okay, so the output now will be model fine-tuned. To that I pass these predict input and take the 0th element. Prediction value will just be tf.argmax because the previous line will give me the probabilities and I need to get the maximum probability for the whole classification for this entire text. So tf.argmax again, take the 0th element value. And after training, when I run this, the prediction value I get is 0. So that is the, remember, that is the actual encoded class. And what was our encoded class? If we go back to our previous code where we encoded that, where is that? Yeah, here. So we encoded each of the categories or each of the classes to actual numerical value. And what is a 0 value? That's business, right? And that's exactly what this was predicted. This whole text, that is dollar hovers, record lows, all these things, $1 bought 102.55 yen, disappointing business figures, all these, the entire text was classified as business. Then that seems to be so much correct. All right, so that was a fine-tuning result done with TensorFlow. And now I'm going to use the same file that was fine-tuned and trained with TensorFlow to use it with PyTorch to do my inferencing. And we will see that how easy it is to interoperate model files between PyTorch and TensorFlow. So I need to first import torch. Okay. And then port my TensorFlow pretrained model into PyTorch by using a particular parameter called from TF. And that's as easy as it is. So load, let's do fine, let's do tokenizer fine tune PT representing PyTorch. That will be DistilBERT tokenizer dot save directory. So everything is just the same. Only thing I need to just add a single argument and model. Fine. What was the name of that one? Quickly, model fine tuned. PT equal to DistilBERT for why I'm not getting it. Oh, I need to also import the corresponding class for PyTorch. So from this DistilBERT for sequence classification is the PyTorch equivalent class of TF DistilBERT for sequence classification that we used for TensorFlow. So all we have to do is just add TF to get the same model in TensorFlow. We use the same DistilBERT tokenizer, that is to define the tokenizer here, but for the class I need to use this one. Pretrained NED, and that will take save directory. And then the most important part is this extra argument from TF equal to true. So here the meaning of this is that I'm telling that although this fine-tuned model is a PyTorch model, but I'm actually loading the model from a TF format because the original model was trained in TensorFlow. So in the opposite case, if I trained and fine-tuned the model with PyTorch and then I want to load the model into TensorFlow, then I just have to pass from PT. That is, original model was trained on PyTorch, but now I want to use TensorFlow to do inferencing. All right, so that's all that is needed. And to do the inferencing, predict input PT, that would be tokenizer fine-tune PT. To that I pass test. I'm passing the same text. Truncation equal to true and padding equal to true. What else? I need return tensor, which now will be PT. Initially it was TF. Model fine-tuned PT. To that I pass predict PT. Prediction value PT. So previously it was tf.argmax, now torch.argmax. Output PT. I take 0 across dim equal to 1 dot item, and just dot item because I just want to print the value of this one. And that produced as well the value of 0, which is a class of my business. That is, as you remember, this 0 represent the category of business. So for both TensorFlow and PyTorch, I got the prediction value for the text. That for the test text, we got this 0 as the predicted class representing business, and which is very right. And that was a very baseline implementation of fine-tuning DistilBERT for multi-class text classification. And further improvement you can do for any more serious project is that you can do some pre-processing on the input text, that is for the training corpus, Also, you can run for higher number of epochs, or you can do more feature engineering on the input text. Those are just suggestions to improve your result even further. Alright, that pretty much wraps up this video. If you have liked this one, smash the like button. And also do subscribe, because I'm going to do many interesting NLP projects over the coming days and weeks. So see you in the next one. Thank you very much for watching.